Hello everyone, welcome to our Cisco Certified Network Associate Bootcamp. My name is Michael Gibbs and I'm the founder and CEO of Go Cloud Architects and Go Cloud Careers, and I'm so happy to be here with all of you today to talk about networking. So this is a free Cisco Certified Network Associate, a CCNA 200-301 bootcamp, and we are going to cover an entire Cisco Certified Network Associate curriculum. My name is Michael Gibbs, and I've been working in technology now for about 25 years. And you know where I spent most of my life? In networking. Let me tell you a little bit about my networking background, then we'll talk about what we're going to do today, and we'll talk about some of the kinds of training we're going to offer. I am one of the original Cisco Certified Internet Experts. In fact, when I took my Cisco Certified Internet Expert exam, it was a 2-day exam. My number is 7417, and we started counting at 1028 because Cisco thought it would be cool to start counting at 2 to the 10th. So after about 3 million people that attempted Cisco certifications before me, I was the 6,400th guy to pass the Cisco exam. So you know exactly how long I've been in networking. And in these last 20 years, I have trained more cloud architects, more network engineers, more network administrators and systems administrators than I can possibly even imagine. And networking is so essential. Networking is critical. And this is networking skills training. And whether you're a cloud architect, you're going to need this networking skills training. Or if you want to be a network engineer, you're still going to need these networking skills training. So while we're going to talk about Cisco networking essentials, and it looks like network engineer training, and it looks like network administrator training, which it is, guess what? It is also cloud architect training, because networking is one of those critical cloud architect skills. So for your cloud career, for your networking career, we're here. What is a computer network? We'll talk about. This is an intro to networking course, and we are going to talk about networking and cloud computing for the next 2 weeks. It's going to take us 2 weeks to do it because there's so much content here. When we look at the AWS Advanced Networking, we can drop that into about 300 pages. When we're talking about this, it's talking about 2,000 pages. So this is going to be deep, even though it's beginners. Letting you know the format, we're going to go for 3 to 4 hours per day, every day, Tuesday through Friday this week and Tuesday through Friday next week. We will have lectures, we will have slides, and we will have a lot of labs. That's right, you heard me. We will be doing a lot of labs. And here's why. When we talk about routing, I want you to see the packets move through the network. When we talk about BGP, even though it's not part of the CCNA curriculum, but if you guys want some BGP, let me know and say BGP. And you know what? We'll probably do an extra session to talk about BGP, because I want to make sure you can all get that network architect job, network engineer job, solution architect job, cloud architect job, or any kind of networking you want. So this is free network training provided by Go Cloud Architects and Go Cloud Careers. So as we begin, I want to give you some guidelines. There is a very good book, in fact, 2 books, and they're written by a gentleman named Odom. He works for Cisco, and he wrote the books for Cisco Press. He's an old school CCI like me, a very old school. We recommend that everybody buy the 2 Cisco Press books that are written by Vernal Odom. My team will pop a link to these books. They are the perfect complement to this. Guess what? Cisco made the test. Cisco hired one of its own people to write it. This is the book. This is the one you recommend, and we always recommend going to the source. So how are we going to do this? We're going to run our course in the following way. We are going to be teaching our material, but we are going to use the same structure as the official Cisco Press books. So if you follow our course and you read that book, if you're stuck on one section of the course, guess what? You can also refer to that book. Watch our course multiple times, because we're going to leave it here for permanently, and marry that with the book. You will get the full experience. We're going to run this like a traditional $5,000 boot camp, and that's what a good boot camp like this costs. If you were to buy it from Global Knowledge or Cisco. When I was at Cisco, I used to teach systems engineers about service-oriented network architectures and how to design high-performance, high-availability systems. So I've been teaching networking to networking professionals now for 2 decades at some of the world's biggest networking companies. WorldCom, now Verizon. Comcast, I was teaching networking to networking engineers. Riverstone Networks, which is now Nokia, I was teaching networking to networking engineers. And I was even teaching the systems engineers at Cisco Networking. So that's how long I've been teaching networking. So we're going to have fun. How are we going to run this? The following manner: 20 minutes content, 10 minutes of questions. Now, we have a lot of labs. Now, most of the labs start when we get to about chapter 4 or 5 of our materials. But if you guys are getting bored, I'll throw labs in sooner because I want you all to become the best network engineers, network administrators, cloud architects, solutions architects, or whatever you desire. So we are going to have fun. We're going to do lots of labs. Let me know 2 things before we get started. Type hashtag CCNA. And then, while you're at it, right, hashtag CCNA 200-301. Get those 2 hashtags there and let's get ready. If you're watching this content and for some reason while you're watching this content, it feels like you're totally lost, please refresh your browser, because what happens if you join it at a different time or you paused it, we could be in one location and you guys could be in another location. And by doing that, you know what's going to happen? We're going to miss. So I want to make sure that all of you guys make sure you get everything done. So we're super excited to have you here. Now, there are people that have blue wrenches next to their name. These blue wrenches are special friends to Go Cloud Architects. They could be Go Cloud Architects employees, or they could be some of our best students you can possibly imagine. And they're there to help out as well, to make sure that you all have a wonderful, wonderful, wonderful CCNA bootcamp experience. So this is our free CCNA 200-301 course, the Cisco Certified Network Associate. And let's get everybody CCNA qualified. And most importantly, let's make sure you have the knowledge to be successful as a network architect, network administrator, cloud architect, solution architect, or enterprise architect. So let's get to the fun. So to begin, what is networking? And networking is just really the interconnection of devices. And that's all it is. But it's the plumbing that makes everything possible. So if I want to send a message to Chris from my team, I have 2 options. I could drive the message over there, I could fax the message to him, or I could send it over a network. I've worked on all kinds of networks. We used to work on IPX networks and AppleTalk networks, and you name it. There were lots of networking protocols. But guess what? It's simple and elegant for you guys today. There's just one. There's only a single networking protocol that we're working with. Life gets so easy. It's just one single networking protocol and protocol stack. It's TCP/IP that we're talking about, and that's what we're going to be working on. So in this first chapter, in this introduction, we're going to talk about a perspective and a history on networking. Then we'll talk about the TCP/IP networking model, and then we'll talk about data encapsulation. We're going to set the foundation for the things that are to come. So big foundation. Got a lot of stuff to talk about. Again, remember, CCNA is about 2,000 pages of official reading. The AWS Certified Solution Architect Professional is about 500 pages of reading or less. So it's about 4 times the depth of that. So we're going to build some technical competency for you guys here. So let's begin with talking about this. Realistically speaking, with enterprise networking, you're going to be dealing with data centers, etc., and users. And that's really what we're talking about. Now, let's kind of look at it, what networking used to look like. And this was kind of, the world where I came from. So let me show you about the old school networking days. When I started, what happened is you'd have these companies that basically were their own autonomous systems called the cloud, a cloud. And what happened is we all just connected everybody's cloud together. And that was the foundation of a network. But they were all these little discontiguous clouds. So you had the government cloud, the ARPANET, and then you had some educational units, and they would just connect to each other. Well, fast forward a couple of years, in the 90s, guess what? We had more use of the cloud. Now businesses were starting to use it. So what were these clouds they were using in those days for connectivity? They were frame relay, they were ATN, they were BGP VPNs, they were all kinds of stuff. But predominantly the clouds in 1990 were frame relay and ATM. And then around 2000, we got to this concept of the single cloud. What was the single cloud? It's called the internet, which is basically a whole bunch of dissimilar networks that all run their own internal routing protocols that are connected via BGP. That's it. That's what modern networking is. A whole bunch of individual entities that are glued together with BGP. And, we maybe do some BGP concepts. So let's talk about this concept of the TCP/IP model. Now, here's the thing. I don't use this, never have. I use the Open Systems Interconnect model, and we're going to talk about that in depth. But I just want you to know right now, there are two models for TCP/IP networking. There's this old model. And if you ever hear people talk about the link, the internet, the transport, and the application, that's the old model. And what's wrong with the old model? Well, network engineers and architects across the world use the OSI model. That has, and we'll go over it in depth. The physical layer, which is the wire. The network layer, which is the card. The data link layer, which is the card. The network layer, which is the IP address. And the transport layer, which is basically TCP, IP, UDP, etc. When we look at this old thing was some weird theoretical academic model, but we all use the OSI model. Guess what? Layer 1 physical, layer 2 data link, layer 3 network, layer 4 transport. The students we have are really great cloud architects in our cloud architect career development program, and they say there's 7 layers, and I say, yeah, but we only care about 4. And they say, why? I say, is networking is just the wire, the card, the IP address, and the routing protocols, and the transport layer. The rest of us as networking people, we don't care. Networking people, we're not using web pages. We're building plumbing. Networking people, we don't, use applications. And when people ask me how to set stuff up, they're like, Mike, I don't understand. You can design a network with 500,000 employees, 200,000 routes on the routing table, and it's nothing for you, but you can't figure out how to use in because networking people to work on layers 1 through 4. So keep that in the back of your mind when we're talking about these things. Now, when we talk about these kind of protocols, let's think about it. When I say physical layer, I'm talking about a wire. So this is a physical layer protocol. This little earphone set to my iPhones, this is physical layer. It transmits what? Electrons. If it was a fiber optic cable, what would we be transporting? Photons or light. No difference. So if we think about the physical layer, think about the cable. When we think about the data link layer, think about the Ethernet card that's in your computer that you plug the cable into. When we talk about the internet, the network layer, we're talking about the IP address. And when we're talking about transport, we're talking about TCP, UDP. And if you're going to follow the internet model, the one I just showed you, guess what? At layer 7, you've got your applications such as your web pages, your email, etc. That's what we're talking about. So let's talk a little bit about how this concept of networking works. It's based upon a logic. It's based upon a logic of, let's say you go to your computer and you say, I want to go to www.gocloudcareers.com. You request that from the server on a specific port, and the server responds to you. So let's think about this. We do a request to the DHCP server. I want to go to www.gocloudcareers.com to learn about cloud architect training. So we send the request. The web server sends a response. The web server sends another response. We keep sending data. Now, what a beautiful system until data is lost. So when we're dealing with networking, and we're going to get in much more depth throughout the course, but we're just introducing some concepts. When we're dealing with networking, we have 2 ways that we can send information. We can send it reliably, via or non-reliability. And let's really talk about what that means. So I see Abigail Marks is on there with one of the blue wrenches. If I say to Abigail Marks, Abigail, meet me at XYZ location at 4 p.m., I know Abigail for a fact is going to say, Michael, I got it. I'm going to meet you at XYZ location at this time. And I'll say, confirmed. I know full well that Abigail heard me, and I know she's going to be back. That's why she's got one of the blue wrenches. She's incredibly reliable. But the key is that's what's clear. I send a message and she responds. Now, watch what happens, how magical this is. So you go to www.gocloudcareers.com. You send a request. You get a response. Packet 2 is sent to you. Packet 3 is sent to you. Hey, wait, packet 2 is not delivered. See, it got lost. The computer itself, because it's TCP, sends a message back to the web server. Hey, guess what? Sequence number 2, message number 2, I lost it, please resend. Now think about that. Data comes in, you lose it in the transfer, and you ask for it back. Wow. Talk about getting things to be reliable. So if I want to send a 10 terabyte file to somebody, I send message 1. They say, got message 1. I said message 2. They say, got message 2. I say, here's messages 3, 4, and 5. And they say, got messages 3, 4, and 5. And I say, I've sent you messages 5 through 10, and they only got 5, 6, and 7. They say, we need messages 8, 9, and 10, and we retransmit them. So TCP/IP, Transport Control Protocol, is used for reliable data transmission. Reliable data transmission. If you see this on a test, TCP is used for reliable data transmission. And we'll talk about times when you don't want reliable data transmission, because there's a lot of times where this would be a problem. But for right now, realize when things are critical, we're using TCP/IP. Send a file, TCP/IP. Bank transfer, TCP/IP. Writing an e-prescription, TCP/IP, because we need to know that the whole message and its integrity was delivered. So, how does communication occur on the network? You got a wire on both sides, so that's called same layer communication. Now you've got an Ethernet card on both sides. That's same layer. So what's happening is each layer is communicating with each other, and the adjacent layers are communicating with each other. And that's really how this works. So I know right now we're talking high level, and we're going to get into much deeper concepts, but let's imagine we're going to the post office. Let's say here, this is my local post office in Palm Beach, Florida, right near where I'm at. And this is me over here. I want to send a letter. So in order to send a letter to my friend in New York, what do I need to know? I need to know his name, his physical address, the number of his house, the city, the state, and the postal code. Why? Well, if I want to send this to Nick Pappas over there in New York, and when I'm trying to send a message to Nick Pappas, if I'm not careful, if I go to Astoria, Queens, where there's a lot of Greek people, and I'm Greek, my family's Greek, but if I go to Astoria, Queens, where there's thousands of Greek people, just what? I might find 300 Nick Pappases. So if I want to send a letter to my cousin Nick Pappas, as opposed to somebody else's cousin Nick Pappas, clearly I'm going to have a problem, right? And that's why every device on the internet needs a unique IP address, so you know how to send things. So everybody has a unique IP address. So there's a Nick Pappas that lives at 123 Main Street in Port St. Lucie, Florida. There's a Nick Pappas that lives at 16 Pine Bark Lane in Holland, Pennsylvania. There is a Nick Pappas that lives at 3224 48th Street, New York, New York. Postal code this. So that when we go to the letter, what do? We take the letter to the post office. The post office, it sends it to the network. It then drops it off at one post office, to another post office, to another post office, to another post office, until Nick Pappas gets the letter. And Nick Pappas calls me on the phone and he says, guess what, Mike? I got your letter. Wow, it was really nice. Thank you. That's how it works. So keep that in the back of your mind. Each one of these post offices along the way is an intermediate stop. Guess what? In networking, we go to locations along the way, and I'll show you how you're going to trace your way through the network when we do labs, and it's going to be cool and fun. But keep that in your mind. That's how the post office does things. So since in tech, we don't invent anything. We just take the old stuff. We basically smack a new name on it, modify it a new thing, and we're good. So let's look at basic routing. Here's what it's going to look like. Here we go. We've got Larry over here that wants to reach Bob over here at 1.1.1.1. So Larry doesn't know what to do. Larry looks in its routing table and says, I have a default gateway that points to router 1. And then router 1 says, hey, Larry wanted to go to Bob. I now have Bob's message over here on router 1. How do I get to the subnet 1.1.1.1, which is probably a /32? And router 1 says, hey, I know what to do. In my routing table, it says send out this WAN interface to router 2. Router 2 says, do I have a route to 2.2.2? And it says, ding, 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 ding. I have it. It's right over here out this interface. So what does the router do? Router 2 sends it to 3, Bob. Now it's on Bob's computer. Bob's computer has to answer. Does Bob have a route to Larry? No, but does Bob have a default gateway in his routing table? Yes. So Bob sends his data over here to router 2. Router 2 says, do I have a route to get to Larry? And it says, yes, I do. Go out this link to router 1. Router 1 says, do I have a link to Larry? And it says, yes, go out this interface. And then Larry and Bob are talking to each other. That's how it happens. That's exactly how it happens. And what you see here, which we're going to talk about in much more length, is see how you have an IP packet? Then you basically have the transmission control protocol header, and then you've got another header related to the type of packet that it is. So that gives you some guidance of what's going on. And so, for example, we've got it. Let's talk about encapsulation. Every layer, in fact, let's talk about encapsulation for a minute. So every layer in networking talks to the previous layer. So think about it this way. You got an electrical signal, right? That's basically electrons. Now, as we move up a layer, we're transmitting frames. So now we've got the data, which has now got an Ethernet frame attached to it. Then we go up to the network layer, we smack an IP header on it. Then we go to the transport layer and we smack a TCP, UDP, or ICMP header. So with each level of the stack, what we're actually talking about, we're encapsulating and decapsulating. So let's go back to our picture over here. In this particular environment, we've got our data and we're adding Ethernet. So there's always overhead of what we're adding. So let's try to look at it from another angle. The physical layer, we're transmitting bits, which are really in the form of electrons. The data link layer, we've got our data link header. At the network layer, we've got our IP header. At our transport layer, we've got the TCP header. So as you can see, even as we go from data at the top of the application layer moving down, we have to add headers and encapsulations. So each layer talks to the other layer. Now, I know this is the least fun amount of content in the entire program, but we have to talk about it, so please bear with me. It's just very important content, even if it's not the most fun stuff in the world. But it is pretty important stuff, so let's keep talking about it. So now let's looking at the perspectives of encapsulation. You can see segment is layer 4. Packet is layer 3. So what do we have here? We have data TCP. So now when it gets to this layer, we're going to have TCP, data, and IP. And then we get to the Ethernet layer. What are we going to have? We're going to have TCP, IDP. We're going to have TCP, data, TCP, data, IP, and then we're going to smack an Ethernet header on it. So now you know how that works. Okay, so let's talk about the OSI model. And we'll talk about it a little bit. This is a pretty important academic model for us to go over, so just bear with me. Realistically, what we're talking about here is as follows. In networking, we've divided the entire world into 7 layers. And this is called the Open Systems Interconnect model. And this, just so you know, is what all networking people use throughout the entire world. All networking people use this TCP/IP model. And what does that actually mean? It means as following. It means that every layer will talk to every other layer on both sides of the network. So physical layer talks to physical layer. Data link talks to data link. Network talks to network. Transport talks to transport. So let's look at the layers. Physical layer, wire. Data link layer, Wi-Fi or your Ethernet card. Network layer, the IP address, the routing protocols that we're talking about. Transport layer, TCP or UDP. Session layer, we're really talking about sockets, but we don't touch this as network architects, network engineers. Presentation layer, we do nothing here. Now, understand that while we do nothing at the presentation layer, that's where things like TLS encryption occur. And then the application layer is what people use when they go to the web browser to go visit a YouTube video, or when you go to a web browser to look at photos of my beautiful cat Cindy, who everybody knows she's world famous because she likes to chew Ethernet cables, unplug servers, unplug routers, firewalls, run on keyboards, and she's a pleasure to have around the office. I mean, she's truly amazing. But there's that. So kind of keep that in the back of your mind. So let's talk about a little bit more at these layers so you know them once and you never forget them. So I'm not a big acronym fan. I'm a big understanding fan, but a lot of people like to say all people seem to need data processing, and that's the way they remember it. So application layer, guess what? Application layer is is where you use the user stuff. Presentation layer, guess what? Is as follows. Present the data to the application layer and other stuff. So what kind of stuff goes on here? ASCII text, binary things, JPEGs, encryption, that's presentation layer stuff. Session layer, this layer defines how to start, control, and end the conversations. It includes control management of the bidirectional messages that are being sent. Transport layer, this is where your TCP is. This layer provides control of the data that's being sent from point A to point B. So TCP, send and resend, or UDP, just send once and then don't resend. And there's a time where you need both, and we'll talk about that. If you did TCP or reliable over voice or video, you'd have a massive problem. We'll talk about why when the time comes. And yes, some of the concepts we'll probably get into will be CCIE level, and some of the concepts will also be on CCNP level as we do things way above the CCNA, but we have to. And here's the reason. There's a massive difference between certification and getting hired, and I want you all getting hired. So we're biased towards the things that are going to get you hired. So kind of keep that in the back of your mind. Okay, so let's talk about, actually, we've spent about 20 minutes, so let's do the following. Let's see if anybody has any kind of questions, and we'll open it up for about 20 minutes of questions, and we'll get into chapter 2, and we'll talk about the fundamentals of Ethernet LANs. And that should be a really good time for a lot of people. And then at some point, we're going to start doing some labs, hopefully today, but if not, we have labs scheduled for every other day this week. So if you've got some questions, Chris, let's bring in some questions. I'll answer some questions for about 10 minutes, and I want to get back to the content. But I want to make sure everyone's having a good time and no one's lost. Can an IP address be spoofed, Angelo? Absolutely. And that's why we use next generation firewalls. We do stateful packet inspection, and we do a tremendous amount of things because, yes, absolutely. We'll talk about man-in-the-middle attacks and other things during the security section. Chris, you can bring in the next one. The routing protocol BGP has application layer, but what we're doing is all network layer stuff. PR. Good question, though. Chris, you can bring in the next one. At layer 2, what protections are against IP spoofing? Angelo, layer 2. There are no protections against IP spoofing at layer 2. At layer 2, you can do MAC address spoofing. You can do layer 2 access control lists. You can do private VLANs. You can segment via VLANs. You can do layer 2 access lists. You can do 802.1x authentication. At each layer, guess what? We've got different level things. So at layer 3, we can deal with IP things. At layer 2, we can deal with MAC address things, and lots of security there. Now, if you're on the cloud, Angelo, realize you lose most of these great security benefits because they do it and don't give you access to these things. But remember, layer 2, which is in a VLAN or a switch or an Ethernet card, that kind of stuff, we do layer 2 MAC address spoofing and layer 2 MAC address filters and layer 2 things, not IP things. We have to do whatever's in the layer. But that's a good question. Chris, you want to bring in the next one? What is frame relay and ATM? So the first clouds were like this. We would connect you to a cloud and we would create a virtual link for you in multiple locations. The first one that I worked with was actually something called frame relay. It was a very slow, old school networking technique. In fact, the frame relay was pretty much T1 lines, which were 1.54 megabit per second, E1 lines, which were about 2.048 megabits per second, or they were fractional. They'd be 64K links, and that was all we were dealing with. That was frame relay. Now, what happened is frame relay was slow, but the cloud concept worked so well of just connecting to this thing that can connect anybody to anybody that we came up with another cloud called ATM, Asynchronous Transfer Mode. And that was an optical cloud. And we could get to speeds like OC 192, which was 10 gigs. And I was working with this cloud and these 10 gig links about 20 years ago. So you can imagine how fast these links were, these OC 192 links. But they're just old school WAN and cloud technologies. Great question there. Why do you focus on 4 layers, Ryan? Because that's all networking is. Networking isn't software engineering. Networking isn't using applications. Networking is simply the wires, the cards, and the communications protocol to get them there. That's all of networking. So it's kind of like, why does a race car driver not learn how to fly a plane? Because race car drivers drive race cars versus pilots that fly planes. Networking is extremely specific. And we focus on those 1 to 4 layers. And Ryan, I could give you 500,000 pages of reading that only focus on those 4 layers, and you'd still need to learn 80% more after 500,000 pages of reading in 25 years. And that's why networking people like me, my world is focused on BGP. And even BGP is a big chunk of networking. And that's enough to build an entire career, just knowing BGP. In fact, you could build a career in a subset of BGP by being so good at it. Great question there, Ryan. I think we have time for 1 or 2 more, Chris. Hey, Mike, application layer is so much confusing to me. Why is BGP considered application layer? Okay, an application is only this. An application is something that does something. So when you get on your cell phone and you click Slack, that's an application. When you get on your cell phone and you text message somebody, that's an application. BGP itself is an application, but we don't use the application. What we use is the networking features of the application. Network layer reachability. Send me a community and match the community and prepend the AS path. Send a community and change the weight. Send a community and change the local preference. Filter or route with a distribute list, a mount path. Everything that we do as network engineers is layer 3. So, sure, you've got a camera. The camera itself you could call layer 7, but the film you could call layer 3. And the photographer only uses layer 3 and down. Now, if you hand it to a movie producer that's going to take the film and edit it, they have another job. But network engineers, we don't touch applications. We don't do any of that. Layers 1, 2, 3, and 4, that's all we do. That's our whole world. Okay, good. Good PR. Excellent. So, Chris, I think we have about 4 or 5 minutes before the next set of questions. Rohit, what's the difference between frames and packets? Great question. At layer 2, we have frames, which are layer 2, and at layer 3, we have packets. That's it. What's the difference? Remember, we go from a packet, which basically is going to have the TCP or UDP header, the data, and the IP header, to the frame, which is going to have the TCP header or the UDP header, the data, and the IP header. And now it's going to have we're going to smack an Ethernet header on it, and now it'll be a frame. Does a layer 3 switch have the same capability as a router? A layer 3 switch is a router. A layer 2 switch is a switch. What happened was we used to separate them, and then we decided to put them in the same device for speed and performance. Is there a difference between TCP and UDP frames? Well, there is no such thing as a TCP or UDP frame. We have frames at layer 2, we have packets at layer 3, and we have segments at layer 4. And yes, there is a difference because they're basically using a different transport control protocol. And we'll get to much more of that throughout the course. What is the difference between UDP? TCP is used for reliable transport, meaning I send something and you say, yes, I got it. I send you something else and I say, you got it. UDP is me just sending you data as fast as possible and hoping you get it. And there's a time and a place for that, which we'll cover throughout the course. Great question there, Mohammed. How does the sender know the MAC address of the receiver? Sadie, good question, and we're going to talk about that. There's a protocol called ARP, or Address Resolution Protocol, where when a host wants to say something, it says, ARP, who has the MAC address for this specific IP address? And it's a big screaming broadcast. And of course, we've got a whole chapter dedicated to that. What do I mean when the layers really talk to each other? Explain in simple language. Okay, so you've got a wire, and you send electrons on the wire. and then you go up to an Ethernet card and you plug a cable between them, and they communicate via the Ethernet format because they're Ethernet cards. Then you have an IP address. That's like a physical address on your house, and the routers route packets to each other based upon their IP address. So you've got a transport layer, which determines whether you ask to see if it's retried or not, and they use the same segment. So I hope I answered your question there. Each layer talks to each other in the layer that it matters. If it's a fiber optic cable, it's going to be photons or laser or light that goes across the wire. That's what we mean. Chris, I think we can probably do one more. Okay, so if you're new to networking, there's a couple of things. I do want you to buy the book that we talked about, the official Cisco terminology book. Now, I'm not using any jargon at all. I'm just using the industry standard terms. So, if you don't know, please look the terms up. Please follow along. Chances are all these questions that you're going to ask, we're going to get to in another section. We just haven't got to it yet. We have 1,000 slides and we're on like 30 something. So we've got a lot that we have to get to yet. And then it'll become familiar as we go through the concepts. So unfortunately, I can't I can't spend 8 hours on every specific word, but if you bear with us throughout the time, we're going to get through the content if you just keep paying attention. And we will get through that content and it will become abundantly clear to you. But, I don't get any benefit when I say, hey, buy a Cisco press book. I'm not an affiliate to anybody. I don't get paid anything. I just want you to go to the official sources. I worked for Cisco for a decade. I'm an official source. The Vernal modem that I talked about is an official source. Cisco paid him to write this book to prepare you for the exam. So where do you think they're going to get their exam questions from? That Cisco book. But I get no benefit from it. I just want you all to be maximally successful. That's why I'm recommending somebody else's product other than mine. Combine mine with theirs and you will have extremely good success. And like I said, I get no benefit out of it, but I get the benefit of knowing you all get hired. So let's talk a little bit about local area networks and kind of keep that in the back of your mind. And as architects, we are front and center. We try not to hide behind slides. I know engineers like to do that, but I'm an architect and I want to teach you how to present naturally, not hiding from behind the corner of a slide. There are times where I have no choice but to do it, but that's a last resort. If any of you guys have architecture careers in the future, make sure you can't hide in the corner of a slide unless you have absolutely no choice. So that's why we'll be out there front and center the whole time, because I want you to learn how to do it the way we want you to do it to get cloud hired or network hired. So let's talk about what is a local area network. A local area network is just this: communication in a small area. So your house, a physical campus, are all different forms of local area networks, and they all look a lot different. We'll show you some basic networks, what they're going to look like. So at the basic smallest element of the world, this is a small office, home office network. Bear with me 1 second so I can find, okay, here we go. So in this particular environment, let's look at a small office. Now this might be something you've seen before. You go into the office, they've got one router to the internet, plugged into a switch, or it has an integrated switch, and there's a couple of ports on it. Guess what? This is your Starbucks. This is my home. Well, not really, because I've got enterprise-grade firewalls and IDS and IPS systems and enterprise-grade switches, not this. But as a general rule, this is your small office, home office, your doctor's office, your Starbucks. It looks just like this. Now, it's a wired LAN. Anything that matters should not be on wireless. I'm going to say this again. Anything that matters should not be on wireless. Guess what? Anything that matters should never be auto anything. Anything that matters, you'll statically hard code IP addresses. You will statically set the speed and duplex of your ports, and we will get to that in extreme knowledge. But keep that in the back of your mind. We have to do these kind of things. So this is a small office. Now, this is an even smaller office with Wi-Fi. Basically, you've got a router. The router typically controls an access point, which is a layer 2 wireless device that enables your users to work. And that's your pretty typical types of environment. And what is the medium for this? How are they communicating? Some flavor of Ethernet. So let's talk about Ethernet standards, because there's a couple of standards. So in the old days, people like me got to work with these 10 megabit per second Ethernet networks, and wow, they were fast for us in those days. Because remember, we were dealing with like 64K WAN lines at best. So 10 megabit per second was huge. But this was 10 base T. It used to be coaxial cable, or it could have been Cat5 cable. And the standard for this was 802.3. That's the standard of internet. All internet standards are 802.3. Okay, so then, now mind you, when these things were 10 megabits per second, I was working in networking. The routers, a big $5,000 Cisco 2500 series router could pass a massive 1.5 megabits per second of throughput. So this router was 6 times faster, this Ethernet port, than the routers could do in those days. So then we had bigger routers, and we had fast Ethernet ports, which were 100 megabit per second. And then we had incredible speed. We had these fiber optic connections that could go a gigabit per second over fiber optics. That was your 802.3C. And I remember putting these things in with the optics in these switches, and wow, it was fast, high performance, and we were all excited. So that was kind of cool. Then, and it looks like my screen is freezing. Then we came out with gigabit per second things that we could use with a coaxial cable with Cat5 and Cat6. And then we came out with 10 gigabit per second ports, fiber optic. And now my computer has two 10 gigabit RJ45 copper ports. How amazing is that? It shows you how fast we've gone. So we've really, really gone fast. So let's talk a little bit about this. Let's talk about the way Ethernet frames work. So at layer 3, we have packets. At layer 2, we have frames, and frames are a little bit different. So let's talk about these frames. Okay, so the way this is going to work is it's going to work as follows. It's going to look like this. Your computer is going to be sending data to the switch. The switch, realistically speaking, is going to be in a position where if it doesn't know what to do, it's going to literally forward the frame out all ports except the port that it came in on. And then if the switch doesn't know what to do, it's going to forward the port to all ports except for the one it came in on, and then it's going to forward it to the host. So in this situation, what's going to happen is you're going to have a PC that's going to be sending frames to the switch. Now the switch will look and say, do I have a MAC address in my MAC address table? And if it does, it knows where to send it. And if it doesn't know where to send it, it's going to send it out all ports until the port that it came in on. And that's exactly the way that's going to work. Okay, so the way this works is you're going to have a set of wires. And I've never made an Ethernet cable in my life in 25 years because I'm an architect, and architects don't do that. But tremendous number of people that I know, and lots of network engineers and all network administrators, are going to do this at some point in their career. And basically what's going to happen is you're going to have a wire, and it's going to have a pair of, And on one side you'll be transmitting, and another side you'll be receiving. And that's why you can transmit and receive at the same time, which gives you something called full duplex, the ability to send and receive at the complete and total same time. So let's talk about the components that make this possible. Each device has its card, the card that occurs in the data link layer. You plug in the card to the data link layer, it goes into the node, and they communicate with each other. And you've got a set of wires, transmit and receive. So let's talk about what these RJ45 connectors and ports look like. Well, I'm sure you've seen one of these Ethernet wires in your own house. And for example, I'm sure you have an Ethernet card in the back of your computer. And also, I'm sure you've plugged into a switch, and that's really what it looks like. Now there's all kinds of switches, but that's your RJ45 port. Now if you're dealing with a switch, and the switch could be any kind of switch, it could be one of these switches, note, there's an optical port attached. And those switches can be they can be something that looks like this. Here's another switch that I have sitting in back. What you'll notice is all these ports are RJ45, and these are 10 gigabit per second uplink ports that are fiber optic. You stick a laser in them. Let's do some questions real fast, and then we'll get into there.
All right.
Cat hired. I love it, Millicent. Yes, Cindy has been hired. Sunny is hired as well. And yes, we love our furry friends around here.
All right.
So a switch is a device that enables you to plug a lot of devices into a single subnet. And we'll talk about subnets, and we'll talk about switches versus router, but a switch is where you plug all your devices in to the network. Good question. Chris, you want to bring in the next one? Are there any prerequisites for these lectures? No. The Cisco Certified Network Associate is a foundational level, but we have 8 3 to 4 hour days, so we're going to cover it all. But again, remember, cloud computing is silly easy. The network, the reason people are going to cloud computing is because they have less management worries about the network. But here's the thing. If you don't worry about the network in your cloud computing environment, everything falls apart. So there's no way of getting around the networking thing. If you want to be a network engineer, network architect, and if you want to be an actual cloud architect or solution architect and actually work and get paid and have a good job, you have to know this networking. So we're starting at the bare minimum 0, and we're going to work our way up very, very significant. Coming quick.
The next one's not quite a question, but I found it hilarious.
Okay. Yes, there is a cat that is eating my Cat 5, 6, and 7 cables. Yes, absolutely. How is the TCP protocol responsible for error correction? Eva Doikia, what a question. So, Chris, I want you to acknowledge messages. Chris is now the computer on the other end. Chris, I sent you a picture of Sunny. Did you get it?
Yes, so cute.
Chris, I sent you a picture of Cindy and Sunny this time. Did you get them?
Yes, yes.
Chris, I sent you a picture of Cindy and Sunday. Did you get it? Chris, I sent you a picture of Cindy and Sunny. Did you get it? Okay. Chris didn't get that. I'm going to resend the data to Chris. So that's what TCP is, and that's why it's reliable. Because what happens is in about 3 seconds, Chris is going to say, hey, Mike, do you mean to send me anything more? I got your first 2 packets, but not the last one. That's exactly how TCP does error correction. But there is also something on there called the frame check sequence and a CRC code that's also going to tell us if things are damaged along the way. Can I please explain about the session layer? The hashed. I am a network architect and a network engineer. I just told you that network architects and engineers only do layer 1, 2, 3, and 4. We have nothing to do with the session layer. So in 25 years, I've got no experience with the session layer because guess what? I'm a networking person. We don't touch the session layer. Yeah, I probably should check my fans for cat hair. They're in a lot of places. Kylie, what a beautiful cat you have there. What a pristine, beautiful Siamese cat.
And I feel like this is prescient because it was your first thing to do. Troubleshooting 101.
Yeah, absolutely.
Yes. That's the old
It
show.
really is. Now, if it's a router, we're not going to be doing that. With the router, we're going to be looking at the routing table and doing trace routes, etc. But with a hobbyist router that you would have your home, yeah, reboot it. With a Cisco or a Juniper router, no, we're going to get in deep and figuring out what's going on. But you know what? Somewhere along the line, we're going to reboot it. And I got to tell you, that'll fix 20% of the problems. The problem is you can't always do a reboot in a production environment. Yeah, there actually is only 2 pairs that you're going to use, and we're going to talk about that coming very soon. Again, I've never made an Ethernet wire because I'm a network architect, not an engineer, but guess what? We'll talk about those 2 pins coming up very soon. Of course, Terminator 365. I used to teach these courses for Cisco. I used to teach Cisco engineers, and I've been teaching engineers for 20 years. I've gotten more people Cisco certified. This is enough. It's more than enough. This is the same as if you paid Cisco $5,000 to take the week's class. You're having it being taught by an ex-Cisco employee. It's identical. So yes. Routers don't use spanning tree. Routers use layer 3, so we don't have that problem with layer 3. Throughput is the amount of stuff you can shove through there. The bit rate and the data rate is the amount of stuff you're shoving through there. They're very similar. Meaning I could have a throughput, I could have the ability to do 100 gigabit per second throughput, but my application may only be streaming at 10 gigabit per second, so I have 90 gigabit left over. That's the bit rate. Good question there. Yeah, I'm more used to debugging, but I got to tell you, after having a cat around, I do more debugging from the cat than other things. Thank you, Angela. My video feels better. I could see on my screen and then I couldn't figure out why, because my GPU was only at 30%, my CPU was only at 4%, and my memory, I still had almost a full half a terabyte, but don't know why. It's working though. Can you apply spanning tree on a router? You would never apply spanning tree on a router. Well, the whole point of using a router is so you don't have to use spanning tree. And you can route between subnets as opposed to bridging. Spanning tree is the ugliest thing. I will tell you that I spent a career removing spanning tree and replacing it with layer 3 links. Yes, we're going to leave these recordings on YouTube.
Sorry, I didn't mean to interrupt you. My finger got a little happy there.
That's okay. No, but we're going to leave these questions on YouTube. And these are good questions. Sadie, as a cloud network engineer, yes, you need to know layer 1. Yes, you need to know layer 2. Yes, you need to know layer 3. And yes, you need to know layer 4. Because if you really want to be a cloud networking engineer, you're going to be setting up software-defined networks to the cloud. BGP to the cloud, you're going to be prepending ASs, changing the weights of ASs. So you're going to need a whole lot more than just the CCNA as a cloud network engineer. You're going to need somewhere between the level of the CCNP and the CCIA level knowledge to be acceptable. Yes, absolutely. How many times does TCP retry? Well, that's based on how you code your application. But we network architects don't worry about that. We worry about layers 1, 2, 3, and 4. This is absolutely live. How long is this course? Great question. If you signed up for the course, you would know that we're having this course for 3 to 4 hours per day for 2 weeks straight on Tuesday through Friday. Where do the lost packets go? They just disappear. They reach their time to live and they just die out. What resources do you think are enough for passing? The resources that I recommend are the official Cisco Pressbook and this course and nothing else. The official Cisco Pressbooks that we listed and provided a link for in the beginning of the class, they're what we recommend, and we recommend this. Those two is the perfect combination. Okay, so Angela, we can do copper or we can do fiber. It's our choice. Most switches use optical networking ports for 10 gig, and the reason they do is twisted pair is only good for 100 meters, and copper and fiber optics can go for miles and miles and miles. So people assume that you need from switch to switch communication, longer cables, longer distances, and they always do it via fiber for those reasons, because you could have an Ethernet WAN, etc. That's a very solid question there. And Chris, I think we can do one more, and then we got to get back to the content.
All right.
Why should there be no specific stuff on wireless? Because wireless is incredibly unreliable. If you basically take your phone make it the Wi-Fi access point for your PC, and then do an extended ping to Cisco for about an hour. You'll notice that you're going to lose about 5% of your data or more. You're going to notice that some of your data takes 2 milliseconds and some of your data takes 200 milliseconds, and the connectivity is going to be horrible. Also, wireless is what's called the shared medium, and we'll talk at some point about hubs and collisions. So if you've got 1 gigabit wireless, it's only good for 100 megabit due to collisions and people transmitting, retransmitting. So wireless is never used for anything that matters. Neither is auto. Okay, so let's get back to the content. Actually, before we do that, if you can type hashtag CCNA in the window, I know you're all here and paying attention.
I want to thank everybody for letting me entertain you with pictures of the cats. If you have any pictures of cats or dogs or gerbils or hamsters or chinchillas or zebras or anything that's a pet that you're legally allowed to have, please send them to admin@gocloudcareers.net. Admin@gocloudcareers.net. You can also send any questions that you might have for us. But send a picture of your pet also.
So going back to this, when we're dealing with Ethernet, we're dealing with twisted pair cables. And basically, you've got one for send, which goes transmit to receive, and one for receive, which goes to the transmit on the other side. And that's why we can talk in full direction at both times. Transmit wire, receive wire. If not, like the old days, like wireless, we transmit, and if we're trying to transmit and trying to receive at the same time, our data collides and we have to start all over again. It's really, really ugly. So this is why we're dealing with twisted pair. Now, a straight through cable, which is normal, is going to have pin 1, which goes to pin 1 on the other side. Pin 2, which goes to pin 2 on the other side. Pin 3 and pin 6, they all talk to each other on the same side. This is called the straight through cable. Why? You plug your PC into a switch, you plug your router into a switch, and that's the way this is supposed to work. They communicate via the switch. Now, if you want to connect a router to another router or a switch to another switch, that changes everything. So I'm going to look at this one more time. Switch to device. Straight cable, same pins on both sides. But if you want to go from router to router or switch to switch, then we have to change everything. We have to flip those cables, and that's called a crossover cable. So router to host, straight through cable. Host to switch, straight through cable. Router to switch, straight through cable. Network device to network device, crossover cable. PC to PC without a switch, crossover cable. So straight through anything that connects through a switch. So how's that going to work? Router plugs into this port, switch plugs into this port, everybody's happy. But if this switch plugs into another switch, we need a crossover cable. Assuming it's on a copper port, not fiber optic. Don't put heavy metal things on your head. It's not good for your neck. So here's an example. Switch to switch, we're running crossover cables. And you can actually see what the wires physically look like with a straight cable. And here you can see what some fiber optic cables look like. I'm not a layer 1 guy. I've been a layer 3 guy my whole career. But what you're dealing with when you're dealing with copper is you're dealing with the core. This is where your laser sends the light. And then you're dealing with basically something that protects it. And then you're dealing with something else that protects it, something that makes it strong, and then a jacket. So that's how your stuff is kept from falling apart. Kind of keep that in the back of your mind. And you can see you've got your photons that are pushing through the core of this. Again, I am not a layer 1 person, but kind of keep that in the back of your mind. So people ask, why are we doing fiber for some? And then what do you call it? copper for others. And here's the reason why. With Ethernet, we're good for 100 meters. Everybody say it. Ethernet, Cat 5, Cat 6, Cat 7, 100 meters. Now, what if you have a campus and you've got a kilometer between both buildings? Well, guess what? It's still local, but now we can't use copper. What if you have 200 meters between buildings? Guess what? We still can't use copper. I mean, we could take a 100-meter cable, plug it into a switch, and then plug it into another cable. I guess we could do that, but then we'd be sticking a switch in the parking lot or burying it underground, so that's no good. So for any distance that matters, what do we use? Fiber. So let's look at the different kinds of fiber. When we deal with single mode fiber, we can go long distances. When we go multi-mode fiber, it's short distances. Why don't we always just use single mode fiber? Cost. Multi-mode fiber is cheaper by far. So what do we use? In the office, we use things like multi-mode fiber because it gives us good speed and performance. But look, that's good for 300 meters, 400 meters, not much. What if we want to go to the internet's point of presence, 10 kilometers, that's 6 miles, that's better. How about this, 30 kilometers or 18 miles, that's getting better. So as you can see, we're using fiber for long. So let's think about the cloud environment. We want to create a direct connection to AT&T or an express connection to Azure. What do? We get a single mode fiber connection to the direct connection location. And we connect that to another switch with a simple cable. And then from there, it gets called back to the AWS network or the Azure network, all on this long distance fiber optic kind of connections. And I'm not really sure what I just did there, but it made it look pretty ugly, but we are back to normal. So, now you understand that. Now let's look at a different kind of cabling. Let's look at the cost of it. The copper cables, cheap. The multi-mode fiber, you're starting to pay for it. Single mode fiber, this is getting expensive. Now let's talk about the part on the switch. Copper ports, cheap, cheap, cheap. Multi-mode, you've got to buy a laser, an optic. It's starting to get expensive. Single mode, you could be paying thousands of dollars for the port. Going back to the distance, copper, 100 meters. Multi-mode, no big deal, half of a kilometer. Single mode, wow, you've got some distance here. So copper, electrical signaling interference. Laser, none. So switch-to-switch communication. Do you want to risk crosstalk on wires or electrical interference? Oh no, your switch-to-switch links are critical. So that's why you're using fiber optics between switches. So let's look into the Ethernet frame, because you do need to know this. This is what your frames look like. So letting you know, any frame less than 64 bytes is called a runt. Any frame less than 64 bytes is called a runt. Any frame above 1500 bytes is called a giant. Any byte above 1500 bytes is a giant. So if anything less than 64 bits is called a runt, which is not good, and anything that's above 1500 bits is called a giant or a jumbo frame. Keep that in the back of your mind. If you have a network and you've got a frame that's 2000 bytes and your network can't support a payload of 2000 bytes, guess what? Everything falls apart. So you must know what's in your frames and your frame size and your header size. But less than 64 bytes, not right. Greater than 1500, specialty frames, you must tell the network to be able to accommodate them or else it won't. So what goes into this header? You've got a preamble which tells you something. This is the destination MAC address. This is the source MAC address. This gives you some information. Here's your data, and here's what's called the frame check sequence. It basically is like a hash, something that shows you if the message has been damaged in the process. So that's kind of what we're talking about. So reading it through another way, the preamble does some synchronization of the messages. The starter frame delimiter begins to tell you the destination MAC address. In the source MAC address, we can see the center of the frame. The type will tell us whether it's IPv4 versus IPv6. The date is obviously how much kind of data you put there. And then the frame check sequence is really about making sure your data got there in an undamaged manner. So just kind of keep that in the back of your mind, and then you're going to have a really good kind of concept. So let's talk a little bit about MAC addresses. So every device that you have has a hardware address. In Frame Relay, we had a layer 2 address, and it was called a DELC. In Ethernet, we have a layer 2 address, and it's called the MAC address. So if you bear with me, if you go to a command prompt or a terminal prompt on your computer, if it's Windows, type CMD on your computer. If you're on a Linux or Unix system, type ifconfig. So if I do an ipconfig/all on Windows, that will tell me what? It'll tell me, go do this on your computer, ipconfig/all or ifconfig in a terminal. Right now, you can see, if I look at mine, I can see my IP address. I can see that my MAC address is as follows: Foxtrot Charlie -34-9 Alpha 0 Foxtrot Delta -16. That is the MAC address on my computer. It is a physically hard-coded address on your computer. While we're at it, everybody, type your own MAC address in the chat box so I know that you've known the layer 2 MAC address of your system. Type your MAC address, type MAC address, and then list your MAC address, and then I know every one of you, and no, we can't connect to you on your MAC address. Your MAC address is way behind your routers, and then we know that you've got it. So keep that in the back of your mind. ipconfig/all, you'll see it, you'll see your MAC address. So let me give you an example of what it's going to look like. Got a user over here. User is sending data. Push. It gets to a switch. The switch works by looking at MAC addresses. So the switch will do this. If the switch knows the MAC address, it will send it directly out the port. If the switch does not know MAC addresses, it will flood out of every single port that it has. So data gets to switch 1 floods it out of everywhere. Floods out of switch 2 to computer 3. Computer 3 says, I have this MAC address. Switch 3 puts it in the routing table, or the MAC address table. They call it a content accessible memory, or CAM table, so it knows which port to send it. So what does it look like? Let's say over here, we're back to my trusty rusty switch. Basically, a packet comes into the switch on this port, and it's destined for MAC address, Foxtrot Charlie -34-9 Alpha 0 Foxtrot Delta -16. And let's say this, the request comes in on this port, it'll get flooded out on every other port on the switch. And then all of a sudden, this computer will say, I have that MAC address, and then the switch will know to send it directly out that port and no other ports. So good job. I see lots of you guys have found your MAC addresses. Woohoo! You found it, now you know. Guess what? While you're at it, you can probably see your IP address there too, right next to it. You'll be able to see your subnet mask. You'll be able to see your DNS servers, and you're going to see it all. So now you know how to find the IP address and the MAC address on your computer. Now, when people ask me why we don't do wireless and why it's not reliable, here's the reason. We used to have this concept in networking called the hub. And then we invented a switch 20 years ago. Now, for some of the AWS certified people, I know there's a certification provider that calls switches and hubs. They couldn't be more far apart than you can possibly imagine. A hub does this. A hub basically creates wireless. So here's what a hub does. And here's what wireless devices. You have two PCs on the same network. And they're either a hub or they have Wi-Fi cards in them. Same thing happens. Here's what happens. Computer 1 and computer 2 both try and send data at the same time. Now, what happens is because they're in a non-full duplex environment, it's like two people shouting at each other, I am here, I'm here, I'm here, I'm here. Now, if two people are screaming, can anybody hear anything? Not at all. So what ultimately happens is that wireless, and in the old hubs, which we haven't used, thankfully, for over 20 years, the two computers would talk at the same time. And then computer 2 would say, okay, I can't talk because computer 1's talking. And computer 1 would say, I can't talk until computer's talking. So they would both stop talking, and then randomly, computer 2 would say, I have to speak, and then randomly computer 1 would speak. And guess what? Hopefully that worked. Now we add 3 computers. Now we've got 3 computers. The chances of them speaking goes up together. Now we add 30 computers, all in the wireless. Now, if any one of the 30 speaks, the other 29 cannot speak at the same time. And if they do, they both collide and their data collides and they both have to restart transmitting. So that's why hubs are not reliable. And that's why wireless is not reliable, because the wireless network may say 3 gigs. But if you've got more than a couple of users, you're never going to get more than 10% of the capacity out of it because of these collisions where everybody's talking at the same time, colliding. So imagine giving a presentation with 1,000 people screaming in the same room at the same time as loud as you. Nobody's hearing you. So that's why we don't use wireless for anything that matters. Because if I'm on my phone here right now, let's say I wanted to say, okay, how many YouTube subscribers do I have? If I check this, and guess what? I can't figure it out. It doesn't matter. Wireless. Now, I have a medical application, an application where if a doctor can't open the application, they won't have access to the patient's information and somebody dies. I'm using wireless. Someone's going to die. Why is somebody going to die? Because 2 people are going to be trying to send data at the same time. Everybody's going to back up the data. We might have 50 nurses and doctors at the hospital on the same network. They're all trying to pull data. They're all talking at the same time. Everybody backs off, and nobody gets any data through. So that's why we never use wireless for things that matter. That's why we haven't used hubs in 20 years. The collisions. So if everybody was in a hub, everybody's data is going to be talking at the same time. But when you're in a switch, it's just you and your own switchboard, except for the broadcast that gets sent on every port. So we're going to talk about that. We're going to talk about broadcast domains at some point and collision domains. Not now. It'll be in the content. Now, by comparison, this is full duplex. Because it's full duplex, this person can send, and a switch can send and receive, can send at 100 megabits per second and receive at 100 megabits per second. This is great. Now, this device can send at 100 megabits and then, oh, wait, this person over here was crazy and plugged a hub into the switch. Now, this is half duplex. Now, if 2 or 3 users are plugged into this hub, every time this user tries to speak and somebody else tries to speak at the same time, they're going to back off and no data is going to go through. So keep that in the back of your mind. That's what we're actually talking about. So we're going to actually start into getting some fundamentals of WANs, which is going to be really fun. And then we're going to start talking about things. So let's continue with the content. Unless anybody wants to take 20 minutes and actually get a feel for what is a Cisco router and then go back to the content. So if you'd like us to do a 15-minute lab to do a walkthrough of the router, I'm up for it before we start the next session. Let us know in the chat box below. Or if you want us to keep with the content, say keep with the architectural content and the knowledge content, and I'll do that. So let me know. You choose your own destiny, but I'm going to make sure you have a good time either way. Type lab if you want lab. Type more content if you want more content.
And remember, we got a bit of a delay. So here are the responses. I'm not surprised by this.
I'm not surprised by it at all. So let me do this. We may have to reset my EVENG server up with OBS, but I'm not sure. So let's see if we can do it first without it. So let's do EVENG. It looks like most people want to do a little bit of lab. We'll do a quick lab, and then after that, we'll get back to, we'll do some questions, and then we'll get lots of content. But let's have some fun. Let's do a little bit of tech content. Okay, while we're at it, how do I do this? Okay, let me go to EVENG. Can you guys see it? Okay, nope. Let me go take care of this. Properties. Okay, woohoo, we got it. Okay, so let's do a nice little lab. Let's just walk into this. We'll call it Cisco router.
Can you make your window, your browser window bigger?
Yes. Okay, so here's what we're going to do. And if any of you guys ever wanted to do a real network simulation, there's, Cisco has a viral program, and there's EVENG. So you can buy a rack of Cisco routers, and that's great. Or you can set up an EVE-NG server. This is a professional EVE-NG server. You can replicate cloud environments with it. You can replicate routers, switches, firewalls, etc. So in this case, we're just going to create a Cisco router, and we're going to go play with it. I'm going to walk you through some basic intro to the router. So,
and Mike, before you get started, I want to let everybody know we can't zoom to make text bigger on this. We can zoom in to make the diagram bigger, but we can't. There's going to be pieces where there's text windows because of the nature of this program. We can't zoom in on text in those specific windows. So we recommend that you go full screen if you're on YouTube.
Absolutely, and letting you all know, EVE-NG is used by every major company right now to test and run simulations. So we're using the most common, most industrial grade thing that you can find. So we've created a device. We're going to turn on the device. Now, when you boot up a router, if you're connected to what's called the console port, and we'll get to that, what you're going to see is it's going to turn on like this. And you're going to see it boot up. And what happens is there's some flash memory. And on the flash memory, what you're going to find is it's going to have an operating system, and it also has a type of RAM where it'll have your configuration. But this is a brand new router. So it's going to boot. It's going to take longer than I wanted to, which is going to be annoying. It's going to read us all of our copyright information. It's going to tell us about the cards that are in the router. And we should be pretty close to it being booted up. We're going to do lots of router stuff this week. I will tell you, the person asked CCNA versus AWS Certified Solution Architect Associate. The AWS Certified Solution Architect Professional doesn't hold a candle to what's inside the CCNA. The CCNA is about 4 times deeper than the AWS Certified Solutions Architect Professional. To put it into context compared to context. We're using this, not packet tracer, because we're using a bigger, more industrial solution, not one that's more of a temporary thing. So when these routers come up, here's what you're going to have. You're going to have it say, do you want to enter the initial configuration dialog? This initial configuration dialog that you're using is, guess what? 30 years old. It was an auto questionnaire. What do we know about auto anything in technology? It will destroy anything you have. Auto anything is bad. So we're never going to use auto. So it asks if you want to use auto configuration. And for, guess what? 30 years, Cisco has taught people not to use this. Because auto is good until it doesn't work. So now your systems come up. Now it's giving us some information. It's telling us about the type of cryptography that's installed on this. And pretty much we're rare. So when you get to the router, you're going to see something. This is a brand new bank router. It says router. They come out of the factory like this. And yes, those messages you see on the screen like that, that's called the syslog messages. And these routers will be spewing these messages constantly. And we'll have thousands of devices all sending off logs. So we collect logs. Logs tell us a lot. So if we want to do anything with these routers, we have to go from what's called user mode to privileged executive mode. I didn't make up the term. That's also called enable mode. How do we get to enable mode? We type enable or en, but I'm going to use the full word. Now look, kind of like on a Unix system. Note how you go from this greater than prompt to this hashtag prompt or the number prompt. That means you're in enable mode. So now I can do things. I can look at the configuration of this, show running config or show run. You can see certain things that are here. It tells me the version. It tells me the current host name of the router. It's going to tell me the type of switching it's using. It's using Ceph. It's telling you the IP addresses, the speed and the duplex of these things. So, for example, if I want to change the name of the router, if I want to configure the router, I type config, and we type terminal, but org t. So now note it says router/configuration. So let's think about this. Every device we're going to put a management address. So, but let's give it a name. If the device says router, we're not going to know what it means, right? Imagine just having, I work on networks that have 10,000 of these things. Imagine not having a name. So let's just say host name. Let's make it simple. Let's call it router 1. That's what they would do in a CCIE exam. And I probably didn't spell it right. Okay, I didn't. Okay, now it says R1. Notice it says R1 instead of this. Okay, now what if we were to put a name, put a management port on this? Let's say we call that a loopback address. And we'll talk more. We'd create an interface, and then we give it an IP address. Let's say 1.1.1.1. And then it's going to need a subnet mask, 255.255.255.255. We'll go heavily into subnetting. Don't worry. I forgot to type the words address. So ADDR is enough. We'll turn on the interface, no shot. And poof, now you'll be able to see if we do a show IP interfaces on this router. That's going to give us too much information. But you're going to see, I could help if I could type. You're going to see that I just created an interface called a loopback address. You can see that this is the IP address. Note, this router has 4 Ethernet ports. Note, they all say administratively down and line protocol down. So what does that mean? Well, if we look at this running configuration, look at the interface. Interface gigabit Ethernet, no IP address, shut down, duplex auto, speed auto, media type. Do you think I'm going to leave anything to auto in reality? No. What am I going to do? I'm going to manually do this. So I'm going to type config T. I'm going to give it an IP address. Let's come up with 172.16.1.1. Let's give it a /30-bit mask because that's what we typically use on a WAN link. And we're going to be explaining what all this means. I just wanted to give you guys a little bit of a lab to give you a little bit of a breakup.
Hey, you said 172 and typed 127.
Thank you.
And now you type 170. There we go.
So the reality is, when you're ever going to work on networking, you're going to build your configuration in Notepad ahead of time, so you don't make configuration errors like I just did by typing. Oh, what am I doing? Maybe I have to type ADDR. Oh, we're not in the interface. Int D0/0. Now we're in the. Then we'll put that same IP address, IP ADDR. We can do 172.16.0 or .1.1 255.255.255.252. And if I turn this port on and I do a no shut, do we think the port's going to come up? It'll administratively come up, but is it going to come up? If your Ethernet card is not plugged into the wall, do you have any link light on your card? No. So let's watch how it happens. And I'll show you the benefit of a keep alive, and we'll get back to the content. So as soon as I do this, interface gigabit Ethernet changed to down. Down. Why is it down? Why is it down? Now this is kind of weird. Oh, I didn't turn it on. I did a no shut, but why is it down? Even though I manually turned it down, why is it down? So guess what happens? If you plug in your switch, your router, and it's not plugged into anything, you've got 2 choices. We could do one of the following. We could disable the keep alive and keep it up, or we can plug it into a switch. So you know how we talk about health checks for you cloud computing people, and we talk about DNS saying, "Are you there? Are you there? Are you there?" And then the sites respond with, "Yes, I'm here." And DNS forwards the traffic. And we have load balancers that have 5 servers behind a load balancer, and they run a health check. "Are you there? Are you there? Are you there?" And they respond, "I'm here, I'm here, I'm here." And if they don't respond on here, they get removed from the rotation. So we plugged it into Ethernet, and Ethernet's sending a keep alive. Are you there? Are you there? Are you there? But there's nothing to respond. So that's why it says up, down. So we've got two options. Now, to just show you, to argue the point, we could go to interface G0/0. I can disable the health chop by typing no keep. Now watch what's going to happen to this port now. Show IP int brief. It probably will, it may go up. It may not. But I can show you what will make it go up. We're going to plug a cable into it. Verify. Okay. Cisco got a little smarter. They used to let us on our lab exams type no keep alive, which was the most dangerous thing you could do. But it used to work for exams. But they disabled it in this feature. So let's do this. And let's re-enable the keep alive, because that's kind of bad practice to do this. So keep. Okay, so now let's fix this. Why isn't it going up if the cable's not plugged into anything? So let's now add an object. Let's add a node. Let's add a switch. While we're at it, we've got a nice switch here. Let's turn the switch on. Router to switch, straight through cable or crossover cable? Everybody type it in the chat box. Router to switch, straight through cable or crossover cable, while we're waiting for the switch to boost. Switch is booting. As we mentioned, we can't change the size of the display. For the commands, we recommend that you maximize the size of your window. Ruth, router to router, crossover. Switch to switch, crossover. Router to switch, straight through.
Can you repeat those two again, Mike?
Router to router, crossover. Computer to computer, crossover. Switch to switch, crossover. Router to switch, straight. Host to switch, straight. Switch to router, straight. So pretty much you use a straight cable anytime you plug one device into another device, except for you use a crossover if you're going to plug devices into each other without a switch or a network device. Okay, so now we're here. Switch is up. Let's enable this. Okay, now what's going to happen if we actually create a port, if we plug in a wire between these two switches? Let's do it. Let's plug in a physical wire between here and here. Now let's do gigabit 00 on the Cisco side, on the switch side. Now let's see what happens to our router after this. Oh, look at that, automatically. Do you see this thing on the port? Interface gigabit Ethernet changed to up. Line protocol changed to up. So before, this is what we looked like here. Now administratively down means shut down manually. Down, down. Now if we do our show IP in brief, what are we getting now? Oh, look at that. It's up, up, up. Pretty cool, huh? Now guess what? If we go to config T, int, this switch may require us to make a VLAN or it may not. Let's see if we can just put an IP address on the port. Yeah, we can't. This is a layer 2 switch where we've got to create interface VLANs. But some let you do it and some don't. But that's all we wanted to show you. I wanted to show you there's this. Now you got a router, but let's look at this configuration a little more. That's a switch. Let's go back to the router. They do things differently. Run. So we could turn this device into a web server if we wanted. We wouldn't want to do that, but they have the ability to manage it. We can manage the line console. We can dial in via an auxiliary line, which we'll talk about. Yes, EVENG requires a license, and I bought the professional license. It's the most robust simulation package in the world. And that's why we use it, because it works for cloud architects, network architects, incredible software. Oh, Alto firewalls, Juniper firewalls, networks, all the stuff you can run through here. So kind of keep that in the back of your mind. That's the first mini lab we're going to do. We're going to do a lot more. We're going to be connecting things. We're going to be showing you packets flowing through the network. But I want you to at least get a feel for the router, see a little bit about what it is before we get into more content, because I just wanted it to be a little bit fun. So covered a lot of stuff. We're getting ready to talk about the next section. So, let me know if there's any questions.
There was a couple that I don't think you got to. I'm going to look back at them just to make sure.
And, well, I can see one thing. People are looking at simulators. Look, GNS3 is a fine simulator. Cisco's got a packet tracer, which is fine. But none of them hold the candle to the professional version of the EVENG. But not everybody has big needs. For the CCNA, you can use the Boson practice thing, but it's like $200. You could use GN3, GNS3 if you. Any of them are possible. I use the most redundant, the most sophisticated kind, because we run a global training organization for cloud computing. And what you can do when these things come up is what we all do is what's the difference between link up and down versus line protocol? Well, typically speaking, there's the link up and down, which is like, layer 1. Is there a cable plugged into it? And then there's the line protocol, which is typically layer 2. Is the Delcy up and running in frame relay? Is the Ethernet frame is an Ethernet port? That's really what we're talking about. Layer 1 and layer 2. Good question there, Anthony. What do I think about 802.1ax? I'm pretty sure that's wireless, but I don't think in terms of acronyms. Let me just confirm 802.11ax is wireless, since 802.11 is generally wireless. Yeah, it is. That's Wi-Fi 6. Again, Wi-Fi 6 is non-reliable, so it's used for things that are not critical, such as playing video games, or trying to check your social media. That's what Wi-Fi 6 is good for. Anything that matters should never be plugged into wireless, because it's going back to the collision nightmare that I was describing to you. Well, NitroPan, we don't normally manually configure our routers. We typically take a router config, make it in Notepad, and then we cut and paste it in. But we could set up a TFTP server and pull our startup, pull a running config from the TFTP server and save it to memory. Yes, we could. I've done it lots of times, but typically what we do is this following. We keep it in a Notepad file, and that's it, a text file. In fact, NitroPan, here's how we used to back up networks that would have 5,000 switches. We would have some Unix Linux person write an expect TCL / script that would basically log into every router and copy the running config to a TFTP server, and then we'd have text files for all of our routers. And that way, if we had to replace the router, we would just cut and paste the new config in. So yes, we do automate it, exactly. Okay, hold on. No, Chris. And then go to the next one, Chris. Okay, Evelyn, great question. So whenever you configure something, always check the documentation and make sure there's not errors. Now, I've been doing this forever. So here's the thing, Evelyn, because boy, Evelyn, that is a really great question. Let's go back into this router. Let me share this for a second, because what a great question that is. So let me do a show IP interfaces. We can look at the interfaces. So we've got a gigabit Ethernet 00, 01, 02, and 03. So let's try and do something wrong. Config T. Let me try to configure an IP address or an interface gigabit Ethernet 0/4, which doesn't exist. Int GE or G0/4. This doesn't exist. Input error detected. Okay, well, let me try. Let's go to the right one. Let's go 03. Now let's try and put an IP address that's not right. So let's do an IP ADDR 172.16.0.0 255.255.255. Now, this .0 for this subnet is the network address. Let's see if it takes it. Incomplete command. What's it want? Won't give it to me. Why? Because the IP address is invalid. Now, if I were to change it to a valid IP address, now it takes it. So what you're seeing, and I love that question, and the reason I brought it is for the most part, the routers won't let you make a mistake, and they catch you when you're making these errors. So as a rule, you don't have to worry about it because they'll catch you along the way and they'll say, nope, that doesn't work. Nope, that doesn't work either. So that's why we're really talking about it. It's hard to make a routing configuration error. Now you can if you can have 10 ports and put the wrong addresses on each port, and then you've got a nightmare to go troubleshoot, but it almost doesn't let you. So let you know, I always build the configuration ahead of time and paste it in, and that way I don't make spelling errors. But I'm doing this stuff live with you. It's live. You never know what happens on live, and that's part of the fun of live. Your computer can freeze up, and we can have fun. So let's get back to some content, everybody. Okay, so, the first day we've got a lot of academic stuff, which is not my favorite kind of thing, but we have to talk about it. So let's talk a little bit about some of these technology architectures. We're going to talk about leased lines. Ethernet is a WAN technology, and we'll talk a little bit about internet access. And this is really an intro to the content, but we've got to start somewhere. In many parts of the world, you're still going to be running WANs like this. What's it going to look like? You're going to have a campus or an office where you've got a switch and a router, and you've got another office and a switch and a router. And we're going to connect these things over a WAN link. Now, traditional WAN technologies use serial lines or optical lines. T1, E1, T3, E3. ISDN is still being used in parts of the world. Frame relay is still being used in China, for example. I know some people that have worked on it recently. So lots of these old school WAN technologies still exist. Now, for the most part, in the US and the UK and Canada, we're using Ethernet. But for most of the world, we have serial lines. This is old traditional technology, which is slow, but highly reliable. And you're going to see it throughout phone systems throughout the world. Now let's talk about how we buy stuff. So for example, we might have one building in New York and another building in San Francisco, and we've got a router with a private line between them. Guess what? That's how they communicate. This has been going on now for 30, 40 years. Routing in between subnets, 30, 40 years. Not new. So let's talk about, traditionally speaking, like a metro environment. You've got a site that connects to the telco switch, which then plugs into another telco switch, which goes to the next customer site, and all the wiring's underground. So, there's two kinds of connections. There's private connections, which you buy from site 1 to site 2, private connections. And then guess what? There's non-private connections, or public connections that use the internet. So when you connect to the internet, that's connecting to you the internet. But a private line is for me to buy a link directly to Chris's house in the Tampa area, from my house in the Palm Beach area. Direct link. No one can see it. 100% secure. 100% secure. And 100% of the bandwidth is mine, and the delay and the jitter is guaranteed. So how good do we feel about that as far as knowing that our content gets to where it needs to be? It should be pretty darn good. So keep that in the back of your mind. So metro environment. So as we were discussing, and bear with me for a second, whenever we're dealing with communication from one layer to another layer, we've got that data link layer, right? Now remember, with Ethernet, what's that thing that's at the data link layer? A MAC address. What does Ethernet encapsulation look like? Ethernet encapsulation look like. But when we're dealing with WAN lines, unless the WAN line is Ethernet, it's going to use another form of encapsulation, another form of encoding and decoding the messages. So I want you to think of it this way. I saw Alex's name on the column. He said Kalimata, which means good morning. If I had responded, if I got that message from Alex in the morning, I'd say Kalimata, Alex Dikanis, which means good morning, Alex. How are you today? And he would respond Imapoli Kala, because I'd be speaking Greek to him. Why? Because he's Greek, so I would use the Greek language. So when we're dealing with Ethernet, we're using the Ethernet language. Now, if I called Pierre in Canada, I'd call him in French because he's in the French part of Canada. So if I had a WAN link to him, I would use his natural language, which is French. And Leo, who speaks fluent English, Portuguese, and Spanish, if I wanted to communicate to him in the language, I would use the language of his choice. So what are we dealing with in networking? We're dealing with choosing an encapsulation type for the WAN type. So when we're dealing with WANs, we've got two types of framing type, two types of encapsulation. We can use point-to-point protocol, or we can use something called HDLC, which is a standard protocol that's used on Cisco routers. So what is this stuff we're talking about? What's it going to look like? Well, it looks like anything else where everybody has a header that they create. Now, I don't like to use Cisco proprietary anything. I love Cisco. I think it's the best company in the world to work for in the world. They've treated me great, but Cisco HDLC is Cisco proprietary. So I would probably use a traditional protocol like point-to-point protocol because I always use open standards. But this is a fantastic protocol. It's in use all over the world. And Cisco is the majority of the network. So keep that in the back of your mind. And the framing looks like this. You've got a field, an address, a control, a type, and a variable, and a frame check sequence. Just like everything else, it's all the same in every language that we're talking about. That's what we do. So let's think about this. What's it going to look like and how do routers work? So let's go back to the routing table. We're going to walk through this routing time thing. Let me tell you, 30, 40 times before we ever get to the routing on the routers, because I want you to know it. So let's go back to the routing thing. Let's go over here and let's imagine PC1 wants to talk to PC2. PC1 says, I want to talk. PC1, sitting on PC1 is Cindy the cat. She's licking her lips, cleaning her hair. You know, she's happy and she wants to reach her uncle, and her aunt, Sunny the cat over there in Tampa. So what does she do? She gets on my computer, and Cindy loves playing with her computer. And she gets on the computer and she goes to www.sunnythecat.com because they've got some kind of cool messaging application between them. They talk all the time. So Cindy goes to that computer and she says, wait, I want to go to sunnythecat.com. So the first thing she does is say, do I have a route? And she says, no. And then she says, do I have a default route? Which says, if I don't know where to go somewhere. And then she says, I do. Good news. It's router 1. And then she says, who has the MAC address to Cindy? And PC1 does this broadcast. It's called an ARP broadcast. And if you get a sniff route, it'll say, ARP, who has the MAC address for this? And the router will answer, I have the MAC address for Sunny the cat. So the PC sends the data to router 1. Now when it gets to router 1 says, do I have a route on the routing table to get to PC2 or Sunny the cat? And it says, guess what? I know how to read Sunny the cat. Go out my right arm to router 2. That's how you reach Sunny the cat. So next thing router 1 says, who has the MAC address for Sunny the cat? And router 2 responds, use my MAC address. I will proxy ARP. I will respond. So now the data is at router 2. The data is at router 2. And that router 2 says, do I have a route to sunnythecat.com? And it says, yes, I do. It's directly connected to my Ethernet port. So then it says, ARP, who has the MAC address of sunnythecat.com? And PC2 responds, ARP, I have the MAC address. So PC2 now gets the message because it responded. Now PC2 says, oh my God, that's my beautiful friend Cindy. Cindy wants to tell me about the new squirrel and rat that she caught last night, which drove her daddy Mike unhappy because he had to clean up the mess. So PC2, which is Sunny the cat, says, okay, I want to talk to you, Cindy. Now, do I have a route on my routing table to reach Cindy the cat? And guess what? It doesn't. So it says, do I have a default route, which says if I don't know where to go? Yes. ARP, who has the MAC address of cindythecat.com? Router 2 says, I have that MAC address. I'm the proxy ARP. Come to me. So PC2 sends its device to the router. Now, the packet's at the router. The router says, who has the MAC address? Do I have a route for Cindy the cat? And it says, yes. My left arm goes this way, but wait, I have an Ethernet connection. ARP, who has the MAC address of router of Cindy? Router 1 says, I have it. I replied to the ARP. Now, packet's now on router 1. Router 1 says, do I have a route on my routing table to Cindy the cat? And it says, I know where Cindy lives. She's over here, but I don't know her MAC address. ARP, who has the MAC address to Cindy the cat? Cindy says, I do. Purr. Now the two of them are communicating like this. And every part of that communication is going to go back and forth. The routers are going to forward it based upon the next hop, and it's going to come back via the next hop. And that is how routing works. So you got the layer 2 with the ARP, and you got the layer 3 with the networking. So that's what we deal with in networking. It's pretty much just that. It's all that. So let's talk a little bit about encapsulation and decapsulation. Again, I'm going through so much fundamentals over here to make sure you're prepared for what comes next. So here we've got a PC. We've got an Ethernet frame, right? And you can see it. 802.3, that's your Ethernet frame, that's your IP packet. So it goes to the switch. Now it goes to the router. The router pulls that Ethernet frame on. Why? Because it's no longer Ethernet. And it sticks the HDLC. So remember, I talked about Alex. I initially called him, and he's in his restaurant. The person answers the restaurant, picks up the phone, and speaks in English. And I say, I'd like to speak to Alex. Alexandros picks up on the phone, and I say, Kalispera, Dikanis, which is good afternoon. How are you today? So I changed the encapsulation because I'm using a different media. Now we get across the WAN link. Alex and I are talking Greek. Now, Alex hands it off to somebody else. And it's Ethernet, so I speak Ethernet to him. So that's how that works. So encapsulation, de-encapsulation. Now, guess what? Now we're entering the cloud. Do you know what a cloud really means? I'm going to tell you what a cloud really means. What the cloud really means is follows. It's all hidden and you don't know what it is. That's what a cloud means. That's why in Frame Relay we use the cloud, and ATM we use the cloud, the internet you use the cloud, because you can't see which autonomous systems are talking to each other as the average user. You just know you connect to it and it works. So now we've got two kinds of options. We can connect to a WAN service provider. What do you think this can be? They can just create us a wire across their switches and everything's perfect. We get a fiber optic connection to them and they run a connection back to their switches. What do you think a direct connection is like? Or an Azure Express Connect? It's this. It's identically this. You're buying basically a WAN service. That's it. Now, what if we decided to take this WAN service, which is traditional wire, and what if we decided to create a different kind of network? We created an IP network, and then we added something called RSVP signaling, some EoMPLS, or tag and label distribution switch software, and we created an MPLS network. And what if we took a wire and all of the wire's electrical signals and tunneled them over an MPLS network? And we'd create a pseudo wire or a wire out of nothing. Hey, when you go to the cloud and they create you a VPC and it's your logically isolated data center out of nothing, it's the same thing. It's the same logical connection, which is why cloud technologies are 40 plus years old. It's not new. I know AWS will say brand new feature in 2021, east-west routing or routing between subnets. Cisco did the same thing 40 years ago. So all the cloud stuff is 30 to 40 years old. So if you know the network, you'll know the cloud. So that's all Ethernet over MPLS is. It's just a wire. So what does it look like? You're sending a packet over here. This guy or girl or whatever you want to call the user over here is sending a packet over here. and it just gets pushed through a wire. No big deal. There's nothing fancy to it. So now you know what's going on in these networks. It's not that complicated. It's kind of like the hot potato routing, meaning, and I'll show you one more time, hot potato routing. Okay, so let's look in this thing. This system over here wants to reach this system. So what does it do? It looks in its routing table. Do I have a route? And it doesn't. So it goes to router 1. And router 1 then looks in its routing table. Do I have a route to 150.4.0? Yes, I do. Go out this port. Gets to router 2. Do I have a route to this destination? Yes, I do. Go out this port. Ethernet over MPLS. Fine. Packet gets here. Do I have a route to this? Wait. Interface G00, next hop not applicable. That means directly connected on the device. ARP, who has the MAC address to PC2. I have the MAC address to PC2. PC2 responds, sends his data to router 3, which goes to router 2, which goes to router 1. That's it. That simple. So let's talk a little bit about what goes into the IP headers, because we're going to need this. There's a version. What version of TCP IP? There's a length. How many bytes? There's this DS field. This DS field is really important. It's the type of service. So I can set this to critical. I can set this to low priority. Now, if I've got a network that's aware of QoS things and is looking for the degree of service field, I can then say, voice and video go first, and Cindy the cat's download of cat photos from the internet goes last. Now, if I deprioritize Cindy the cat's cat photos, my cat won't be sleeping on my chest and licking me to wake me up at 7 o'clock in the morning because she'll be mad at me. But the point is she can't make sure that our YouTube thing goes down because she's downloading 50 terabytes of data on cat photos. So that's kind of thing. So we can prioritize, and we will get heavily into QoS because QoS is critical for security. Yes, QoS and security, and the two most people don't realize it, but all experienced network architects know that you can use QoS to dramatically increase the security of your situation. So time to live. Okay, so someone asked previously, hey, we send packets out there. What happens to them? So every time a packet hits a router, its time to live gets degraded. So all packets have a time to live. And what is that time to live? How many routers they'll go through before they die. And why is it there? Because if we had a loop and I sent a packet and it circled the internet 1,000,001 times and never died, I could fill up the whole internet. So what happens is the internet has the time to live. Let's say I want to go to Ivadoikio, and there's 20 routers on the way to Ivadoikio's house. So I go to the first router. My TTL is 20. It's now 19. Drops it to the second router. My TTL becomes 18. Drops it to the third router. My TTL becomes 17. Once I cross 20 routers, my packet is dead. So the application will set a time to live based upon how far you think it needs to be. So I know we're hitting all the fundamental concepts right now, but we just have to. We'll get to the fun soon. I promise it's coming. Let's not waste your time. Let's go back to this. I'd like to show you the ARP process again. So when I said router 3, it literally looks like this. ARP, who has the MAC address? So what happens is these devices send broadcasts. Now, what is a broadcast? A broadcast is when you send something and everybody has to look at it. That's what a broadcast is. When you send something and everyone has to see it. That's what a broadcast is. So I want you to think about this truly. If you have 500 devices on a network, what are the chances that all 500 of these devices at the same time are going to send devices? A lot. So, allergies are there. So what happens is every device you have sends a broadcast. So at some point we'll talk about subnet size, and we'll say your subnet should never go above a /24, /23 at the largest because of all this broadcast. This is one of these broadcasts that we're talking about. Every time somebody sends a broadcast, every host on the LAN has to look at that broadcast and process it so it can degrade the performance of your system. So we'll talk much more about that later and why. So the good news is the next section, we get to do some lab stuff. So before we get to the next section, let's open it up for some questions and let's have some fun. Chris, I'll let you aggregate some questions. I saw a lot of stuff coming in. Where does PC1 get its MAC address? PC1 has its MAC address and it's physically burned into the card. So let's see if I can do this. Chris, I'm going to try and share another window in OBS. I don't exactly know if I can do this. Okay, I can't do this. Okay, so totally fine. If you do an IP config on your computer, it's going to be very simple. You're going to see the MAC address that's attached to your computer. Now, when everybody do an IP config, /all if you're on a Windows system, and if you're a Linux system, do if config, pull that up in the chat box. Note, you're going to see your port and you're going to see the MAC address. It's burned in. It's called the MAC address. So my MAC address is Foxtrot Charlie 34 9 7 Alpha 0 Foxtrot Delta -16. Now, when we look, and if any of you guys pull up that if config in Linux or IP config /all, and you're looking at your MAC address, you're going to notice that it's got six things that are each like FC-34-97. Now, if you look at the first half of that, the first three, mine is Foxtrot Charlie 3-4 9 7. That's something that's called the OUI. And that basically identifies who the MAC address manufacturer is of your product. And if you do that, you will see whether your card was made by Intel, whether your card was made by, for example, Broadcom, etc. You'll see it. And then the second half of that MAC address, the last three dashes, that will be the address that's specific to your card. First part called the OUI. Second part is called is a unique address to your card. And remember, this is in hex. So with binary is 0 and 1, hex is 0 to F Foxtrot. With 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, alpha equals 10, Bravo equals 11, Charlie equals 12, Delta equals 13, Echo equals 14, and Foxtrot equals 15. Chris, you can bring in the next one. Well, ARP is a hybrid layer 2/3 protocol that maps a layer 3 IP address to a layer 2 MAC address. So routers communicate to other routers via ARP, and it's because at layer 2 if they're using Ethernet connections, but they still communicate via IP. See, where does PC1 get from its MAC addresses from all the other PCs it wants to talk to? Well, if they're on a subnet, ARP everybody, yoo-hoo, all of you, who has the MAC address? And then somebody responds. That's what it's really like. Yoo-hoo, everybody, I'm out there, who's got this? If you're on a LAN. Now, if you get off of your LAN, Sadie, and this is where it gets tricky, off of your LAN, the router responds to that ARP. So going back to this example that I described to you over here, when we're in this, let's pick up one of these, let's go to one of these routers because we walked through this, but that's a good question. So let's go back over here. PC1 says, who has them, it looks in its routing table and it sees router 1 has the route to PC2. So PC1 says, ARP, everybody out there, who has the MAC address for sunnythecat.com/PC2? Now, do broadcasts get forwarded outside of a subnet? No. That's why we use routers, to make sure the broadcasts don't leave the subnet. Routers promote security, all kinds of cloud stuff. So we'd have a problem. If PC1 says, yoo-hoo, everybody, who has the MAC address for PC2? PC2 can't answer because the broadcast from PC1 will never make it to PC2 because the router stops the broadcast at R1. Routers stop broadcast. That's why they're so awesome. So what happens is when PC1 says, ARP, who has the MAC address? Router 1 says, I do. and router 1 answers on behalf of PC2, and that's why it's called proxy ARP. Router 1 says, I have the MAC address. So when router 1 sends the data to router 2 says, ARP, who has the MAC address? So we're always going to be transferring things as we go through a network. So I hope I answered your question there, because that was an exceptionally good question. Well, does router 2 have an Ethernet header trailer instead of HDLC? If it's got an HDLC link, it'll be HDLC. But once we get to the Ethernet port, we're going to strip off that HDLC, and we're going to be communicating to the routers via Ethernet. So it's going to have to swap. That's what we do. We encapsulate. So layer 2 Ethernet. Now we're going to WAN links. Strip off the Ethernet header, smack on an HDLC header. Go back out the Ethernet port, pull off that HDLC header, slap on an Ethernet header. It's going back to communicating in the right language of the people you're speaking to at the same time. That's really the key. Nice question there. Is the time to live the same thing? No. So what happens is we will be doing trace routes, Alex, and the trace route will literally show us the path that we're going through the network. And then I will show you how, when your traffic gets lost on the network, to use the trace route to solve it. That's coming up in the troubleshooting sections. Definitely. Great question. What methods do you use to configure switches? Generally speaking, when they first come out of the box, you have to connect to the serial port to set them up and put an IP address. And then after that, you can use Telnet or SSH. We used to use Telnet. We don't really use it a lot of the time anymore because it's plain text and hence not secure. So we tend to use SSH. We can now push configs via an API in today's world, if we choose to, once they have an IP address on them. But we also, the routers typically have an auxiliary port as well. And you can basically plug in a modem to them. And we can call it up and, ding, 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 ding. And it's an analog line, which we had set up to 9,600 bits per second, 8 and 1, which we'll talk about that later. And we could basically dial a direct phone number into it, which is highly secure. So these days, we're predominantly using SSH because it's somewhat secure compared to Telnet. It's not the most secure protocol in the world, but it's secure enough. Does multicast addressing use broadcast? No, multicast addressing uses multicasts, which are a very specific kind of thing. And broadcasts aren't forwarded out of the thing, but with multicast we create something called reverse path trees to the source. I actually consulted as an IP multicast engineer for about 5 years, so I've spent lots of time in IP multicast, but reality is multicast can get really complicated, and I wouldn't have enough time in the next 2 weeks at 8 hours a day to really cover multicast if we spend 8 hours a day for 2 weeks straight. So because of that, I'm going to just say that multicast is a special kind of broadcast. For example, if you have TV in your house and you have IPTV from your cable company, it's multicast. And what multicast is, you subscribe to what you want and you see whatever you want. But if somebody else doesn't subscribe to it. So there's this new TV show I watched the other night. It was called, it was about money laundering. It was called Ozarks. It was on Netflix. It was pretty good. So here's the key. If that was being streamed and 1,000 people tuned in at the same time, because it was live streamed, guess what? That would be multicast. And that way, the server would send it once and hundreds of thousands of people could watch it as live TV at the same time. That's versus me watching it at my own time, which is unicast. So multicast is like that, but that's kind of where it works. Chris, I think we can do one more. Alex, I'm glad we got your question. Does ARP work with CDP? So Franklin D, I strongly recommend, if you want a career in architecture, never, ever, ever to use acronyms, because CDP can be a lot of things. It could be a coupon code. It could be Cisco Discovery Protocol. I could give you at least 50 more things than that is. So my recommendation with regards to technical precision is never to use acronyms. If you want to be an architect and use an acronym, that basically will keep you from being hired, because the hiring manager won't hire you. For engineering, it's acceptable. So keep that in the back of your mind. ARP is mapping a MAC address to an IP address, and CDP, or Cisco Discovery Protocol, assuming that's the CDP you're talking about and not like something else. CDP helps routers identify other routers, so they're completely unrelated. When a packet is sent from router 1 to router 2, what's the packet's destination? It is directly the IP address of the next router and the MAC address of the next router. The ARP is to figure out who has the MAC address, and then you send it. Chris, where were we on questions? Do we have to get back to content?
No, that's it. We can get back to the content.
Okay, perfect. So let's get back to the content. Let's have some fun and talk some networking. Let's make sure we get you to the right section. Okay, so in this section, guess what? It's talking about using the command line interface. So we're going to do some of that. So, this goes back to the last question, which was super intelligent with regards how do you manage these? And I love the question. So what happens is in the old days, our computers had a serial port. And we would plug the serial port. It had like a bunch of wires and we'd plug it in. And what would happen is we would take the serial port. The serial port would give us something called a rolled cable. We would plug the cable from the console port into the serial port of our PC. Now, in recent years, PCs stopped making serial ports. So what did we do? We bought a USB serial port that would plug in to emulate the serial ports. And that's how we would connect to these things. And that would give us hands-on terminal access. And realistically speaking, that's what I'm referring to over here. This is what I'm referring to. There's some devices that have a USB thing that you can, that's the converter that you would use to the serial port that I was referring to. And that's pretty much it. So let's talk about setting up a terminal. So on your computer, you're going to have to set up the terminal settings. And here's what they need to be. I'm going to sound the alert. Test question, test question, test question, test question. Know how to do the job question, know how to do the job question. Critical, critical, critical. Learn this. These are your terminal settings. The bit rate or the baud rate is 9600. The data bits are 8. The parity is none, and the stop bits are 1. So memorize this. 9600, 8 and 1. 9600, 8 and 1. You will be tested on this, and you will need to know this for the job. You will need to know this for the job. So let's go back to the concept. 9600, 8 and 1. So when we get to these devices, we've got two sets of users. Basic, which is user mode, and enable mode, which I called privileged executive mode, because that's technically what it's called. But the rest of us call it enable modes versus user modes. So what's that look like? Well, it's going to look like this. Let's go back to this. Let's go back to this router. We get into the router. What's it look like? User mode. So Prince, it's going to be 96008N1. 9600, 8. N is in November, and the physical number 1, and you'll be good to go. So we now get to the router. We're in user mode. User mode. How do we know we're in user mode? It's got a greater than symbol. User mode. Type enable. It changes to a prompt, a hashtag. Guess what? That's called enable mode. That's all you needed to know. Now let me show you the difference. While we're at it, let's go back to, let's exit out of this. Let's go to the console port. We'll be in user mode. Let's reload the router.
Are you sharing your screen, Mike? Or do you mean to be?
I was trying to, but reload. Guess what? It didn't accept it. The command wasn't recognized. So now what's it trying to do? It's trying to resolve it. Hey, to telnet into this device because we didn't tell it, and it's going to time out in a couple of seconds. Why can't we reload this router? We don't have the privilege. Why don't we have the privilege? We're not in enabled mode. Now, let me just take the config. Now let me type enable. Let me save the current configuration. Now this is like root access. Now let me type reload. Confirm. Yes. See the difference? Privilege comes in. There you go. We rebooted the router, but I couldn't reboot it in user mode. I could do it in enable mode or privileged executive mode. So does that sound like Unix permissions for everybody? It's the same. So when we're going through the software, as soon as this comes up, let's play with it a little bit. Let's give you an example of how to navigate this when you don't know. Now, when you don't know, what do? www.cisco.com. They give you the documentation. Heck, the knowledge required for these things is so great that on the CCNA exam, they used to give you the CD, and it still had a 97% failure rate at the time. They would give you the instruction manuals for configuration because they knew that anybody could configure anything. It was the knowledge that was hard to know on how to do it. So let's go back to this. Let's go back to this environment. Our device is going to be booted up. Okay, now, want to know what to do? There's a question mark. Wait. Gives you help. And we can look through more and more and more, one at a time. These are all the things we can do from when we're here. A lot of things. If we don't know, let's get some help. Let's type ping. Hey, we can, what kind of ping do we want to run? Do we want to run the CLNS echo, like from, which we now use with the intermediate system protocol? Are we using DECnet from 30 years ago? Is it an Ethernet frame? Is it MPLS? What kind of ping do we want to send? And we can help that. Let's say we want to configure an interface or just configure the router. What do we have here? Oh, wait, we've got new things. AAA. Wait, authentication, authorization, accounting. Where have I ever heard that term before? Cloud, they call it identity and access management. Same thing. Access list. I can create an access list. In AWS, they call it an ACL. Same concept. Azure calls it, I think in Azure Network Access Control. I'm drawing a blank right now, but I normally would, it's in the back of my mind. So, that's the thing, is we can do it. So let's just, somebody else asked the question. We're now into G0/1 at support. Now you got to spell it wrong. If you spell it wrong, it won't let you. So now what do we have in options? Okay, I can configure things on the port. I can configure an IP. If I do IP, what's next? I can do an address group to tie an access list. I can pop an address. Okay, let's pop in an address. So let's do over this. Let's type in ADDR. Now what options do I have? I can tell it to pull via DHCP, which I would never do. I can come up with a pool that I could use if I was going to turn this into a DHCP server. Or guess what? I could just give it an address. 192.168.1.1. Guess what? Oh, wait, I need a subnet mask. 255.255.255.252. Wait, is there anything else I should do? I can add a secondary address. You know what a secondary address is? I can have a primary address and a temporary address if I'm changing my IP addresses, or I can just be done with it. No, I'm going to do a shut, but no AAA, meaning no identity and access management, no ARP, no backup, or I can just shut. I can turn on the interface, no shut. So the point is you're guided no matter what you do by this. So keep this in there. Azure has network security groups, but they also have network ACLs, I believe, in addition as well. So that's really what we're talking about. So keep that in the back of your mind. With every command, you can get help. So let's talk about some other things. Any of you guys or girls ever use Linux and Unix in your life? Okay, so let's do this. Config T. Let's go to interface G0/1. Okay, wait, does anybody notice that I didn't type it right? So in Unix, if I type Control A, it begins me to the beginning of the line. If I type Control E, it takes me to the end of the line. If I type Control B, typically moves me back a space. Where do you think these things come from that the command line follows in Cisco? Unix. Unix. So all of the same commands that work in Linux and Unix, especially in Bash, are pretty much the same way the Cisco command line works. Why? Where were the first networking devices? They ran on BSD Unix. Well, this is not on BSD Unix. The Juniper routers were for a while, but here's the thing. Everything comes from Unix, so that's where the stuff is coming from. So of course you can backspace on these devices, and of course you can use, the arrow keys. Also, up arrow repeats the previous commands. Down arrow will do the same thing. So keep that in the back of your mind. It's just, working your way through this, just like Linux, Unix. So if we're dealing with the switches, when we're dealing with routers, they build routing tables. And how do we see what's in the routing table on these devices? We look at the routes. So let me just show IP route. What do we see on this device? We can see the one subnet that's up says directly connected. Keep that in the back of your mind as we walk through some of these things. That's really what we're talking about. Now, if it was a switch, guess what? We'd be looking at MAC addresses. So let's kind of play with it a little more. Let's prepare this thing for Telnet or SSH, etc. So we'll go to the config terminal. Note, I typed a spelling error. It doesn't let you. So in general, when people tell you they made a networking misconfiguration and it was a typo, realize it probably wasn't a typo, because you can't make a typo. Right? It's very hard to. Realize typically you can configure the wrong routing protocol. You configure the wrong routing thing. You can do all these things that are wrong, but usually it's because you didn't know what to configure, not how to configure it. Because here's the thing, we can get this configuration materials in seconds. It's easy. Just go to the Cisco page. It's knowing how to do it. So let's make this so this thing has virtual terminals that you can manage. So they're called line V2I 0 flare. Let's say here we wanted to type password Cisco, transport input all, which is going to enable us to come in via SSH, Telnet, etc. And no login. Now we'll show you what. Now we can reach this device from another one. So let's do this. Let's connect the second router. Let's get rid of this switch over here.
Hey, Mike, you're not sharing your screen.
Not sharing my screen. Yep. Thanks, Chris. Was I not sharing my screen for any of that?
It only started in like the last 30 seconds or so.
Okay, perfect. Okay, so good. So now let's delete the switch. I didn't mean to do that. So how do I remove this thing? Okay, so stop. Shut down. Let me see if I can just delete. Okay, can I? All right, we're not going to worry about that. So we're going to basically add another router. Let's say Cisco iOS router. We're going to bring another router here. Now we've got two routers, everybody. Let's configure this next router. But while we're at it, let's make sure it works with router 1. So show IP int brief. And we need to make sure we know the IP addresses that are on this router. Okay, so let's set up router 2. And on router 2, we're going to make it connect Ethernet 0/0. So let's draw a connection between G0/0 over here and G00/G00. So We're going to get to subnetting tomorrow, but just in case you guys already know subnetting, let's go to this brand new router, router 2. Let's set it up to work. Let's make it work. It'll be fun. So router's coming up, it's booting. That's why it's slow. Let the router come up, we'll configure it. And then we did some configuration today too. I tend not to be Mr. Loud, but some of this stuff is just pretty important to know. This thing up and running? Yeah, it is. It's just still booting. Come on, wake up. Okay, so router's up. So let's boot it up. Let's have some fun. Let's change the host name. So if this device is called R1, what should this device be? Let's call it R2. If you can hear me, I see there's some people that are trying to write some content on PIM and multicast. Could you share the document that I wrote 20 years ago while working at Riverstone Networks, which is used by every major company for IP multicast troubleshooting in the world? I know you found it somehow, Ivadoikia. I don't know how you found it. So if you can just share a link to that document, I think it'll be helpful to people that are interested on multicast. Because I want to make sure that we're accurate and correct. Because I can't really see what's going on there. So this device says router. So let's give it a new name. Let's call it router 2. Host name, R2. Oh, it's already changed. Now let's put a loopback address on it for management. So let's create a loopback interface, LO0. And of course, I typed in extra O. Now the interface by itself is going to be down. Let's put an IP address. Let's call it 2.2.2.2. Let's give it a 255.255.255.255. That's called a host root. Now, guess what? Did I put IP address? No. How do I get to the beginning of the line? Control A. Huh. Now I can just type IP ADDR because I forgot. Enter. Oh, wait. I made a spelling error. I added an extra dot. It didn't like it. And it even showed me with that little caret thing there where my mistake was. But still didn't like it. Why didn't it like it? Oh, wait, I forgot a dot and a 5. Now it looks right. Is it going to take it now? Yes, it did. So no shut. So there you go. Ivadoikia Pop, my intro to multicast document. And there we go. Now, this gigabit Ethernet 0/0 on the one side is different than this one. That's 172.16.1.1. So this one should be 1.2. Again, we're going to cover subnetting. So int G0/0 IP ADDR 172.172.16.1.2 255.255. I'm assuming that's the subnet mask I used. 255.252. Let's confirm on our previous router that I'm on that subnet, because if we have an address on a different subnet, guess what? It won't work. So let's just confirm that the link between them is on that. It's a /30. So we're here. We've got the right IP address. And guess what? We're going to turn on the interface. Now, do we think that interface is going to come up because it's now plugged into the router? Whoa, look at that. Line protocol gigabit interface up. So show IP int brief on the second device. Guess what we see? We've got a loopback address. And the loopback address is on there. And we also have the far end. So let's have you guys work through it. I'm going to give you your first networking troubleshooting challenge of the day. If this 172.16 is on one side of the link, 172.16.1.1, and on the other side of the link, we have 172.16.1.2. You guys think I can ping across the link? Do you think I'm going to have IP connectivity from one router to another router after I put them on the same subnet? and we ran a wire, are they going to be able to talk to each other, everybody? If you think so, put the answer yes in the chat box if I can ping across that link. If you think the answer is no, type no and why. Here's a hint. Same subnet. There's a wire between them. Can they talk to each other? Yes, they can talk to each other. As we've mentioned, we use EVENG Professional. That is the simulator we're using. They can talk to each other. Fantastic. Yes. Now, can router 2? Yes, they can talk to each other because they're on the same subnet. They're both on that same /30. So let's ping across and check it out. Ping 172.16.1.1. Can it reach it? Okay. ARP, who has the MAC address? And we can't. So what did we misconfigure? Did we put them on show run? What did I misconfigure on this? Did we put it on a different subnet by accident? Nope, 172.16.1.2. And this one over here is 172.16.1.1. G00, G00. So this should be working unless we made a configuration error on one side. That's timing out too. So why isn't this link up? Gotta love doing live technology demos. I may have configured the wrong link. Let's give it a minute to see what's not going on between these two devices, because we should be able to ping across the link. We are not passing traffic over this link of any kind, layer 2 or layer 3. So we're on the same link on the same subnet. Something's not pleasant. Okay, we'll let that do its thing. Most likely, we just need to reboot one of those things for it to actually work. But that's the thing. What you can see is you can configure it. You can put your links on it, and typically they'll work. Now, there's no reason why that shouldn't work unless there's a challenge with the logical wire we just created, because that will work on anything. Now, what should not happen is we should not be able to reach the loopback addresses without turning on routing. So we probably should figure out what and why that occurred, and we'll get back to that. I'll go back and debug it a little bit, but I want to keep the flow. So let's go through the next phases of things here. Let's walk through the modes of configuration while we're at it, as soon as these devices come back up. So let's walk through the modes. And of course, our devices are still coming up. One of these guys will be up soon, and I'll be able to show you the modes. While we're at it, let's turn this device on. Oh, well, there's a very good reason we're not able to ping across the link. Can anybody tell me why we can't ping across this link? It's shut down. Let's turn it on. On routers, devices come from the factory. Shut down. So now do you guys think we can ping across this link? Ping ourselves first to make sure our address is good. Woohoo! Let's ping across the link. Why are we going to lose this first packet? Oh, let me just check and make sure that this is turned on this side too. Okay, that one shut down too. Okay, so now.
And Mike, can you pull that? I guess you would call it the bottom window up a little bit. Yeah, there we go.
Now let's ping across the link. Now the first packet's going to be lost and the second 4 are lost. Huh. First packet lost and the second packet's lost. Now if I repeat the ping, does anybody think I'm going to lose the next packet? I won't. How fast that was. Why was it that first packet was lost? Okay, so I'm on the device. ARP, who has the MAC address of 172.16.1.2? That ARP broadcast took about a second or two to get a response. That's why we lost that first ping. Note if you look very carefully, you get a period and then you get the 4 bangs. And then every subsequent time we get 4 bangs. So that first one was lost due to ARP. So I see a Jim Weaver there. I don't know if you're the same Jim Weaver I know from Cisco. If you are, it's great to see you. If you're in a different Jim Weaver, I'm thrilled to have you here as well. So we go back to these devices. Everything makes sense. So now let's think about this. Will I be able to, from router 1, be able to ping router 2? This loopback address, the 2.2.2.2. Let's try it. Well, before we try it, let's do a show IP route. Do I have a route to 2.2.2? No. So is it reachable? No. But let's try it. Let's pretend we didn't know. Ping 2.2.2.2. Timeout. 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 Now, why can't it reach 2.2.2.2? Okay, Jim, you're the other for my class. Wonderful, fantastic, thrilled to see you. Why can't it reach 2.2.2? Because it doesn't have a route. So if you're a cloud architect and you can't reach something and you look in the routing table and you don't have a route, guess what? You're not going to be able to reach it. Now let's think about this. If I don't want to be able to reach 2.2.2.2 on this router here, if I don't give anybody the route to it, can they hack me? No. So no route, no path. No path, you can't be hacked. So when we start talking about security, and we're going to get into cloud security and network security, if you don't have a route, you can't hack it. So I want to go visit Ivadoika over there in Hungary, which is across the ocean. If I have an airplane, I can visit her. If I have a boat, I can visit her. But if I don't have an airplane or a boat, guess what? I can't visit her. Why? I don't have a route. So keep that in the back of your mind. So now I could put a route on this. I could put a static route that says to reach 2.2.2.2, go over that link. And guess what? If I made a static route over here, it would be perfect. I could put a route here and a route back. Why? There's only one link. There's no recalculation. But what if I wanted to make this smart? Let's just turn on some routing. So now you're going to see config T, router, OSPF. We're going to turn on a routing protocol called OSPF. I'll go into it in more depth. Network. Let's just say 1.1.1.1, 0.0.0.0 area 0. We'll be talking about how this protocol works in depth. I'll spend a full day on it. Then we'll take this network 172.168.1.1.0, and then we'll basically take this 0.0.0.3. I'll teach you what this means later. And on the other router, I'll do the same thing. I'll go to this router. I'll go to config T. I will do router OSPF1. We'll do a network for the statement for the loopback. Then we'll do something for the WAN link, 172.16.1.0, 0.0.0.3, area 0. Let's see what happens now. Just enabled routing on 2 different devices. So let's going to see what's going on. Make sure we put the configuration in correctly. We put in some OSPF. We popped, okay, so neighbors didn't come up. Why? Is the network 126 or 172? It's 172, not 127. So if you type something wrong, what's going to happen? Show IP route. We're not going to have any. Now, if I change this and I do to router config T router OSPF1. Now, if I add a network statement, let's remove the one. So if we had a network statement that says 172.16, and I have to type it right, 72.1.6.1.0.0.0.3 area 0, I'm going to tell this interface to participate in OSPF. Oh, wait, did you see this message? Look at this message. OSPF adjacency changed. Neighbor is full. Okay, now, if I do a show IP route on this device, look what we see. And if I do a show IP route on this device, what do you see? Now, before, on this device, when you wanted to reach 2.2.2.2, you couldn't. Can you now? Yeah, you can. Why? It's in the routing table. See? You've learned 2.2.2.2. Now, this is router 2. So can we reach 1.1.1.1 on the other end? Well, it's in the routing table. If it's in the routing table, we probably should. Okay, we can. So now you're seeing that we're learning it. So what routing protocols do is they tell other people what the routes are. So let's go back to router 2, and for fun, I'm going to add some more interfaces. Int loopback1 IP address ADDR 3.3.3.3 255.255.255.255. Okay, no shut. While I'm at it, let me add another one. Interface loopback 2. Of course, it has to be. Let's see, I mean. Hold on. All right, now we're on router 2. So we just added 2 interfaces to this device, show IP int brief. We added, remember before we could reach this and we could reach this, but we added 3.3.3 and 4.4.4.4. From router 1, does it know about them? Can router 1 know about these devices? Does it know how to reach these 2 devices? Well, let's look at its routing table. Show IP route. Wait, I don't know about 3.3.3.3 and I don't know about 4.4.4. Can I hack it? No. Can I reach it? Let's check. Now, if it's in the not in the routing table, here's the secret. You won't be able to reach it. It won't happen. No. Let's try 4.4.4. It's not in the routing table either. Is it reachable? Well, no, not at all. And you're going to see, we're going to talk about these things. So now I could put a static route on router 1 that says, hey, to go here, take this link. But the problem is if I have backup paths, so this is like me visiting Chris. I know to visit Chris, I've got to go take I-95. I've got to go make a left and go west to Tampa. And then once I get to Tampa, there's a certain things that I need to meander. And that's fine. I'm good with that, right? But let's say I printed them out like a static route and I've got a piece of paper in my car. And now the police have a roadblock up. Can I get to Chris's house anymore? No. So if I had a GPS in my car that knew every street, but it'd say, recalculating, make a left, make a right, go 46 miles, and then you're going to see Sonny the cat. So, my GPS has the intelligence, so the routing protocols can too. So let me show you how fast this is going to work. So we're going to do config T on here. We're going to do router OSPF 1. We're going to add the network 3.3.3.3 into OSPF 0.0.0.0, and we're going to put it in area 0. Is that going to be reachable here? Let's see. Let's look at the routing table. Nope, not yet. Ah, look at that. 3.3.3.3 popped in the routing table. Can we reach it? Yeah. Can we reach 4.4.4.4? Show IP route. We don't have a 4.4, so let's try it. 4.4.4.4. No route. We can't reach it. Okay. Should we tell it about the route so we can reach it? Watch this. We'll go over here. We'll tell OSPF, which is a routing protocol. And we're going to talk a lot more about routing protocols, but I wanted to give you a feel for networking. 0.0.0.0. Wow, we're going to stick it in area 0. Now we're going to tell OSPF that we know. Now let's look over here. Let's look in the routing table. Do we have it? Wow, 4.4.4. And how is it learned? Oh, OSPF. This 110 thing is going to tell you about administrative distance, which we'll talk about later. And this 2 is the metric of the route. So now can we ping it? Oh, we can. We have a network and it's fully functional. So now you get it. So let's talk about the configuration modes of these devices. So there's configuration mode. This is global configuration mode. There is interface configuration mode. How do we get to that? We pick another one. We go to interface loopback 0, where now it says config IF, interface configuration mode. Now we type router OSPF 1. Now we're in router configuration mode. So keep that in the back of your mind. These will all be test questions, and they're all things that you need to know. So when we're dealing with routers and switches, we're going to have a bunch of different kinds of memory. We're going to have RAM, DRAM. It's the same DRAM that's in your computer. Same thing. And it's memory that stores the routing table, it runs the routing software, et cetera, et cetera. Now, in your computer, you have a hard drive, which stores your operating system. On your mobile phone, you have flash storage. What do you think Cisco routers use for storage? Flash storage, just like your mobile phone. Why? It's fast, it's efficient, there's nothing to break like no hard drive. So we have DRAM, we have flash. Now we have something called a ROM. And like in your computer, you've got the BIOS that you boot into, the basic input-output system before you get into the hardware. Well, and that's like a bootstrap. Well, pretty much the ROM that exists on Cisco router is just like that. It's just like the BIOS in your computer. And somebody asked, where can we store the configurations? I think it was NitroPan. We store the configurations in something called non-volatile RAM. It's basically a form of flash, et cetera, and it stores the text files. What do these text files look like? They look exactly like this. If you do a show running config on a router, your text configuration is going to look like that, and that's it. It's just standard text, and that's what you're going to see there. How do you get the stuff that we're working on to the startup configuration? Well, we can do The old school CCIE is WR because it used to be write memory, but it technically is copy, running, dash config to startup dash config. That's how you save it, destination file name, etc. Same as my write memory, but it's the appropriate terminology, the one that Cisco actually recommends. Like, I've been an architect for too long. I've been dealing with this stuff for too many decades. I may potentially use a different approach for those reasons. So basically, startup config runs in NVRAM. Your running config is running in RAM, no big deal. So the next thing, we showed you how to show the running configuration. And there we go. That brings us to chapter 5, which is, guess what? Is going to bring us into LAN switching and really, really, really cool stuff. So let's do this. I don't want to overwhelm you. I want you all to become great network engineers, great network administrators, great solution architects, great cloud architects, or whatever that career is that you want. So let's take some questions. And then after some questions, if you guys want, I can go a little more, or we can call it for the day. It's up to you guys. What's the loopback between a loopback and a regular Ethernet address? What a good question there, Sarah Ahmed. So Sarah, a regular address is a physical port. A physical port. A loopback address is a logical address that you put on the routers. Why do you put the loopback addresses on the routers? For the following reasons. You're looking for some logical address that doesn't go down. So when we connect to the cloud providers, they say, hey, we've got a high availability device, because it's not a real device. It's just logical device that's created in software that can exist anywhere. So that's the difference between a loopback. A loopback is a management interface that we put on there. It is not a real interface. And we can assign any kind of interface IP addressing we want to it, including a /322. It's just there for management, router identification. Great question there, Sarah Ahmed. Chris, if you want to bring in the next one. Nitropan, what does area mean? Oh, Nitropan, we're going to have fun with this topic. So here's the key. When we deal with the Dijkstra routing protocols, whether it be intermediate systems to intermediate systems or OSPF, open shortest fast first, what happens is we divide our network into sections, and they're called areas. And the reason we divide it is inside of an area, you need to know everything about everything inside of that area. But in between areas, you don't need to know as much. So it gives us a means to decouple or segment our networks to make them scale. So I was looking for that question. Nitropan, that's an extraordinarily good question. And we will spend 1 to 2 days on this matter of the areas, specifically for our cloud architects and our network architects that really want to do system design. Knowledge of OSPF is critical. So great question. It's part of the way we segment our Dijkstra-based algorithms that run that shortest path first calculation. Fantastic question there, Nitropan. The loopback is an address that will never go down. It's a management interface. So I want you to think about this. Let's go back to this example. Not this example, this example. So now that we're back into this example, watch what happens if I disable this link, like a cable gets cut. Hold on. Let me see if I can disable the link. Suspend the link. Okay, so the link just went down. Now that the link went down, oh, there you can see it. Here you can see what happened. Line went down, and OSPF noticed it. It took OSPF a little longer to detect the calculation. The link went down over here, and it took 10 milliseconds for OSPF to notice that the link was down. So that's what we're talking about. So, keep that in the back of your mind. So now, if I do a show IP route on this, do we have any of the routes from the other side? No, we shouldn't. Hold on. Why are we not going to have any routes? The link is dead. Watch. Now, if we go to this device, is the loopback address still up? Show IP int brief. Now notice our Ethernet port went down because the link went down. But notice that all our loopbacks stayed up. So you asked a really great question. So let's make the link come back up. Let's resume the link. Watch what's going to happen. OSPF is going to detect it. We're going to see a neighbor adjacency change. Watch it happen. There we go. Now, line protocol went up. Now, we should be notified of an OSPF neighbor change fairly quickly. What has to happen is the routers have to say, hello, 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 I'm here, you here, we're all here. So I didn't see an OSPF net, so show IP OSPF neighbor. I haven't seen it come up yet. Well, apparently the neighbor's up. We can see, and we'll get into this, but it's not completely up. Let's give it a minute. Let's see where the OSPF status is. 2A GR others. So let's look at the show IP route now. We're not seeing, OSPF just came up. Now, if we look at the show IP route, we're going to start seeing that we're going to get routes from the other side very quickly. We haven't gotten them yet. We're still calculating, still calculating, still calculating. Oh, now they came in. We can see the OSPF. So let me show you why we use a loopback, because right now it doesn't make any sense. Let's draw another link between these connections. Okay, so now let's do this. Let's pick another link between these connections. So on router 1, now we're going to configure one on gigabit Ethernet 0/1. So config T, interface G0/1, because we didn't use that one before. So G0/1, so let's do an IP address, IP, ADDR. Let's say 192, did we use 192.168? No, we haven't. 192.168.1.1, 255.255.255.252. No shut. Now on this side, let's configure this router. Config T, interface G0/1. Of course, you have to spell it right. IP address. What did we use on the other side? .1. So 192.168.1.2.
Can you pull that window up just a little bit?
You got it. So now we added this. Let's Control E. Let's add a subnet mask 255.255.255.252. No shut. Now, when we shut this, when they're both ports come up, this port should go up. So can we ping across the link? Let's make sure. Ping 192.168.1.1. Okay. Why did we lose the first one, everybody? ARP! Who has the MAC address? And that's why we lost it. So let's go to the other side. Can we ping across the link now? Ping 192.168.1.2. Can we reach it? Yeah, we should be able to. Oh, well, the reason we couldn't is because I typed 192 as 129. So that will explain that. So let me retype this. Woohoo, now the link's working. Now, let's look at the routing table again, because this is really important. If we do a show IP route, look how it's reaching everything. Gigabit 0/0, gigabit 0/0, gigabit 0/0. It doesn't know to use this link for anything. So how do we make this work? We go back. So we go to OSPF, router, OSPF1, and watch what's going to change. We'll do a network. We'll add this 192.168.1.0, 0.0.0.0.3, area 0. Now you'll see why we're creating a loop. Now you're going to see why we're creating the loopback. Config T, router OSPF1, network. Network 192.168.1.0, 0.0.0.3, area 0. I couldn't fly, but we'll see. What we expect to see if we did this correct, and I didn't make any spelling errors, we're going to see an OSPF adjacency come up, and we'll see in about 30 or so connection seconds. But let's make sure that I didn't, do a typo. Ah, look at that. We're beginning to form our neighbor relationship, and we'll talk about what these states mean. We're going to do it again. Oh, it's still filling up. It's still filling up. Let's see what's going on this side. Oh, wow. Look, we just formed a full neighbor, and we exchanged our stuff. So now we're going to look at the routing tables in both of these routers, and they're going to be very different now. I'll show you why. So now when you get to this router, do a show IP route. It'd help if I could type. Now, wait a second. Does the routing table look a little different? Go to this one. Show IP route. Now look at this routing table. It looks a lot different than before. Now for 2.2.2, which path do you have? Gigabit Ethernet 0/1 and 0/0. We have two equal cost paths now. So what happens if I want to form a neighbor relationship and I do ping 192.168? We do ping, yes, 192.168.1.2. This is what's called an extended ping. There's a reason we're going to do this. Repeat. Let's change this to 100. Let's change this to 100. Datagram size here. Oh, well, that went a little faster. So, but what I wanted to show you is this. Right now, we're pinging across that link. But let's say right now we ping 8.8.8.8. That's not an address we have. Never mind. We have to pick an address that we actually have on the device. That would be my fault. So show IP route. Okay, you can see how we've got everything. So if we want to do a ping to 4.4.4.4, everything works great, right? Now, let's say we want to ping across the other end of that link, 192.168.1.2. That works, right? Let's say we've got a cable cut. So we would never use a single network provider. So one link is on AT&T and one link is on Verizon. The same way it would be insane to stick all of our things in AWS or just Azure or Google. We always want to use multi-cloud and multi-providers. We've been doing this for 30 years for this reason. So now this is your AWS or your AT&T link. That's dead now. So watch what happens. Can we ping the far end of that link? No, because the link is dead. We can't ping it. The link is dead. But now, do you think we can ping the loopback address? Yeah. This went dead. Why did this go dead? Because it's a physical device. The cable was unplugged. But this logical device, guess what? The reason it works is we rerouted. So let's bring this link up. Now, how long is it going to take for OSPF to discover each other and fully load? Well, line protocol's up. Let's watch it. In about a minute, we're going to get a notification from OSPF that the network is self-healed. Let's wait for it. Let's wait for it. Let's wait for it. Still coming up. We should form, so now let's look at the let's go back to here. Let's go back to this router. Let's do a show IP OSPF neighbors. Show IP OSPF neighbor. And what do we see? It's XStart, which is on the way to form, loading full. Now we've got full neighbors. Woohoo! So now guess what? We should be able to ping across the link. We should be able to ping the 192.168.1.2. We can also ping 4.4.4 because we've got two paths. Now let's take the top link. So we lost the AT&T link is up, but the Verizon link went down. This is why you should never use a single cloud. It's insane because this stuff's going to happen. Now, are we going to be able to ping on the other end of this link? We're going to be able to ping can we ping the 4.4.4? Watch what happens. Now the top link was the primary link. Now it's healed. Now notice we lost ping 1, ping 2, ping 3, ping 4 in the process, but now we got them all. Now let's bring the link back. Resume link. Okay, right now, can we reach it? Let's see. Can we reach it now? Yeah, because we're using the backup link. Can we reach it now? Can we reach it now? Yeah, we're reaching the backup link. Can we reach it now? We're reaching the backup link. Can we reach it now? We can still reach it. We can still reach it. Now we may lose connectivity during the healing for a second. Maybe not. Let's see. Still getting all these pings here. Fast. Guess what? We haven't lost anything. Why? Because we have two links on two different service providers. That's why never, ever single cloud, or never, ever buy all your links for Verizon, or buy all your links from BT, or AT&T, or NTT. That's why we always recommend two links on two different service providers. So now you know that's why we orchestrate networks the way we do. Whether it be networking or clouds, we should never allow a single plane of failure. And 1 is none, 2 is 1, and 3 is greater than 2. So we talked about a lot of stuff today. I'm sure there's some questions. Let me answer the questions and let's call it a day so you guys can get some refreshed and come back tomorrow and become strong. I want you guys all getting the best cloud architect jobs, solution architect jobs, network engineer jobs. And that's why we're doing this free CCNA training, the Cisco Certified Network Associate training, CCNA 200-301. Here's the thing. This is the foundation of the cloud. Know the network and you know the cloud. And I want you all getting, guess what? Hashtag cloud hired. So Chris, bring in the last questions and then let's let everybody have a good night's rest so they can have a good night's sleep. And we'll get back to it, hardcore networking tomorrow. It'll be fun. Can I please make somewhere summary? Sure. Networking is about the connectivity between two or more locations. Network devices include routers, which take your information and direct your traffic through the internet. They include switches, which we'll talk a lot about how the switches and bridges work, which we'll have lots of fun with. We talked about today WAN technologies such as serial ports, HDLC, frame-relay, ATM kind of things. We talked very briefly about LAN technology. Actually, we spent a lot of time talking about Ethernet, Ethernet frames, Ethernet headers, etc. We talked about using some network diagnostic tools such as ping. We talked about the router and switch configuration modes. We talked about user mode, enable mode, or privileged executive mode. We talked about interface configuration mode and router configuration mode with regards to the OSPF that we did. We introduced basic routing. We introduced basic routing tables. We introduced routing logic, the hot potato logic. We talked about how we map layer 2 addresses to layer 3 addresses with this really cool protocol called Address Resolution Protocol called ARP. We covered the OSI model. We covered the internet model. We covered how to access Cisco routers, 9600, 8, and 1. Why do I say that? It will be at least one test question, and I want you all to get it right. So these are the concepts we kind of talked about. So if there's any questions you'd like, Chris, let me bring the questions. We may not be able to answer all, but I'd like to help with some. I want everybody to have an incredible experience. Gus, the engineer. Mike, in terms of layer 3, how many layer switches are used for routing? Gus the engineer back in 1998. We used to do this crazy thing called router on a stick, which I'll talk you through, where we basically had switches that were layer 2 and routers that were layer 3. Around 2000, every switch that I've ever worked with was a layer 3 switch, and it was being used for routing and switching at high speeds and high performance. So I don't do a lot of layer 2 stuff. The only kind of layer 2 switches that I even have are these kind of things like me that I have running through my house. And basically the reason I have these layer 2 switches, Gus the engineer, is I'm running a private cloud, an OpenStack cloud here, and I've got a bunch of servers that I aggregate into these switches, which that can plug directly into my router. And I'm running very high performance routers here that in this house. So yes, lots of layer 3 switches used for routing. And somebody asked a question about a trace route. We're going to get into that heavily, but I can show you a little bit about a trace route if you desire. But what we can do with it isn't going to be very useful until today. But I can show you a little bit about what it would do. So if we're on router 1 and we wanted to see how to reach 4.4.4, we would do a trace route, and it will show us the path. Trace route 4.4.4, and it's going to show us the path that it takes. And what would ultimately happen is, as it's showing us the path, it's going to tell us exactly how the path to get there. So let's see what it tells us. It tells us the first hop is this interface. And it tells you the next hop is here. And this is the third hop, which is the destination. So why is that important? Well, it's a great question you asked. So if I were to add another router, let's say I pop another router over here, and we draw a link between these two routers, and we turn this router on. Real quick, we'll just make a quick interface, and I'll show you what I mean by the full trace route. Because that's a great question. It's going to take a minute for the switch to reboot itself. Switch you up. Okay, let's go to this new device. Here we go. We've got a new device over here. Let's make sure it's ready. We can do this pretty quickly. I'm going to do some quick configuration of this by taking a couple of networking shortcuts, which I'm not going to recommend you guys do, but just for the speed and precision, we'll avoid any of the math, just to make it clear. So I'm going to configure this third router in, relatively fast speed. Okay, come up device. This reminds me of the processors when they were 25 megahertz and we had 16 megs of RAM. Okay, are you up? Come on, work with us. Please work with us. I love this question. Okay, so we're never going to do this crazy dialog box. So here's what we're going to do. We're going to let it come up. We're going to do a real fast configuration of this device. All right, so okay, enable. So let's give it a name, config T, host name, rar3, int, hello, oh, let's put a loopback address on it, IP address. .8.8.8.8. 255.255.255.255. No shut. Now, what's the link on this device that connects? Int G0/0. Help if I didn't put the O. Int 0/0. Let's say IP address. We're going to do 192.168.2.2, 255.255.255.252. No shut. Let's do router OSPF1. That's basically going to put everything into OSPF in a single command. That is not something we would normally do because we want security. But what are we trying to do over here? We're trying to work real fast to just create an interface. Now let's go back to router 2. And router 2, what is the Ethernet port that's connected to that? All right, let's just do. Router 2 is on the opposite side of that sign. So config T interface. What do we have at G0/2? IP ADR 192.168. What was the address we used? 2.2. So let's make this 2.1, 255.255.255.252. No shut. Router OSPF1. Network 192.168.2.0, 0.0.0.3, area 0. So if we did this right, our ports are going to come up. We'll be able to ping across the line, and we're going to form a neighbor adjacency directly over that connection. So let's see if we did. Show IP route. If router 3 knows how to reach, it can. So router 3 can ping 1.1.1.1. But what if it couldn't? What we would do is we would do a trace route to find the path. And watch, it's gonna give us the sequence. It's gonna show us the path. So the path is gonna work right now, and you're gonna see it. But what happened is if we were here and our data made it to here and then got lost, we would know to go to this router to see where the problem is. As you can see the path. It's mapping out the path for us. And then Chris has a few questions, which I definitely want to ask, sir. But you can see the path and how directly it gets there. There you see. That's what the trace route is, and that's the function. Chris, I know you had some questions for me. Okay, I didn't see the first half of the question, Chris.
They want to know, as an architect, am I going to be configuring? And the answer is no.
The answer is generally no.
And so this is the follow-up.
Okay, so why are you learning how to do this? Well, if you don't understand the routing tables and the routing information, you'll never be able to design anything as a cloud architect because the network is the foundation for everything. Why am I doing this? Teaching this basic networking configuration? Well, I can tell you that if you just had an AWS certified solution architect professional, it's not enough to get hired. And the thing is, as an architect, you have to have the internal knowledge. You have to know how it all works. And this networking thing is really, 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 really theoretical. So I'm giving you the configuration so you can see it. Now, here's the thing. When you're building a certification portfolio for a cloud architect, and by means, certification does not get you hired. It's everything else that does. But certification will get you an interview. And on the interview, they love to see infrastructure background, like networking or Linux. So how do you get a networking certification? You have to know how to do this. So what looks good for an architect? A network certification, an architecture certification, an MBA, leadership, emotional intelligence, executive presence, et cetera, ROI modeling skills. But networking is the heart of the cloud. And if you don't know the network, you don't know the cloud. So Why am I teaching you networking? So you learn the foundation. So when somebody asks you, hey, have you ever set this up? You can say yes. Why do you think I make my students build a cloud? Because when they tell their customers, I've designed and deployed an OpenStack cloud, the customer takes them seriously. So if they say, have you done it? And you say, no, it doesn't look good. So the answer is, yes, I've done it. But my background is design and digital transformation. But if they ask you if you've done it, I want you to be able to say yes. So that's the reason why. Yes, every device has an ARP cache, and the ARP cache is, you can configure how long it stays in memory. Absolutely. The longer the cache stays in memory, the less overhead and broadcast. But the more stale data can be there. So you got to remember that. And that's always the problem with the cache. But great question. Yes, routers have an ARP cache. Excellent. When you copy the running configuration in the router to the startup configuration, it stores it on the flash. That's it. Should we download my simulator? You can download my simulator. You can buy my simulator, and you can do like I did. You'll have to purchase the software for the devices. So you can do it, but realize it's going to cost you a fair amount of money to set it up properly. Layer 3 switching works completely at layer 3. What happens is we're going to create a VLAN, and we're going to give it an IP address, and the ports are there, and it is 100% layer 3, no different than a router. It's just that it's routing in between VLANs as opposed to routing in between physical ports, but it's 100% layer 3. Now, CT scanner, you're going back to WAN interfaces like serial interfaces, and they have data termination equipment and data communications equipment. But for the most part, we rarely deal with that stuff anymore. And that is provided by the service provider, typically speaking, in their DCE device. But the point is, I think it's DCE, DTE, but whether it's the termination device, which is your router where you connect it to, the clock rate is always supplied by the carrier, your service provider, that based upon the bandwidth that you've purchased. That's your clock rate. Now in labs, people set the clock rate, but in reality, it's done by the carrier. Yes, those blue rations are awesome. John Clark, I don't normally use acronyms, but if I said open shortest path first, that wouldn't mean anything to you until we talk about the open shortest path first routing protocol. So it's typically called LSPF. I don't know of anybody that uses the name open shortest path first. Kind of like very few people would say, today we're going to work on the border gateway protocol. In fact, they call it BGP, and that actually became known as its new name, its official name. So what are some of tomorrow's topics? We've got so much to cover. We haven't even begun to begin. Some of the things we'll probably cover tomorrow. And, I have to tune what we cover based upon, realistically speaking, what people are paying attention to. And I'm going to go back and forth based upon things. But what are we going to be doing? We're going to be talking about a lot of LAN switching. In the beginning of the day, we covered some basic routing. And then after we cover switching tomorrow, we're going to talk about remotely managing switches, and we're going to get our hands dirty playing with some switches. And then depending upon how far that goes, I'd like to get us into some VLANs tomorrow too. So happy to provide this training. Thank you so much for coming, Anil. Was thrilled to see you here. What is G0/0, G/1? That is the physical port numbers on the routers. So all these devices will be logically based on slot number and port number, and that's just the way they refer to them. If you go on your computer, you'll have an ETH0, an ETH1, an ETH2, based upon how many network cards you have in it. That's all it is. Good question, though. Sadie, I'm so happy you were here. Was thrilled to see you. I'll see you tomorrow. Mohammed, thank you so much for contributing. Everyone contribute. Thank you so much for being here. Sadie, yes, thank you. Thank you. All my blue wrenches, they're amazing. Thank you, Chris. And William Byrne, I am actually so happy to see you here today. At some point, you and I should sync up. I know you've got all kinds of great backgrounds, and I love to talk to you about that. Millicent, I'm so happy to see you here. Yes, it's all about competency. Why am I working so hard to make sure you all have the underlying technical knowledge so you're competent? Everybody type hashtag CCNA one more time. And when you're done with that, type hashtag cloud hired, because that's kind of our thing. Thank you, Pedro, for thanking Chris. Chris does so much work. Eric, we are so honored and privileged to be able to help make sure people have the best careers. We're looking forward to tomorrow too. Yes, please like, comment, share. We really love that. We really want to share our message. Abigail, thank you so much for everything. And I think I saw a blue wrench, so thank you as well. Jal, so much. Marjan, so good to see you. Anil, great to see you. Nosa, so wonderful to see you. Leo, thank you so much for helping out as well. Don, thank you. And yes, thank the blue wrenches. Thank you so much, Remy. We're going to start getting into more fun stuff when we talk about routing, but we've got to start somewhere. You're here. Yeah, we could talk crypto one day. I like talking crypto. I've got a lot of blockchain background. Thanks so much, John. Roshu, it's always good to see you. Have a good night. Alex, Yasas, it's good to see you. Marla, thank you. CCNA. Ivadaikia, CCNA. Hand of God, good to see you, CCNA. Casigo, so good to see you. Remy, good to see you, CCNA. Ivadaikia, Marla, wonderful. Abigail. Okay, so wonderful, wonderful, wonderful. Super honored and privileged. Grateful to have you all here. Honestly, it's just wonderful, wonderful, wonderful. And I'm just thrilled to see you. So let's get you all network hired, cloud hired, whatever you like. Let's make sure you've got the skills to be great at your job. We are covering 80% of the certification, but as you notice, I'm not exactly sticking to the certification things because I want you guys getting network hired or cloud hired based upon what you want. So I want you to be competent. Certification and competency aren't even in the same universe. I'm concerned about competency for you because that's what's going to get you hired. Loving seeing these names from all over the world. Actually, maybe for fun, tell us where you're at in the world right now. I know we've got a lot of people from all over the world, and I absolutely love this. Wow. Las Vegas, Amsterdam, Australia, South Africa, Nashville, Australia, Brazil, Atlanta, and Detroit. We'll keep the Detroit. UAE, that's a place I spent a lot of time and absolutely loved. Las Vegas, fantastic. Cayman Islands, Cornelia. Oh, wow, you're in a beautiful spot. Winnipeg, fantastic. Haven't been there in a little while. Nigeria, fantastic. We welcome you. Asheville, North Carolina, fantastic. Atlanta, you know, this is great. New Mexico, Moses. Germany, Anil. Gabriel in Zambia, fantastic, Gabriel. Wisconsin from MJ. Man, I love this. I mean, how many people we can get from all over the world, all coming together to make each other's life. Can you get this live again? You can watch this recording as many times as you want. We're going to leave it on YouTube. Share the wealth, spread the word, help as many people as possible. UK, Hand of God, I like that. Derek you're in Atlanta, Derek? Wow, for some reason. Molly's in Nigeria, I love that. Maryland, US. See how diverse we are? Charlotte, North Carolina. Cameroon, fantastic. Kansas, Maryland, Bridgeport, Connecticut. In Maryland, wow, this is great. Fantastic. Fantastic. So I will leave you all with, we're going to have some fun tomorrow. We're going to have a networking party tomorrow. So get some rest. Relax. Atlanta, fantastic. Mexico, I haven't been there in a year, so I love it. Florida, fantastic. That's where I'm at. My advice for you preparing for the CCNA is as follows. Follow this course, and like we said in the beginning, buy the 2 Cisco press books, for which case we gave you the link to it, and that's all you need. You're going to be in great shape. Chris, you want to bring in the next question? Okay, fantastic. So thank you all so much. Have an absolutely wonderful night. Get some rest because we're going to hit it hard. We got about 7 more days first. So I don't want to burn you out. I want you to become great network engineers, great network administrators, guys, cloud engineers, cloud architects, whatever the career of your dreams is. See you all tomorrow. Have a wonderful, wonderful night. Welcome, everyone. This is Michael Gibbs, and I'm the founder and CEO of Go Cloud Architects and Go Cloud Careers. And this is day 2 of our free CCNA program. Now, this is the CCNA 200-301 course, and my name is Michael Gibbs, and this is day 2. This is network administrator training, network engineer training, whether you call it networking for cloud computing or cloud computing technical skills. What we're here about today is to talk about networking. So, the networking is a critical cloud architect skill. It's critical in cloud architect training. And if you want a career, the best cloud career tips I can give you is to learn the network in the data center. So we're here with a complete and total set of cloud network training and a completely free Cisco CCNA course to help you build your best networking or cloud computing careers. So I like to view the CCNA as an intro to networking course, where we'll talk about everything from what is a computer network to CCNA course for beginners. But let's just face it, we're going to teach you networking. We're going to have lots of labs. We're going to have lots of discussion. We'll have plenty of time for questions and answers because I want all of you, whether you want to be a cloud architect, a solution architect, a network administrator, a network engineer, or a network architect, to get the right training. A little bit about me, in case you don't know, I've been working in networking forever. My Cisco certified internet expert number is 7417. I spent about a decade at Cisco as a lead architect in an industry vertical. I've worked for the world's largest internet service provider, which was WorldCom at the time, which is now Verizon. I had the opportunity to be a lead network architect on Wall Street and design the busiest market maker systems on the NASDAQ. I got to be a principal 2 architect at Comcast, responsible for the backbone design. I got to be an industry-specific architect at Cisco, and I got to be a lead architect doing consulting for IP multicast and video solutions over at Riverstone. So I've been doing this networking thing forever, and I've been teaching networking at Riverstone Networks, WorldCom when I was there, or even Cisco Systems. So this is me, and I've been doing it for a while. So we're going to have networking fun. So before we begin, let me tell you one thing that I want you all to attend. Please join me tomorrow for our completely free How to Get Your First Cloud Architect Job webinar. Please join us. The link is in the description below. We will tell you everything you need to do if you desire to be a cloud architect. And guess what? A lot of this stuff is going to be useful if you want to be a network engineer, network administrator, network architect as well, because we'll tell you the things that the hiring managers care about. We'll show you the things that should be on your resume when you have no experience. And we'll teach you all how to get cloud hired. So everybody, to let me know that we're ready to begin, type hashtag CCNA and also hashtag cloud hired at the same time. Hashtag CCNA, hashtag cloud hired. When I see a bunch of those, I know we're all ready to begin for the day, that you guys are awake, alert, and oriented and excited to begin. So give me a hashtag CCNA. And then after that, a hashtag cloud hired is 2 separate messages. When I see a bunch of those go across the screen, and it's going to be looking like a shower of cloud hired and a shower of hashtag CCNAs, I know we're going to be out there. Now, tomorrow's free webinar, while you're giving me these hashtags, is going to be exclusively on Zoom, not YouTube. And here's the reason. I want every one of you to be able to ask questions live. Come to this session. We're going to have an absolute ball. I'll tell you how to get hired, and you can ask me questions. We can go over your background, your goals, all of it, all of it, all of it. So love to get you all cloud hired, network hired, or whatever it is you want. Network administrator, network architect, network engineer, solution architect, cloud architect. The whole point is to get hired. So tomorrow's webinar is extremely exclusive. Going to be limited to the people that sign up on Zoom. So sign up now and let's make sure we have a great day tomorrow. Let's get you all CCNA certified in our CCNA 200-301 class. And this is free CCNA 200-301 training part 2. So let's get into the fun. Let's start talking about our CCNA course. Today we're going to talk a little bit about LAN switching. We'll talk about LAN switching concept, and we'll actually walk through playing with some switches. No, we'll have a ball with this. So let's talk about, what is switching and campus LANs. So realistically speaking, this is pretty normal. You might have a data center, and then across the building, you may have a bunch of users for that. So you can kind of think about that. In this particular environment, you've got a data center, and then you've got the campus. And the campus is a bunch of people plugged into switches, which ultimately go to routers, and they have high-speed connections back to the data center. That's traditional environment. Oh, wait, cloud computing. Guess what? See where we have the campus LAN? We have two connections to the cloud provider, and instead of being the data center LAN, it's just a cloud provider. So data center here, cloud there. Nothing changes. So if this was on the cloud, guess what? We'd have the same virtual machines that we'd be using the switches at Amazon or Google or Microsoft, or it doesn't matter. And it's the same thing. What is a cloud? Somebody else's network in a data center. So what is a cloud? It's a rented data center that's a virtual private data center. That's it. So this is your typical campus, but this is also your typical cloud environment too. It's the same thing. So when we talk about switching, we kind of have to look at what we're switching. So remember that we're going to talk about Ethernet, because when we're switching, we're predominantly dealing with Ethernet. So what does an Ethernet frame look like? Well, remember, we've got the preamble, we've got the destination MAC address. Where's it going? Source MAC address, the type, the data. Now that's your payload. So it could be a voice packet, it could be a video packet, it could be anything. That's your payload, but it's a frame at this level. And then there's this thing called the frame check sequence. It's basically, if that gets corrupted, you know that your data is corrupted or your frame's corrupted. That's all. We don't need to make it complicated. And I know in networking, in cloud, we make simple things very complicated, but we don't have to. Well, that's really all that's going on. So let's walk through it. Typical switch forwarding. So let's say we've got Eva Doikia over here, who I like to call Evo, even though it's not her real name. I just like to call her that, and she's super awesome. We've got Laman, who's a fantastic network engineer over here. We've got me over here, and we've got Chris over here. So what's going to happen if we're in the switch, what's going to happen if Laman wants to speak to Eva Doikia, he's going to send the frame. And what's going to happen is the switch initially is going to say, I don't know where to send it, so it's going to flood it out this port, it's going to flood it out this port, and then it's going to flood it out this port. And then what's going to happen is Eva Doikia, where it says Evo, is going to say, I have this MAC address, let's talk. And then when Eva Doikia responds, it goes into the switch. And the switch says, do I know where to send it? Which port? And it looks in its MAC address table, and it says, I sure do. Laman sent a request to Eva Doikia on fast Ethernet port 01. So what happens is this port gets flooded out all ports. Then Eva Doikia responds, and Eva Doikia responds, and then the switch looks in its MAC address table, and it says, yes, I know the destination MAC address, go out this port. And now, as long as Eva Doikia and Laman are communicating, everything's working perfect. Now, if Eva Doikia says, I want to send a picture of Mike's cat, so I want a picture of Mike's cat. So Eva Doikia requests something from me. She wants a photo of my cat, Cindy. She loves cats. So the request goes out this port and this port and this port too. And then I respond, I'm here, Eva Doikia, I'm here. And I respond to her. And now the switch looks at it and it says, does it know Eva Doikia's port? If not, it floods. And it says, it sure does, because we sent it. And now you see. So what we see over here, this MAC address, that's like the routing table at layer 3, but at layer 2, switches forward on MAC address. At layer 3, switch routers forward on IP address. Same thing, no difference. So that's really what's going on. At layer 2, at Ethernet switching, we're dealing with MAC address tables. So now let's pretend we have 2 switches. Same thing. Laman wants to send out something to Eva Doikia, but he's never sent her a packet before. So what's going to happen? Well, at first, it's going to be flooded out this port, which is then going to get flooded out this port and this port too on a separate switch. And then it's also going to flood it out this port. And then Eva Doikia responds and says, I have this MAC address. And guess what? The switch builds an entry in the MAC address table if you ever hear the term CAM table, which means content addressable memory, same thing as the MAC address table that they're talking about. And realistically speaking, that's how all this stuff works. So pretty simple stuff. Switches forward based on destination MAC address. If they don't know where to go, they flood it everywhere. Then somebody says, I got it. And then it only sends it out that port and the rest of the ports don't get used. So switching really constrains your traffic. The only time you have broadcast is either it's a broadcast that gets sent out all ports, or if it's a unicast frame, meaning one to one person, and it comes out until you learn, you send it all ports, and as soon as you learn, you only send it out the right port. And that's what we're talking about with switching. That's the way the learning works. That's how switches determine how to send data from point A to point B. And if you want to look at it a little deeper, what you can see is when these packets are flooded, you can see what's responding. There's an address table before and afterwards, and it's populating. And that's really what's going on. It's really no different than things. So because of that, because the way bridges and switches work, where they take in your traffic and they flood it out every port, except the one it came in on to learn. So switches flood traffic out every port, except the one it came in on. So know that. That concept is critical for what we're going to get into next. Switches take all unknown MAC addresses and they broadcast it out all ports until someone says, I got it, and then it only sends it out this port and not the rest. So that's how switches learn. So I want you to think about something, and I want you to really understand the complexities of how challenging this could get. So now, let's pretend we've got frames and we don't know where to send them. So let's look at this example, and I'm actually going to draw this with you while we talk. I want to talk about it, and yes, I've got professionally drawn slides for this, but let's just have a little fun and whiteboard this out. So imagine this. You got a switch 1, SW, call it 1. And now let's have a little fun with this. Let's add switch 2. Switch 2. While we're at it, let's copy these things. Let's make switch 3 and switch 4. Now this is where things get ugly. So of course, we never want an environment without redundancy. So if currently speaking, we have something that looks like this right now, as it stands right now, switch 3 can talk to switch 1, who can talk to switch 2, switch 4. So everyone right now can talk to each other. Now we've got no fault tolerance in our network, and this would be a horribly stupid thing to design our systems this way, because there's no fault tolerance. This is about the equivalent of using a single cloud provider, something you should never ever do, and that's why you should always go multi-cloud. But let's just say over here you've got Evo. So you got Evo Deutsche sitting on over here, EVO. So Evo is over here. Now Evo likes my cat Cindy, and she wants to send a message to Cindy. And Cindy's really sweet. So what happens is, currently speaking, this is the way this is going to work. Evo Deutsche, and let's make sure we have a couple extra ports on the switch. This is going to be an Ethernet LAN, and this, by the way, is a symbol for a LAN. And there's a reason we're working through this. And by the way, let's put an extra switch port over here, and let's pop an extra switch port over here. So now I want you to really think about this. Evo wants to reach Cindy. So yesterday we talked about so she says, what's Cindy's IP address? And she does an ARP. Who has the MAC address for Cindy? Now, as soon as she does that, this packet is flooded. The switch doesn't know where Cindy's MAC address is. So it hits switch 4 sends it out this port and this port into switch 2. Switch 2 sends it into switch 1 out this port. Oops, I don't even know what happened there. And then switch 1 moved it over to switch 3, and switch 3 sends it to Cindy the cat. Cindy the cat purrs, meows, takes a selfie with my cell phone because she steals things. My Cindy's a thief. She steals everything. Now Cindy responds, and now the next time Evo wants to talk to Cindy, it follows the path because she already knows. Now, Cindy and Evo are talking to each other, and they're all having a really good time. And then we decide that Evo likes cats so much, she wants to see Chris's cat, Cindy, or Sunny. So now we've got Sunny over here, Sunny the cat, and I'm going to show you what's going to happen when these guys try and talk. So right now, everything's fine. But Sunny the cat read Mike's manual that says, never have any single points of failure. So Sunny the cat decides to put a cable between switch 3 and switch 4. And Sunny the cat says, Mike, I heard you say 1 is none, 2 is 1, and 3 is greater than 2. So I added an extra cable. Now, I want you to think about a problem. So Evo sends a message request. ARP, who has the MAC address for Sunny? What happens? I want you to think about this because this is where it gets ugly. And this is why we're going to talk about another protocol. So Evo sends the message to switch 4. Switch 4 sends it out this port and this port. Switch 2 sends it to switch 1. It sends it out here. Now switch 1, it sends it over to switch 2. It sends it out this port. It sends it out this port. But it also sends it out this port. And now we've got traffic that's going to be circulating forever, all this unknown traffic. Eva Doikya sends a ARP, or a broadcast message. It circulates. The network recreates it. It's one message. It becomes 2 messages. It becomes 4 messages. And the next thing you realize, the network is dead. It's called a broadcast storm. And why does that occur? Because switches forward unknown broadcasts out of all ports, except the one they came in on. So, Sunny the cat, when she read my manual on high availability, when she said, I'm going to run an extra cable, and she did, she broke something. Now, why? Because the way switches behave. So what if you could run this cable between these 2 switches and tell the cable, don't be active. And then if this thing fails and this link goes off, tell this link, be active immediately. So now Evo sends the message, it goes out switch 2, there's no place to go, it goes out this port, it goes out this port, and now it hits Sunny the cat, and Sunny the cat comes in and brings it back, and it goes back to Evo, and we don't have this problem. So when we're dealing with switching, which is not routing, switching cannot have all links active at the same time, or you get the looping of your traffic. It's called a broadcast storm. So we need something that will tell these links to dynamically block, unblock, block, unblock, block, unblock. And that's how we make our systems reliable. So that's called a broadcast storm. So if you're there and you're paying attention and you got it, type hashtag CCNA, because now we're going to get into the spanning tree, which is a little ugly. So I want to make sure that we're all ready. So give me a hashtag CCNA, and then we'll go start talking about spanning tree. We'll be talking about that today. So what do we do? How do we stop this? We create that dynamic protocol. That dynamic protocol is spanning tree. And I'll show you why. We'll look at MAC address tables of switches. We're going to have some fun. And when we do this, it's going to make a total bit of sense. So start walking our way through. Alexandros, I'm happy to see you. Tom Orthios, Doidio. For the rest of you, CCNA, I think it's so fantastic. Fantastic. So let's have some fun with this. So now, if we look in this environment, we clearly can see that this stuff looping around forever is a problem. So we're going to have a protocol called spanning tree, which we're going to get into at some point to talk about that. But I want to make sure you understand it. So these switches build a table, and it looks like a routing table, but it's not. It's a switching table. So what's it going to look like? If we go, when we'll do this, at some point we'll do a show MAC address table on one of our switches, and here's what you're going to see. You're going to see the MAC address, the VLAN, and the port numbers are associated with it. And when you do that, you're going to totally understand it. It'll make total sense for you. So now Let's go back to the single switch, remind everybody what it looks like. Everybody's sending information to each other. Single switch topology, we don't have any of these problems. So let's get on board. Let's get on the switch for a little while. Let's have some fun with it. Let's boot up a switch. Let's walk through the console. So let me go to my fancy EVENG server. Right now, pretty sophisticated setup we actually have running here. This is a full enterprise grade version of this. Let's do this. Let's make a new lab. Closed lab. Okay, so if any of you guys ever decide to invest in an EVENG server, and again, this can get fairly expensive because for what we're using here, we're using a 24-core server with a half a terabyte of RAM. We're making sure we've got all the good stuff on it. But that's for us. So let's just basically, we're going to create a new lab and walk through our place with a switch. We'll call it basic switch. And in the switch, we'll just say demo. And if you happen to get an EVENG server, there's a community one, which is great. This is obviously the production kind that organizations use to test things. Demo switch. So let's make sure we do this. Now we're going to save this. Whatever. Do I need to add anything else? Name, description, demo, save. Why is it not taking it? I must be missing something. Oh, basic switches. There we go. I guess it would help if I would read the instructions, which would tell me that I named the same thing twice. So let's, in our object over here, in our node, let's pick a Cisco IOS on Linux switch. Let's add some Ethernet ports. Let's change it to 24 so it feels like a switch. Let's save it. Now let's take this switch up. Let's boot it up. Let's console into it. And hopefully you guys are having an easier time seeing this. What we decided to do is we found some settings on the browser, which should be able to make it a little easier for you to see. They do take a minute to boot, so we'll work our way through it. All right, come up, wake up. Okay, as we can see, the router is coming up. It's coming up. Slowly coming up. That is the thing with technology, especially when you're doing live demos. It's never as fast as you want it to be. And, at some point, I promise you're going to be doing lots and lots of demos of stuff, especially presentation demos of things. And when you're in these kind of environments, let me tell you, you find yourself to be pretty busy. So, and reality is demos never work the way you want them to be. But that's just part of life. So is our switch fully up yet? Okay, we're here. It's a switch. So everybody, let's walk our way through the switch a little bit. Let's have a little fun with the switch. So let's look at some things we can do on the switch. So we can look at the interfaces, right? So we can see what's kind of in there. So let's look at the interfaces. So let's do the show interface status. Show interface status. What do we see? We can see there's a whole bunch of ports in here. What do we see? We see the G0/0 ports, the G1/ ports, the G2. And when you see these numbers / something, they're referring to the card number and the port number per card. Just kind of keep that in the back of your mind. That's what that means. So now you know what it looks like. You can look at a switch and there's there. So we can also see what VLANs exist. We'll talk about virtual LAN. So what you're going to see here is VLAN 1, which is the natural VLAN on all switches, which is a virtual switch. We'll talk much more about VLANs. Now you're also going to see a couple other VLANs. I'm telling you this, FIDI was something that we used to use back in 1999, 1998, 1997. So these kinds of interfaces, for the most part, are some pretty old networking things that we're not going to be using. But keep that in the back of your mind. VLAN 1, and we can create as many VLANs as we want on these devices by using some VLAN things, and we'll be walking through configuration commands as appropriate. So let's pretend we wanted to see what was going on one of these interfaces. We'd be able to do a show, interfaces. Let's say we pick an interface G0/0, and we could look at counters. And what this will do is it'll tell us, how much stuff was passing through the traffic. Guess what? How much stuff is passing through there? None. Do you know why? It's dead. And that's why, and I'll show you why, we're not going to get anything to our show interface counters. But I still want you to understand what it is, just so you know what it is. Let's walk through some other stuff. If we wanted to see the MAC address table, and we're going to build a lab later where you can, what we would do is we would show, how I showed you before, we would do a show IP route for the routers. That's going to give you your layer 3 routes. How many routes are we going to have here? None, because we didn't add any. But if we did a show MAC address table dynamic, we could actually see all the MAC addresses that were learned out all of these switchboards, which again is none. Why? Because it's a brand new switch. And that's kind of the reason why. So let's go past this. So heck, while we're at it, let's continue with the lab that we're doing over here. For example, I walked you through how you do the show. So let's talk about basic switch stuff now. Let's do some basic switch configuration. So let's have a little fun with it. Let's talk about how do you secure the CLI. And then we'll talk about enabling an IP address for remote access. And then we'll talk about some miscellaneous settings. So switches and routers, you can access them via a few ways. The virtual terminals like Telnet or SSH, the console where you plug it directly in. So in any case, you have the two things on the switch, just like you did for the router. So let's go back to that router like we did yesterday. When you log into the device and you first press enter, this is called user mode. And if you want to do anything here that's substantial, like config, no, it's not going to let you. So if you've ever been on a Unix machine, you try to execute something and you don't have execute permissions on the script, it won't let you. So this is no different. So if we want to configure or do anything complicated, we have to get to enable mode, also called privileged executive mode, otherwise known as root. All right, when you become root in Unix, you can do pretty much anything you want. So kind of keep this in the back of your mind. So now we're talking about root. So let's talk about some other things that we can do when we first get this. What should we do first? Guess what? We should probably put a password on the switch. So let's configure it. Configure this router. How do we configure switches and routers? We type config terminal, config T, terminal, config terminal. Wow, we're in configuration mode. How do you know? It says config. So let's change the name on the switch. So let's call it hostname Evo. Picked Evo. Obviously, you have to spell the word hostname correctly. Now, guess what's the switch called? It's called Evo. Pretty cool, right? Now, let's put a password on this switch so that you can't just type enable without a password. What do we think we're going to do there? We're going to type password. Now, because many of you at some point will do CCI labs, and they'll force you to use the password Cisco. We'll just call the password Cisco. By the way, for the longest time, that was the most common password on the internet. With me. Now, what happens? We'll get out of this. We want to go to log in. We're there. Enable. Wait, it needs a password. I have to type correctly, and now it lets me in. So that's the first thing that we're going to do with all these devices. We're going to configure it. Thank you so much, Aguilo. we're going to configure it. So next, let's configure our virtual lines. So config, so we can do this. We can go to our configuration and we can type config E. We could do line virtual terminal 0. We can pick 4, 0. We can 15. We can type login, type password. So what you can see here is we went to the virtual terminals. We set up a password. We determined whether we would allow SSH or Telnet in. I just decided to do both. And that's realistically speaking what we're talking about when we're setting these things up. It's pretty easy. And there's lots of ways we can do this. So now let's look at this. So when we run through our running configuration, or what's actually going on the routers, let's make sure we're here. Show run. You're going to see something that's probably not the best idea. Show run. So as you're looking at the running configuration of this, if you have the password to log in, guess what you can see? You can see the password. Now, what if, for example, I'm doing my network architecture, my network design, and I'm having a ball with it. We're super excited. And I bring in my buddy Billy Bob to help me out. Now, Billy Bob is, what do you call it? Billy Bob is an expert on BGP. So I brought Billy Bob in to look at my BGP. Does Billy Bob need to know my passwords? No. So we should never allow that. So how do we fix this? We configure this. We type enable secret. When we do this, and it's not going to like that. So let's see if it enables us to do it again, and it won't. So let's give it Cisco 1 instead. Now let's look at the running config. Show run. What do we see? We see we can see the new enable secret password is this. Now what else can we do? We can also do this. Config T, we can do service, passwords, encryption. Show run. Making sure our passwords look like this as opposed to like this. So we can get rid of that. Gonna make life easy. No, enable secret. And that's how quickly we remove it. And it's done. So just kind of keep this in the back of your mind. That's kind of the things we're talking about. Let's walk through some little more things on the switch. Okay, so there you go. I've enabled Telnet and SSH. Reality is in today's world, we should only implement SSH because it's much more secure. But, just kind of keep that in the back of your thing. So the next thing that we're going to talk about is switched virtual interfaces. Let me see how much more content we have on that to determine whether we should take a break or not. So let's talk a little bit about switched virtual interfaces, and then I'll take a break and we'll go over some questions. So let's go to this environment here. So in a lot of environments, you're going to have what's called a switch inside of a switch. And what I mean by this is, got this switch. Great Cisco switch over here, and it's got a bunch of ports. At some point, I can chop these ports up into multiple switches. So what if I decided to say these ports over here were a single switch, and these ports over here were another set of single switches, and another set of ports here was a switch, and another set of ports here was a switch. That would be called a virtual LAN. And what is a virtual LAN? When you take one switch and you chop it up to multiple logical switches. In cloud computing, what is a virtual machine? You take a server, you smack a hypervisor on it, you use that hypervisor to chop it onto multiple things. So how old do you think virtualization is? Old. All the things that cloud computing is doing is old. It's 40 years old. This is virtualization 30 years ago. Pre-VMware even. What is it? You take a switch, you chop it up into a lot of switches. Now, what happens, and we're going to talk about this, is when we put our ports together, if we cross subnets, we need a router. And by doing so, we need to route between subnets. So what will ultimately happen, we're dealing with switches as the concept. We can create a VLAN, but we can also create what's called a VLAN interface. And what is this? This is something very special, and it's something very different. So if we go back to our server, if I create an interface, I can create an interface called a VLAN. And let's call it interface VLAN 1. Now, with this VLAN, what can I do? I can do the following. I can give it an IP address. 192.168.1.1, 255.255.255.0/24. I can give it a no shut on this command. Now, guess what? I've got an IP address to the VLAN. Now, if I created two VLANs, let's do it. Interface VLAN 2. And in this VLAN, I do an IP address on a different subnet. 192.168.2.1, 255.255.255.0. No shut. Now let's look at this. If I do a show IP interfaces. Let's do a brief so we don't. Now, what do you see? Oh, wait. You got this VLAN 1 and VLAN 2. Now, you got two interfaces. Now, if we were to enable routing on this device, it would route between these interfaces. So how's this VLAN thing going to work? We're going to add ports. We're going to take, these ports over here and say, hey, you're VLAN 1. And then we're going to take these ports over here, for example, and say you're VLAN 2. Or all of these are VLAN 2. And by determining which ports go to which virtual switch, guess what we have? Virtual switches. And what are the interfaces? It's a router inside of the switch. So a layer 3 switch is you take your ports, you add your ports to the VLAN, and then you convert this VLAN, and then you add IP addresses and you route between VLANs. So it's pretty cool stuff. So let's look at this. Look at this slide to see. So now we've got these ports in this VLAN, and we've got this port in this VLAN. Now we're routing in between subnets identically to the way we would do anything. Now let's just talk about this, the default gateway. So if your switch is not a router and you want to manage it via SSH or Telnet, it's going to need a route to be reached. Now, what could you use for the route? A default gateway, a default route. So your switches, if they're not layer 3 switches and they're not doing routing, will definitely need a default gateway to be managed. Just like any other computer that you have in your environment. If you wanted to configure an interface, we showed you how to do it. It's that easy. Guess what? If we wanted to put a default gateway on it, we could do the same thing. We'd go back to our device. Config E. I've got the. I don't really do a lot of work on switching. I predominantly work on routers in my life because I'm more of a routing I was more of a routing engineer and then a routing architect. But the point is, IP, and I think it's default-gateway, and you would just give it an IP address, 1.2.3.4, just like you would your PC, other than you would hard code and manually assign it, as opposed to doing this. What do you call it? I'm sorry, I was going to show you how you do that. So if you wanted this to work, you would do an IP I'm going to put a default gateway on this, IP, default, gateway, and then you give it an IP address, 192.3.4. And we don't want to install that because we don't have a router for it to point to, 1234, but kind of just keep that in the back of your mind. That's what we're talking about. So while we're at it, you could also configure to switch to use DHCP, which would be insane. With networking devices, we don't do it, but we could do config T. Oops. Let's create an interface, VLAN 3. And in this, we could do an IP address, DHCP.
Hey, Mike, are you sharing your screen?
Oh, nope, I am not. So let's get out of this so I can demo it again. You can do this with this. Well, that didn't work. Give it a minute. It's trying to resolve the DNS name clear. I should have disabled that functionality for the demo. Bear with us for a couple of seconds. But the good news was it'll clear the screen from some of the excess that I had here. Now, if you're working in a cloud environment and you have a direct connection or a private line or direct interconnect or express connect, as Azure likes to come up with their creative names, guess what? You typically send them a VLAN. So now you know why. So let's say we create interface VLAN 3. We can, generally speaking, you got to be in configuration mode. Interface VLAN 3. When we can do this, we can put an IP address. They used to let you do via DHCP, but they don't allow you to do this right now. But they used to let you set up with DHCP. And remember I said never let anything automatically? Well, I guess that's why they disabled it. So you would just pop an address like 172.16.1.0, and then you'd enter a subnet mask. And you're good to go. And then you do a no-shot on the interface, and Bob's your uncle. You are 100% up and running. Life is good. So, see if there's anything I wanted to show you. Now, there is one skill that I should try and show you. Generally speaking, these routers try to resolve DNS until you said that. And what they will do is they will literally try and telnet into whatever you put the IP address for. So if you don't want that to happen, what you do is you set no IP, it's domain -lookup. Now when you enter something silly like Cisco, nothing will happen. And then it won't be trying to resolve it for you, and you're good to go. So let's do this. We covered a whole lot of tech, like a whole heck of a lot of tech. So Chris from my team is going to bring some questions in. We'll bring some questions in. We'll answer some questions. And of course, this is networking. So networking is fun. So let's answer some questions. Let's make sure everything is clear. Chris, I know you've been seeing questions. I've been babbling about networking. I love networking. So let's make sure this is the best Cisco Certified Network Associate Bootcamp you take. Let's make sure it's the best Cisco CCNA 200-301, CCNA 200-301. And this is a free CCNA bootcamp. So bring in your questions. We want to help you learn the network, learn the cloud, and get cloud hired, network hired, and everywhere in between. So Chris, bring in some questions.
Mike, are you looking at the screen?
Yes. StreamYard.
It's on the screen.
I don't see anything in StreamYard. Oh, wait, hold on. I could have two. Sorry about that. Apparently I had two separate StreamYard windows open and didn't even realize. Sadie, we don't use Telnet anymore. We use SSH. I just mentioned Telnet or SSH because there are some companies that are still using Telnet, but the reality is nobody should be using Telnet. It should all be used as SSH. Good question. I would recommend not using it, but people still do it. So there's that. Chris, you want to bring in the next one? Okay, so Angela, this is a good question. So the reality is this. You will never be able to put more than 250 hosts, max 500 in a single subnet. Here's why. ARPU has the MAC address of this. ARPU has the MAC address of this. Who has this? Who has this? So there's so much broadcast. So you're never going to be able to put more than, say, 250 to max 500 users in a single subnet. So we have to segment the network, otherwise the network falls apart. So that's why we're doing it. Now, let's think about it this way, Angelo. Let's talk about some other reasons. Let's say you work in the security department. They can put you on a subnet and then create a security policy that only you in the security department could even be able to reach what do you call it? To even be able to reach the management ports of the switch. So you can literally put your users in a VLAN and make it that they can't see anything outside of that VLAN, or which they do. So we're creating VLANs for network scalability, but also security. A finance VLAN, a development VLAN, a production VLAN, an interfacing VLAN, all separate from each other. So our demilitarized zone, where basically our firewalls and our load balancers sit, and our VPN concentrators sit, that's going to be one VLAN with a set of security policies. Now, we're going to have different VLANs for different departments. The CEO may need to say everything. Somebody else may only need to access to one set of things. So we segregate our users. So by doing it, it's like having a house with a lot of bedrooms. You go to this bedroom, you go to this bedroom, you go to this bedroom. But the other reason is if we buy a high availability switch. Now, when we deal with the cloud providers, they're like, oh, use any old router to connect to us. It doesn't matter. We're reliable. Now, what happens is when we're connecting to a cloud provider, if that router dies, we lose everything. So we can't be afforded to do this. So we're going to be using big routers to connect to the cloud. Routers with 2 brains in it, 2 control modules in case one fails. Routers with multiple power supplies plugged into different outlets. So if there's a power failure or a circuit breakage, the network doesn't go down. We'll be putting our stuff on multiple line cards. And by the time we're done with this, these switches get really expensive. So by being able to virtualize them and create multiple VLANs, we can reduce the cost. So it's like any other kind of virtualization. Is it cheaper to go to AMD and buy one of these awesome 128 core servers with these epic CPUs and about 6 terabytes of DRAM and run VMware? Yes, huge. Where it would not be efficient to just buy a bunch of 4 core servers and buying 30 of them. And why? 30 sets of space, 30 sets of cooling, 30 sets of power. And that's the reason. So great question there. Chris, if you want to bring in the next one. Well, Elvis, at layer 3, we have a destination IP address. So when layer 3 gets mapped to layer 2, I have the destination IP address of 1.2.3.4. So what do? ARP! Who has the MAC address of 1.2.3.4? And it literally says, when you sniff it on a protocol analyzer, it'll say, ARP! Who has the MAC address? And when the person responds, I have this MAC address, then the switches see where that source frame came from, and it adds it to their memory table. And that's it. Great question there, Elvis. Could you use dynamic host configuration protocol? Millicent, I want you to think about what it would be like using dynamic host configuration protocol. So let's say you've got 10,000 routers in your network, and let's say they miraculously just automatically IP address themselves. And, at least where it's out, and this router used to be one address, but tomorrow it's a different address, and tomorrow it's the next day. You would have a network that would be a disaster. And when you'd be trying to SSH into things to fix things and looking in the routing tables, you wouldn't even know which router you were at. Now, Millicent, I did see one person try this, and we advised them not to do this for this reason. And we said, if you do this, make sure you send your DHCP lease to infinite permanent so that it's effectively the same as a static IP address. The customer's like, yeah, Mike. So anyway, I brought in some extra experts. They all said, never do this. And the customer decided, we're doing it. And the customer did it. A few weeks later, their addresses were changing. They had outages, and they couldn't even figure out where the outages were coming from. So I don't recommend dynamic anything. When you set up a server in the data center, whether it's a cloud or regular data center, you set the speed to the full or the speed to the max speed, and you set the duplex to full. And you do it on both the switch. We don't even allow auto negotiation because it causes problems. So no auto anything for anything critical. Carl, if I wanted to connect your PC and 2 laptops at home, would I just need to buy a switch? If all you did, Carl, was plug those 3 PCs in a switch, they would be fine. Now, if you wanted to make sure that one was yours and you could access anything, one was your child's and they could only access something, and then one was your husband's and he wanted to access everything, but you didn't want him accessing this thing because he likes to purchase exotic cats and buy $5,000 cats, and you don't want him to buy $5,000 cats. You want him to rescue domestic cats from the cat store. You could put him in his own VLAN and you could limit what he's actually able to even do. So, kind of keep that in the back of your mind. And then if you wanted to connect your subnets to them, you would need a router. Exactly. And they would have to configure their router with a route back to you. Exactly. Excellent, Kenya. I don't know what you mean by drop, so I can't actually answer that. But if you're referring to DHCP, we should never use it to configure a router. Why do you use 04 on VTY? I don't know, John. For some reason, Cisco made up those virtual terminal lines, and that's why I'm using them. Don't know otherwise why they call it that. No, listen, what if we had a bunch of devices to configure? That's why we have lots and lots of network administrators to go configure them. Yes, we're going to configure thousands of them, and they're all going to be configured manually. There's no auto anything. Raw meats too. Can we talk more about VLANs? We'll be discussing VLANs in a lot of depth throughout the course of the program. What about enabling IP routing? We're going to be doing plenty of that, Mark. We did some of it yesterday, and we're going to be doing a lot of that when we get into the routing sections. Mohammed, I don't know what you mean by controlling the priority number of the switch. There's about 1,000 different things in switches and routers that have priority numbers. If you're talking about spanning tree, at some point we'll talk about setting the root bridge and setting the root port and determining these kinds of things. No, it doesn't get pre-populated. It floods until the devices respond. Chris, you can go to the next one. Is it reasonable to assume that all switches have the ability to route? No. We have layer 2 switches, which don't have any routing capabilities. And we have layer 3 switches, which can do routing. And ARP is not done for routing. ARP maps an IP address to a MAC address. Routing is done via static routing protocols, interior gateway protocols such as RIP, enhanced interior gateway routing protocol, which is Cisco proprietary, so we probably don't use too much of it. OSPF is open short dispatch first. IS to IS, which is intermediate systems to intermediate systems. These are routing protocols. BGP is an exterior gateway routing protocol. That's what's used to route. But no, not all switches can route. But it's a good question. Linux, what is the max number of devices that can be assigned to VLAN? Well, you could potentially assign an infinite number. Once you get past 250, what happens for the most part is the systems have too many broadcasts. ART broadcast, net buoy, net bios kind of stuff. Apple bonjour broadcast. Who's got which server message block broadcast? These systems send broadcast. So once you get above 250 systems, for the most part, your systems are overloaded. So that's why you constrain it. I have taken VLANs up to 512 devices, but they were only very specific computers that didn't have a lot of broadcast, and they were really tuned down. And it was more of a blockchain data center. And the thing was, we had about 1,500 blockchain servers, and they were dealing about 10 megs of data because everything was small little transactions. So we shoved 500 in the VLAN, and it worked, but we really pushed it for that. So 250, and layer 3 switches enable you to route between VLANs. Otherwise, you've got to connect your VLANs to a router to route between VLANs. Well, Kaigoso. So layer 1, physical layer wire. Layer 2, MAC address card. Layer 3, IP address. Layer 4, TCP, UDP, ICMP. So when you think about this, if IP addresses are layer 3 and MAC addresses are layer 2, ARP, who has the MAC address, of a layer 2 thing, you can see where that protocol sits in between layer 3 and layer 2, where it's functioning. It's mapping layer 3 to layer 2. Good question there. In the coming sessions, will we have information about subnetting? We will bore you to death with hours and hours and hours of subnetting. Absolutely. But we're breaking it down into certain parts. So yes. And hours on routing. To add to the question about how connecting a router with a route back to you, then how does hacking happen? So just think about it this way. The second you connect to your internet service provider, you have a default route which says send everything to the internet service provider. Done. Now the internet service provider has a route back to your subnet. So that's how you're getting hacked. If you didn't have a route to the internet and they didn't have a route back to you, you couldn't connect to the internet. That's how hacking happens. But it's a good question. What is an ARP response? An ARP response is, I have the MAC address for this IP address. Literally speaking, take a sniffer. Or go to if you have a Unix system or a Linux system, super user or sudo based upon the thing. Do a TCP dump -I attach to your Ethernet interface. And then start going to different websites. And you'll see your system will do an ARP who has the MAC address of Cisco.com. You'll see it. ARP who has the MAC address of Amazon.com, and you'll see it. You can literally see those messages unfold right before your eyes. So we're going to get back to the content in 1 minute. Please type hashtag CCNA. So I know you're here, you're awake, you're alert, you're oriented. Hashtag CCNA, please. And then we'll get back to the content. And while you're typing hashtag CCNA, I can answer one question, and then we'll get back to the content. Chris, you want to bring in one more? Well, everybody's typing CCNA, so I know that everybody's paying attention, awake. Raw meat stew, how do you keep networking information in your head? Raw meat stew, I got to tell you, I've been working in networking for 25 years. I will tell you that after I became a CCIE, that's when I actually started to learn networking, that all the CCNA, all the CCNP, all the CCIE stuff for me, that was just my intro to networking. See, what happened is after I became a CCIE, what happened is then people would start to bring me on the big projects. And when I got brought onto these big and massive projects, I was doing things where the simple became complex. And let me tell you this, if you take something that will work and then you scale it 10,000 times greater than anybody thought it would be, unless your design is perfect, it's going to break. So raw meat stew, as an architect, what did I do? I spent 99% of my career fixing things that were done by jack of all trades and a master of none. These were really, really, really smart people. I mean, in many cases, far smarter than me, but they knew a little about a lot of things and they didn't know anything well. So what happened is every time they did something in the network, they'd break it and then they'd bring in a specialist like me to fix it. So that's how I got it, about 25 years worth of experience. But you're going to do well. By the end of this week or the end of next week, you're going to have good networking knowledge. Play with it for a little while, study it, work as a cloud architect, network architect, and you'll be just like me. Who knows, maybe even better. And my goal is this, for all of you to be better than me. That's why I'm here. That's why I train hard. I want you to be the best in the world, whether it be a cloud architect, network engineer, network admin, etc., etc. So, Chris, should we get back to the content at this point? I see people are popping in CCNA. I know they're awake, alert, and oriented, and that's what I care about, because if you're awake, alert, and oriented, you're going to learn networking, and it's going to be fun. So we'll get back to the content here, Chris. We're going to do a little more switch stuff. For example, just to walk you through a few more things. I want you guys getting a really good experience out of the whole thing. And then from there, so let's go to my EVE-ENG server. Let me see if I can find my EVE-ENG server real quick. Oh, here we go. Let's walk through the content we've got over here. So now let's play with an interface on a switch. Let's try to make it a little clearer for you guys. So let's, did we choose Cisco as the password? Yeah, we chose Cisco. So let's look at the running configuration and see what we've got here. Let's take a switch port we haven't touched yet, and let's give some descriptions to it. So let's say this switch was a WAN. We were using it for the WAN. So let's go to Interface. We configure this. Now let's say we want to go to Interface, Gigabit Ethernet. And let's say we saw G3/3. Now when we're here, let's do what we would normally do. We would hard code it. Duplex, we'd say full. I'll let you set out the duplex full. Show, run. The reason it's not letting me do this, there's another configuration command in here, locking it out. Config, let's do this. Config T, interface G3/3. We'll do a no negotiation auto. I'm gonna put an IP address on it. Let's set the speed. We'll put the speed SP. Let's set the duplex to full. So we know that speed in duplex is going to be configured. Now, let's have a description on the port. So we configure description, connection to AWS. So now we know what that port is doing. Now, when we look at this thing and we're looking through our configurations and we don't know what's going on, we can look and see if we go to that port, it didn't take it for some reason. So let's see why it didn't. Config T int D3/3 description. Link to AWS. So now let's look through our running configuration. And let's see if it shows us what's going on here. Now we know. You can see how we've selected the media type, we've selected the speed, and we've selected the duplex setting. That's how we typically set these things up. So let's walk through that. So now you can see that's realistically how we can look at these things. So now, should we connect these switches to another switch so we can start adding some switching and things like that? Let's add a switch, add an object, add a node. Let's add another switch. Save. Switch connects to switch. Oops. Let's add another switch here. Let's start the switch up. Let it come up, which is going to take a few minutes because it's these aren't the fastest devices in the world with regards to booting. No server boots up like a PC. PCs boot up fast. Servers, they've got memory to check. They've got all kinds of CPU cores to check, etc., etc. So there's lots of stuff that goes on. For example, keep that in the back of your mind. The system's almost up. It's coming up. This is exciting. I love watching stuff come up. That means we can use it. Now, I want you guys to all think about this. Will the switch and that port, Gigabit 3/3 that I say connection to AWS, will that port be up? If you think that port will be up, that port that I just put, port up in the chat box. And if you think that port that I just turned on, that Gigabit 3/3 on switch 0 on the first switch will be down, type down. Now remember, that port that I wrote the description for on switch 1, and I set the speed to 100 or 1,000 and the duplex to full, there's no cable plugged into it. So what happens to a switch port with no cable? Is it up or is it down? it's going to be down. And that's the reason why it's down, because as you can see, there's literally nothing there. So let's draw a connection between these two switches. Connected. Good job. So now let's say we take the port that was 3.3 on this one, and let's see which port we're going to use. Let's say we use 0.0 over here. So now let's think about this. Let's go to 3/3 here on this side so we can look at it. So now we can, okay, so on 3.3, show IP int brief. Now, as it turns out, GE3/3 is now up, right? Why? Because it's plugged in on the other side. It's plugged in on the other side. So now let's look at this over here, G0/0. Show IP int brief. 0.0 is up. Now, let's look at let's look at this. Are we happy with something? So if we look at the show run, are we very happy with what we see with GIG 00? So on one side, we negotiated speed 1,000, duplex full. And on the other side, we've done nothing. So we have a mismatch here, and we don't want this. So on this, we're going to go to config T. We're going to go to interface G0/0. We're going to write a description. We're going to write a description so we know what it is. Link from AWS to data center. It's any name we want. Guess what? While we're at it, we'll do a no. We'll set this. We'll do a no negotiation auto. We'll set the speed to 1,000. Set the duplex to full. Show interfaces. Okay, it's too many. Okay, so wait, speed duplex mismatch. Speed duplex mismatch. Why? Are they both hard coded, or is one auto and another's not coded? So show run interface G3/3. 3/0. What do we see? We see that this one is set to media type RJ45, speed 1,000, duplex full, no auto negotiation. And what do we see over here on this side? Show run int G0/0. Feel like this? Here's what we got going on. Okay, so we've got speed and no negotiation. These two should be working, but they're not. Something's bothering them between them. So normally you'd set them, but we've got an error here. So let's go back to this, config T. We'll go to interface, and what's probably going on is I probably misconnected them. So let's look at G3/3, G0/0, and that should work. But for some reason, it's not liking our cabling. So we go back to the other words until we'd figure this out. So we'll go to config T, we'll go to interface, G3/3, no speed 1,000. Oops, it should be 1,000. No type in negotiation auto, which won't let us do because full the duplexes. So what we have to do is it's going to tell us is we're saying no duplex full. Let's see if it lets us do it now, because that's the thing. These routers, they guide you, which is really great. Okay, negotiation auto. So now we can look at a show run int G3/3. Let's see if it took our configuration. It shows us what the configuration. Okay, then that looks good. So now on this side, we've got a negotiation problem. So let's go to config. So no negotiation. Go back to this port. Int G0/0. No negotiation. Auto. I'll say so speed. No speed. 1000. No duplex. Full. Negotiation. Auto. Now, what's going to happen now with these two ports? Are they going to fix themselves? If we configure the right ports, yes, they will be. And if we don't configure the right ports, it's not going to look at it. So show IP int brief. Let's see what we got on that port. Now it's up. Not getting any more syslog errors showing it's wrong. So what you'll see is with these devices, they tell you when they're unhealthy, and they're pretty annoying about it. Wrong, 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 wrong. So the next time you hear about an impaired network, realize there's no such thing as an impaired network. There's things that don't work right. There's a cable, there's a speed duplex, there's a routing issue, there's an IP addressing scheme. Impaired networking, it's not like routers and switches go to a bar and get drunk. I mean, it's just not what they do. Impaired networking could be anything. So now, as better architects, better engineers, you'll be able to listen to cloud providers when they say things and say, does this make sense? Or no, it doesn't make sense. Because as an architect, you need to advise your customers and you need to know you can't be brainwashed, for example. So what we can do here is we can actually start looking at a port status. So if we do show.
You're not sharing your screen.
Oh, I was a minute ago, right?
Yes, you are.
So if we were to do, for example, a show port.
Can you move that window up a little bit?
I sure can.
I feel like the Wizard of Oz.
And this may not even allow you to look at the port status anymore, because that's the thing. Oh, it's just show interfaces. Never mind. I've worked on so many Cisco devices over the years. And the first ones, they used one set of CLI. And that's because Cisco bought it from another company, the Catalyst 5000. Everything was a set, a shell. It was the most beautiful thing. Then we created iOS ones. Then we merged the iOS and the set, etc. And in the end, where we ended up was like 40 different sets of switching commands. So for a routing person like me, when we're dealing with switching, it gets pretty interesting pretty fast. So let's look at this. So let's look at a little bit. We talked about the speed. We showed you the show. So let's see if there's anything else that I want to show you while we're at it on here. So I think we're good on the tech piece for this. I'll be getting back to it for a second. Let's get back to a little more content. I want to really walk you guys through this information. So when we're on those switches and I do a show IP in brief, and it says administratively down, that means it was shut down and you have to do a no shutdown to turn it on. Then the interface says down, down, but not administratively down. Probably because your Ethernet cable was unplugged. Now, this is an iPhone speaker cable, but if you've got a layer 1 problem, it's down, down. Now, if you have what's called an up and a down, which really isn't something we typically see on LAN switches, but it's something we constantly see when working with the various clouds, things like Frame Relay, ISDN, for example. What'll happen is we'll turn it on, we'll get link light, which is layer 1, but the line protocol or the encapsulation will be wrong. Maybe you've got a wrong DELC in frame-relay, for example, or maybe you're configured for point-to-point encapsulation, but you want to use HDLC. Maybe you're running Cisco HDLC versus somebody else's HDLC. So when we're dealing with encapsulation kind of problems, that's where you're going to see up and down. Now, if you're going to see down, down, and it says error disable, that's because what happened is port security disabled it. So what kind of security are we talking about that we can do on the network? Really cool stuff. So I'm looking at Eva Doikia. Eva Doikia is in my house in Florida. She comes into my house. She plugs in her computer. She gets the internet port goes up. Eva Dyke is there, and everything is working great. Now, I'm going to pick somebody that's here. I don't know Angelo, although I've got a million relatives named Angelo. It's a wonderful name. So Angelo comes into my house. I don't know Angela. He plugs into my Ethernet port, and an alarm goes bing, bing, bing. The port shuts down, and a bunch of Navy SEALs come from upstairs to the person to say, hey, we need to talk. So that's basically something called 802.1x, which is basically MAC address authentication. Note, we lose all those good security things in the cloud. And when you see up, up, it's working and life is good. So kind of keep that in the back of your mind when we start looking at these things on our switches and routers. That's what they actually mean. So let's go look at interface. Let's play with it back for a minute. Let's get pretty deep into this tech. Let's actually look at one of our interfaces. So let's go back to, nope, not back to the server. So let's do a show interface T0/0. Now we're going to get a lot of information here. What are we going to see? We're going to see that this is a gigabyte. We can see our MAC address. Now what you see is this first part of the MAC address is called the OUI, which identifies the manufacturer of the card, and then the second half is the one that's unique to the device. Now this is the description, what we manually put in here. MTU is the maximum transmission unit, meaning this link can handle a packet of up to 1,500 bytes, no bigger. So a frame of up to 1,500 bytes. Now we can see the bandwidth in kilobits per second. We've got a delay. We've got reliability information, which we could change if we wanted to. A keep alive is there for 10 seconds. What does that mean? It's going to reach out to the switch. Are you there? The switch is going to reach out to the device. Are you there? And it's going to say, I'm here. 10 seconds later, are you there? I'm here. 10 seconds later, are you there? I'm here. 10 seconds later, are you there? No response. 10 seconds later, are you there? No response. 10 seconds later, are you there? No response. Remove the link, set it to down. Don't send any data on this down. By doing it, guess what? You won't be sending data and losing it. So that's how these ports work. Everything has a health check. So when you're dealing with DNS and a load balancer, are you there? And the server say yes. When you're dealing with a load balancer, are you there? And the servers say yes. All of this all comes from networking. This is 30, 40-year-old networking technology that we now use in the cloud every day. That's what that keep alive is, auto. So we see that we've set it auto duplex, auto speed. For whatever reason, with our virtualized environment, that's what it wants to use. ARP type, ARPA, basically the original kind. The last time we looked at the queue, now we can see what's going on. The queuing strategy on the interface, we could change it. FIFO, first in, first out. 5-minute input rate. How much data is coming in over 5 minutes, averaged out? How much data is going out over 5 minutes? Now, do we really think we're going to get good data every 5 minutes? No, because we could be peaked at 100%, and realistically speaking, at 3% the rest of the time. And we don't know, but this gives us some information. We can, 0 input errors means no hardware errors. 0 CRCs basically means there was no damage to the frames, et cetera, et cetera. Let's see what else we got over here. Realistically speaking, if we were in a hub, we would have things called collisions, and collisions would be a nightmare. So let's talk about the concept of a broadcast domain versus a collision domain, et cetera, because it's a pretty important concept, and I don't think anybody really makes it easy enough to understand. So let's walk ourselves through here. So let's look at the 3 alternatives: collision domains and broadcast domains. So let's say we were crazy enough to be using a hub.
Are you
Which we would.
sharing your screen?
If we were crazy enough to be using hub, here's what a hub is. A hub is a box with 1,000,001 ports on it. I've got a port over here, like a switch, but not a switch, and very different from the switch. So I know there's a certification provider that likes to call a hub a switch, but this is the problem with a hub versus a switch and why they're so very different from each other. let's say these are all your different computers that are plugged into a hub. Now, a hub is what's called a collision domain. Now, in this hub, currently speaking, and let's say we had 5 hubs that were strung together. We got a hub. Let's say we've got another hub. And we've got another hub. And each one of these is all plugged into each other in a hub-based network, which is the worst thing ever. We've got users here. Let's add a couple more users on the hub. I want you to really, truly understand the problem of broadcast domains versus collision domains versus and where routers and switches actually do their work. So right now, this is a hub. And let's say on the hub, who are the blue wrenches we have over here? Let's say over here, we've got Eva Doikia. She's got a blue wrench. And who else has a blue wrench today, Chris? Abigail has a blue wrench. Perfect. So let's say Abigail is over here. So we've got A-B-I. And not exactly the right spelling, but we're working here. So let's say that Abigail comes up with this great idea, and she wants to send it to her friend Eva Doikia over there in Hungary. And she decides to send data. Now, everybody over here is also a user. As it turns out, Abby wants to send data, Eva Doikia wants to send data, and all these other users send their data. So here's what happens. They're connected to a hub, which is basically shared medium. Everybody talks, and everybody sees everybody else's traffic. Now, if Abby and Eva Doikia or any one of the thousands or hundreds of people that are sitting on this hub transmitted data at the same time, we get a warning. Warning, beep, 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 beep. All data stops because the data collided. So then what happens is every one of your computers random back off. And then guess what? Abby and Joey try to transmit at the same time. And guess what? Not allowed, back off. So then randomly they all back off. And Eva Doikia sends her traffic and it gets through. Life is good. All's good. Now she's sending her traffic to Abigail. It's all getting through. And now Sam starts submitting traffic at the same time. Now Abigail's disconnected, Eva Doikia's disconnected, and Sam's disconnected. And now everybody waits and they all try and retransmit, and then 30 people try and retransmit at the same time. That's what a collision domain is, where your traffic will collide. Now, when you deal with wireless, it's all collision domains, which is why your wireless can say 50 gigs, and you're not going to get more than 500 megs, because the collisions basically give you about 10% of the capacity that you would actually get. So that's what a collision domain was. Now remember, if this turns into a switch, everything changes. So now we're in a switch. Now the things are different on the switch, and I'll show you why. Switch. And I'll show you where routers come into play. Now we've got this switch over here. This is a really good setup. Now we've got users here. So Eva Doikia wants to see a picture of Abigail's beautiful cat, Noni, and it's one of the most beautiful cats I've ever seen. So she sends a request, Eva Doikia, I'd like to see it. Now, the first frame, ARP, who has the MAC address of Abigail's computer, does get broadcast out all these ports and all these ports and out Abigail's port. Now, Abigail says, I have it. Now, all the traffic going between Abigail and Eva Doikia goes through. All these other users can be sending each other's traffic to each other. It's not a problem, because on a switch, it's not a shared medium. A switch is not half duplex where you send and receive on the same wire. It's full duplex. You send on one set of wires to receive on another set of wires. The switches don't allow unknown traffic out our ports, so the data never collides. So each port on a switch is its own collision domain. So basically, 10 hubs strung together is one collision domain. One port in a switch is its own. So by using a switch, we don't have any problems. We don't have collisions. We get the maximum throughput. Now, where do routers come in? So I'm going to show you the difference. Now, got a router over here. And this is why routers are so cool. But let's say we've got 3 VLANs over here. We've got Evo and a VLAN. And let's say we've got Chris and another VLAN. And in addition to that, we got Leo in a separate VLAN. They're all in different VLANs. Get rid of all this nonsense over here. Let's keep a couple of these. So let's keep Abigail over here. Now, while we're at it, let's say we got my buddy Alonzo. Alonzo's over here. Get rid of all these things. Now we put a router in between them. Now these are all different subnets. So the router is going to route between the subnets. So while the router is routing between the subnets, I want you to think about how much coolness we have now. So we've got this router routing between subnets. You know, this is not my prettiest architectural diagram, but it is what it is. And we've got a router routing in between subnets over here. Let's call this a router. Now let's think about how much cool stuff we can do. Alonzo and I are collaborating in a cloud engineering program. He's my good buddy. So Alonzo, oh wait, I never put me in here. Hold on, let me add me. Alonzo wants to reach me. Alonzo's in one VLAN. Now, in order to get from his VLAN to my VLAN, he has to go through a router. So Alonzo has a route to me. And because Alonzo has a route to Mike, he can reach me. Now, because it's a router, I've got a layer 3 access list that says Alonzo can reach this on my subnet. I can now say Alonzo can reach my one server. Alonzo can't reach anything. I can lock Alonzo down into port 22 coming into me on my router with an access list on the router. I can't do any of that coldness on the switch. I can then say, Leo and Chris need to talk to each other, but Chris needs access to the most sophisticated parts of our company because he's my chief operating officer, and Leo only needs to know the top 80%. So I can create a policy between Leo and Chris so that Leo gets 80% of what he needs, I get 100%, and Chris gets what he needs. So by bringing in routers, we take the broadcast domain, and every port on a router is its own broadcast domain because it's its own subnet. So in a routed network, we can grow and grow and grow because how many people can we put in a subnet? 250 to 500 max, and beyond that, it's all lost. So we can't keep creating VLANs of 10,000 users. We can create a VLAN of 200 users, a VLAN of 200 users, a VLAN of 200 users, or one user, it doesn't matter. And we can route between them. But because of the routing, that enables us to do things like access control lists and filtering and things. So we enable ourselves with routing to be able to do so many cool things. And that's the difference between a router, a switch, and a hub. So now we're going to start doing some VLANs. Chris, how long have we talked about this since the last break?
About 30 minutes.
Okay, let's take a break then. Let's cover some concepts. So Chris, hopefully you've been capturing the questions. And I will bring up StreamYard so I can see the questions, and let's answer some questions. I want everybody to have a wonderful free CCNA experience because I want everybody getting that cloud architect job or solution architect job. Why are switches named switch? Angela, we name them whatever we want. By default, they come and they say switch, so you can identify it as a switch. But realistically speaking, you should have a naming convention. Every company has their own naming convention, and you make one. But you can name it anything you want. What is the difference between a VLAN and a subnet? Tony D, each VLAN is a group of ports on a switch or switches, but each VLAN has to be in its own subnet. So the subnet, which we'll have lots of time talking about, is an IP network that's broken down into a fraction of that IP network. And we'll spend probably 2 to 3 days talking about subnetting. But understand this, that each interface on a router needs to be on a different subnet. And that means that each VLAN also needs to be on a different subnet. So we'll spend lots of time on the mathematical calculations of subnetting and definitely cover that in depth. But great question. Eva Doikia, Mike, collision domains happen when the data is transmitted at the same time. And it only affects hubs because they're half duplex. Yes, but because it's not just half duplex, they're all sharing. What is a hub? It's basically 2 wires, or it goes out, a couple wires that goes out every port. So everybody's seeing everything. So that is the reason. So yes, it's half duplex, but by nature, because all the ports can see every bit of electrons that go on the wire, that's why it's shared. So everybody's talking and everybody can see each other's traffic. But on a switch, if you're plugged into one port, I can't on another port see your traffic. So realistically speaking, and now that's really a good point. So let's talk about, wow, Ivadoike, that's a really good question. So let me bring in another slide, because I really, really like that question. So realistically speaking, if this becomes a hub, what happens is when a packet comes in, that packet literally hits every single device at the same time that's in here. So it's literally getting sent to everybody. And since it's duplex, it's half duplex, it creates this environment. But the point is the way CSMA, CD, collision detection, collision multi-avoidance networks work, and the way they were designed, is that exponential back-off strategy. And that's the way Wi-Fi works, which is why Wi-Fi's performance is so bad, and you would never use it for servers. Because when this comes in, everybody over here all sees the same thing. Now, if this becomes a switch, and we've got you over here instead of a router, and we've got me over here wanting to send you a photo of my cat Cindy, or Cindy got a hold of my phone and she sends it to you. When you get that message from Cindy, yeah, the first packet may go out, all these things, but they're full duplex, so it doesn't cause a problem. And then as soon as you respond, Cindy's just sending your traffic to you. So guess what? If you're on this port, you can't see the traffic on this port. And if you're on this port, you can't see the traffic on this port. So what do we actually have to do when we want to actually see what's going on in the network in a switched environment? We actually have to create a special kind of port. And I'm going to show you what that port looks like. We create a port, and we typically call it a SPAN port. SPAN, and I don't know why Cisco made, I'm sure it has an acronym. And what happens is the SPAN port is where we plug in a computer, and we'll call it a sniffer, and it's basically a protocol. Let's call it a protocol analyzer. That's the right term. So what happens is we can create something called the SPAN port, and what the SPAN port will do is it'll take all the traffic on all the other ports, and it'll send it out the SPAN port so you can run your network analysis tools, but you would never plug a device into there because it's like a hub. So when you're dealing with switch environments which have security, and the whole point is to make sure people can't see each other's traffic, if you need to see the traffic for analysis, you have to create another kind of thing which replicates it so your protocol analyzer can see it. So I hope I answered that question for you, Ivadoike. And then Chris, if you want to bring in the next one. If you had a layer 3 switch, you wouldn't need a router in the middle. The layer 3 switch, what happened is you still have your VLANs, and then what would happen is we would create an interface for the VLANs, which is just the router part. So yes, routers would do the same thing. And a layer 3 switch is a router. A layer 2 switch is a switch. A layer 3 switch is a router that just can combine switching and routing functions. All switches broadcast the first packet out all ports until they actually learn the port where the MAC address is, and then they send it directly to the port where the MAC address resides. So only thing that switches use all ports, and switches use MAC address tables. So they broadcast out all ports, and as soon as the person responds with the MAC address, the switch only sends it between the sender and the receiving ports. So that's what we're really talking about. Brian, we would never use a hub. I don't think you could even buy a hub for 20 reasons. The only reason I brought up the hub is one of the AWS certification providers that's very famous tells everybody that a hub and a switch are the same. And then when people get asked these questions in job interviews, they can't get hired. So that's the reason I'm talking about it. We don't use hubs. The only place where we actually use the equivalent of a hub is Wi-Fi. And the reason we're using the equivalent of hub for our Wi-Fi is we don't really have an option. We've got an access point that sits on the ceiling, and we got hundreds of computers that need to do this. And it's not like we can have a different radio frequency for every single user to keep them all separately. So that's why Wi-Fi is effectively the same as a hub, which goes back to 30, 40-year-old technology, which is Wi-Fi. So, That's why we never plug in a server over wireless. That's when we never do anything important over wireless. And that's why we hard code everything for those reasons. Good question there, Brian. You've heard the term, but what is payload? Well, okay, so you got a car. It's got a trunk or a boot based on what country it is. You stick it in the trunk, you drive the car. The stuff that's in your trunk, that's your payload. The data that's in the frame, that's the payload. So you put passengers on an airplane, 1,000 passengers, they are the payload. The payload is whatever you're transporting. Good question there, John. You can connect VLAN to VLAN, or you can connect VLAN to router, either. Good question, though. Why do you need a routing table? Well, if you got in a car and you wanted to know the destination, you'd have to know how to get there. That's what a routing table does. It's like the GPS in your car. Go straight, make a left, make a right, make a right, go left. If you don't know how to get there, you'll never get there. Routing table is your map. Chris, want to bring in the next one? Okay, how does domain name service work? Well, we will have a small DNS section that we'll cover, but realize DNS is not a network engineering thing. DNS is typically a sysadmin thing. It's typically done by your Unix people or your Linux people. But having said all that, we will discover or discuss domain name systems, and we'll go over it when we get to the section of the curriculum that does include that. So we will get to it. You can't use 1 gig base T not being full duplex. It's a laser. So, so if you're using 10 G base T, which is laser, you're going to have a send laser and you're going to have a receive laser. There's no possibility to make it not full duplex. Why do you need a broadcast domain? Well, there's no option. That's the way Ethernet was set up. So unless we want to redo Ethernet and redo all of networking, we have no choice. That's the way it works. We have a broadcast domain. Basically, everybody in a broadcast domain can see each other's broadcasts. So ARP, who has the MAC address, requires a broadcast. Hey, I have a message here. One of the Microsoft messages. That's how servers identify each other. Everything requires broadcast. So if we don't have broadcast domain, we have no networking. But that's the way the networking protocols were set up 50 years ago, and that's why we still have them. Does the term dumb hub? Not really, because hubs don't exist for 20 years now. And what is the difference between a smart switch and a dumb switch? Well, if you go to Best Buy, you can buy a switch that's not a smart switch. Every other switch in the entire world is considered a smart switch. What is the difference? If it can put VLANs on it or you can manage it, it's considered a smart switch. So there is no such thing in networking as a smart switch because there is no switch that's not smart in networking. Now, for a user in their home, you can buy a $30 device that's not considered a smart switch, but that's about it. All switches are smart switches. Now, layer 2 switches just do switching. Layer 3 switches do switching and routing, but no, none of that stuff is applicable. Unless you're dealing with the consumer space. Hubs and switches are entirely different technologies, and they can never be used to simulate each other. I would say that a hub is if you took a box and you plugged an identical wire out every single port so that when an electrical signal comes in on every single port, it goes out all ports. That's what I would say a hub is. That's why we don't use them and haven't used them for 20 years, because what happens is all your users try and talk at the same time, and then nobody is allowed to talk. So imagine a hub is like this. A hub is like going to a busy dinner table that's got 60 people in the table, and everyone's screaming all at the same time, listen to me, listen to me, or listen to me. So that's why we don't use hubs anymore. The switch is basically like this. Mike and Chris can talk. Evo and Abigail can talk. Pritapal and Agilo can talk. Elvis and Earl can talk. And they can talk to each other, and you can't hear anybody else's stuff. So that's why people use switches. That's why we stopped using hubs about 20 years ago. The only thing left of a hub is Wi-Fi, and that's why we can't use Wi-Fi for anything important. I'm sure we will spend some time talking about spanning tree and rapid spanning tree. And when we do that, we will go over spanning tree terminology and the spanning tree protocol and the spanning tree elections and the algorithms, et cetera, et cetera. But trying to explain one thing out of context. Dan, what is the typical limit of your standard home grade switches and enterprise switches? Home grade switches, they don't have much of anything. And I have no knowledge of home-based networking. People don't pay me to design, their Wi-Fi in their home. And let's be fair, I've never designed a system where I could go to Best Buy or Staples and pick up a hub or a switch to that. So I don't know anything about home networks. Now, big core switches, remember, they're going to be handling millions of routes in the routers. And a lot of those are switches, so they can store thousands of MAC addresses like nothing. Nothing. Hundreds of thousands of them too. But relatively speaking. Best way I can describe it is if you've got 1,000 people at a table talking to each other, you're going to have congestion. If you got 1 million cars on the highway at the same time, you're going to have congestion. So that's why. Router and switching configurations are very different because routers are dealing with routing and switches are dealing with switching. So switching will include things like VLANs, and routing will include things like routing protocols like BGP and OSPF. So they're going to be very different. Now, a lot of the commands will be similar because they're made by the same people, but the technology and what we're doing are very different. Okay, so let's get back. Before we get back to the content, everybody type hashtag CCNA, and then I know you're ready. Because it's kind of hard, and I know that way I know you're not sleeping while we're talking about these things. So let's talk about VLANs and making VLANs, et cetera, et cetera. So we're going to talk about VLAN concepts. We'll talk about VLAN and VLAN trunking, configuration and verification, and we'll be doing some troubleshooting of some VLANs. Excellent. I know you're awake now because of the CCNA that you're typing. So, and again, I want everybody passing the CCNA 200-301 exam, but more importantly, I want you to get hired. I want you to be capable. I want the world to come to you, and I want the world to know your name as great network administrators, network engineers, cloud architects, solutions architects, network architects. Let's have some fun. So let's realistically talking about this. What we can do is as follows: we can take our switches, switch 1 over here, switch 2, and by keeping them separate, we can have a broadcast domain. But we could take a single switch and we could chop it up. So I like using this example, and I like creating my own whiteboard stuff on the fly sometimes. Imagine this. Now we've got a switch. Switch. Here we go. Get rid of let's change the color of the text because we're going to have fun with this. Let's change the text color to black. Let's make sure there's no fill over here. So now we've got a switch. Now, a VLAN is just this. Chop this switch. We'll make this mini switch 1. And let's do this. We're going to make mini switch 2 inside of the switch. Now we're going to make mini switch 3, and then we're going to get involved and talk about what these things are. But I just want to walk you through a high-level architectural overview first. And then let's say we've got switch 4. Now in this switch, this switch, this switch, this switch, and this switch cannot talk to each other because they're all their own VLANs. That's why it's a virtual switch. This cannot talk to this, who cannot talk to this, who cannot talk to this. Now, if we had a router between them, we could route between VLAN 1 and VLAN 2 versus VLAN 2 and 3 versus 2 and 1 and 2 and 4, et cetera, et cetera. We can do that with a router, but they're all in different subnets and they can't talk to each other. We are secure and it's fun. Okay, so we're secure, life's good, things are working. Now, let's say over here, switch 1, let's say this is finance. And let's say switch 2 is accounting. And let's say switch 3 is development. And let's say switch 4 is production. Now, everything's in one switch. Wait, I need more ports. I ran out of ports on that switch. Okay, now, what could we do? We could buy another switch. Okay, now we've got another switch. Now, what if we've grown so much that I need to hire some more people for finance? I need to hire some more people for accounting. I need to hire some more developers, and I need to hire some more production servers. So now we've got 2 switches. Now we have 2 options. Switch 1 and switch 2 can't talk to each other right now. Now, we could make switch 1, VLAN 1 talk to VLAN 2 by doing this, by running a cable between VLAN 1 and VLAN 2. And then we could also run another cable from switch 1 over to here to switch 2. And then we could run a cable between this VLAN over here and this VLAN over here. And then I could run a cable from switch 4 to virtual switch 4. Everybody's talking to everybody. VLAN 1 can talk to VLAN 1 because they're in the same subnet and same VLANs. VLAN 2 can talk to VLAN 2. Great. VLAN 3, VLAN 3, VLAN 4, VLAN 4. But is there any problems here? Well, no. I've got 4 fiber optic connections and I can cross the switch. Now let's think about this with a little more complexity. Now let's think about it this way. Now let's say this is in building 1. Now let's say this switch is in building 2. Now let's say there's a kilometer between building 1 and building 2. A kilometer. Now, I'm not going to go out there and I'm not going to get my cheap little cable and plug it in. Not one bit. Why? It's not going to stretch. An Ethernet cable or copper is good, what, 100 meters? So now I got a problem. But I've got fiber buried under the ground. So I now have one piece of fiber between point A and point B. But let's say it's a powerful fiber. It's 100 gig fiber. So I've got lots of speed that I can do between buildings. 100 gig. I've got a single fiber. So now, what if I could take the information from VLAN 1, take it, somehow miraculously put it on this piece of fiber, get it back to VLAN 1, and then I could take the information from VLAN 2 on this one wire and somehow get it to VLAN 2 while not letting it see VLAN 1. And then I could take the stuff from switch 3 and I can move it to VLAN 3, and then I could take the stuff from 4 to 4. Now I've extended my VLANs and I've extended my users across buildings. And I did it with a single strand of fiber. I did it with a single connection. And what is that called? That's called trunking. What is trunking? It enables you to put multiple VLANs on a wire. And we're going to talk about it a lot. We'll talk about 802.1q at some point. We're talking about framing, but that's what a switch is. We take a switch, we chop it up, we've created our VLANs. We want to route between VLANs, we need a router. We want to connect our VLANs and our switches to switches. What are we doing? We're connecting them via something called a trunk port. What is a trunk port? It enables you to securely put multiple VLANs. So for those of you guys that are out there in the cloud computing space, and you buy a private line to whatever that point of presence is, direct connection location is, whatever you want to call it, and they run a cable to their switch, and they make you send them a VLAN. Why? They've got a trunk port going back to the AWS or the Azure network, and they're sticking your stuff on that trunk port, and they're separating you by your 802.1q VLAN tag from everybody else. That's the kind of thing we're actually talking about. So now you know. Chris, I did share the screen for that, right?
Yes, you did.
Okay, perfect. So we'll show you some more professionally drawn images that my team made, which look a little more professional than I would draw. So you can see we've got Chris and Lamin in one VLAN, and we've got Evo and me in another VLAN, and Evo and me can talk to each other, and Chris and Lamin can talk to each other, but Chris and I, or Lamin and I can't speak to each other because we don't have a router. And that gives you a pretty good environment. Again, if it's multi-switch, it's going to be the same thing. Nothing changes. You know, you've got users plugged into one switch versus another switch, and you could have a cable per VLAN, or you could have a trunk port, just like I showed you. So kind of keep that in the back of your mind. So now let's talk about what's actually going on this VLAN trunk. So let's have a little bit of fun with it. We're talking about some multi-switch configuration. Apologies. I've got too many windows open on my 3 monitors over here. It's a little bit challenging. So here's how that wire works. When the information goes from the VLAN adds this thing called the .1Q tag. And this .1Q tag puts a tag on it. So this VLAN was tagged VLAN 20. This one was tagged VLAN 10. This one was VLAN 20. This is 10. So what happens is the switch on the far end does the following. It removes the tag in places where it wants to be. So kind of keep that in the back of your mind. So let's look at a little more. Port sent, untagged, it leaves, it gets tagged. It gets sent across. So what's this kind of tag look like? Well, it looks like this. Remember everything I told you was called encapsulation, where you take your stuff and you just smack a label on it, or you smack an IP header or a TCP header, and at each stage you just put a little more stuff along the way? Same thing on VLAN trunking. What do? You take your Ethernet frame, destination, source address, remember, type, data, frame check sequence, and you slap on a tag. It's a VLAN identifier. It's a 12-bit tag. That's it. And now, when you put this VLAN tag on, the switch knows left VLAN 2, because it's got VLAN 2, received by switch 2 in VLAN 2, strip off the VLAN 2 tag, drop the packet, or I'm sorry, the frame in VLAN 2, and everybody's talking to everybody. That's what trunking is. So we'll keep that in mind. Now remember, with layer 2, VLANs can't talk to you. So I had some people drawing some Flintstones thing. You know, the Flintstones, maybe you're too young for the Flintstones, but many of us loved it. And whatever, we had these Stone Age characters with dinosaurs and cats, and we put Fred and Dino on one VLAN and Wilma and Betty on another VLAN, and they couldn't talk to each other without a router. So what will ultimately happen is, if we stuck a router here and we plugged, we took this VLAN and plugged it into one port on a router, and this VLAN plugged it into another port on the router and gave an IP address to each subnet, then guess what? We'd route between those VLANs. So we're going to show you lots of ways to route between VLANs through this program with routers, with the scary thing that I haven't seen in 20 years called router on a stick, but it's on every CCNA exam. So we'll talk about it. And then there's this, but you know, kind of keep that in the back of your mind. And when I talk about router on the stick, I want you to understand that's from the old days when routers could push a mega traffic on a $5,000 router. So, I mean, just kind of keep that in the back of your mind. You know, these are the kind of things that you're talking about. So let's talk about how to set up VLANs. So we'll configure some VLANs, we'll play with it, and we'll look at it. So let's go back to our EVE-NG server. Okay, actually help me if I get on the right window. Bear with me, everyone. Let's get on our EVE-NG server. Let's wipe the config that we have on this. So for realistically speaking, we'll wipe them all. And the reason I want to do that is I want to just play with it. So let's start this router, and once it comes up, we'll have a little fun with it. Let's bring the other one up just so the port goes up. Start this while we're at it. Let's let the one device come up. It's like Jeopardy. Or however that song went. I'm sure somebody remembers that. But the point is we're going to be here. We're going to wait for the switch to come up, and we're going to create a VLAN. And you know what? Maybe we'll put some ports in that VLAN so we can see it. router came up. You can see around the time that the operating system for this router is, it's about 5 years old, which, for me is not that complicated, or not that old. So I'm used to seeing stuff that says made in 1989, 1993, those kind of things. So when I see 2015, it feels brand new to me, even though it's a couple of years. So let's go to this router or the switch. Let's give it a nice name. This is going to drive us nuts. So let's say config T, and I don't want to see every single message. So let's do no logging console. And that way it won't drive us batty, because otherwise we're going to see 1,000,001 things going across our screen. Now let's give it a different host name, config T. Why do I keep doing all this basic stuff each time? Because at some point you guys are going to remember it. We're already there. Let's change the host name to switch 1. Okay, we changed the host name. Now let's create a VLAN. Created a VLAN by naming it. Let's name it. Name. Call it Fred's VLAN. Now it's got a name. We can find it. Now, let's add some ports to this VLAN. So let's look at the ports that are on this device. Show interfaces. We can't add ports that we don't actually have. Well, we got a whole bunch of gigabit Ethernet 3/3s. That doesn't make any sense to me. So let's just do this. Let's take gig interface. So let's make an access port versus a trunk port. So we're going to do this. We're going to type interface. We'll add some ports to a VLAN. So let's say config the terminal. And then let's say we change it to a switch port mode. Get in there. We have to get to the port. Let's get to the interface. Let's say G0 /0. And let's add a couple ports to the VLAN. All the way to G0/3. I think this will let us do this. Oh, I know what I'm doing wrong. I forgot the range command. Access means where users are going to plug in. I think that should be enough. So let's do this. Show VLAN. You can see what we did is we set up this VLAN, and you can see the ports that we placed inside of that VLAN. So now you know how we add ports to a VLAN. That's exactly what we're doing. Now, by comparison, let's you want to see what it looks like in the running configuration, so we can do a show run. Basically, look at consider the show run to be the thing that's the show running config that's really going to be helping you out constantly, because this is where you're going to see where you mess something up. So, these are one of these kind of things. Makes life a little more complicated, but, we want to make sure you're all doing great. So you can see it through the show run. No AAA new model. What's that mean? No authentication whatsoever. Not good. What is AAA? Authentication. Who are you? Authorization. What are you allowed to do? And accounting. What have you done? Well, what do we call that in the cloud? Identity and access management. Make it complicated. What is it? Who are you? What are you allowed to do? And what did you do? We networking people make life simple. Our world is so complicated, we can't afford to make things obvious. We can't afford to make things complicated. So kind of keep this in the back of your mind. That's what we're talking about here. So let's have a little more fun with these switches. Let's create another one where we're at it. Let's have fun. Let's create another VLAN. I want you guys to become an expert. So what are we going to do? We're going to go back. We'll config T. Now let's go and anybody remember the ports that we have sitting on this device? Okay, so let's say we're going to add these ports now to another VLAN. Gigabit Ethernet 1/0/123. So let's look at this. Here, what are we going to do? We're going to have fun. We're going to do let's say we say interface, Gigabit Ethernet, and let's do interface range, G, 1/0 all the way to 3. Okay, we're there. Let's make it an access port. Switch port, access. 3. I think we have to do switch port mode access. Guess what? Work now. Show VLAN. You can see it's there. You can see we've added the ports to the VLAN. Now you know, pretty basic stuff. Pretty basic stuff. So now you know basically how we're setting these things up. Now, let's talk about some trunking things. When we talk about trunking things, because we're going to talk about now how we create trunks at some point. So remember this, an access port, where you plug into the switch. Me, the user. A trunk port, switch to switch. Now, there's this concept of all this auto negotiation, auto trunking in between switches. And I kind of hate auto anything, but these switches run it. There's basically two forms of trunking that we can be talking about. We can talk about the Cisco ISL trunking, and we'll probably talk about it at some point. And that is really cool trunking stuff. But why won't we use it? It's Cisco proprietary. And even when I worked at Cisco for a decade and I was teaching Cisco engineers how to do stuff, I would never recommend any proprietary service. So what kind of tagging will I be recommending? 802.1q tagging. Why? Because it works with Cisco, Juniper, AWS, Azure, and everybody. And I never use stuff that's vendor proprietary because it's like a prison sentence. You are locked in and you can't leave. And I don't do that to anybody. So remember the concept of dynamic desirable. And what this does is it initiates negotiation messages to determine which VLANs and things are going to be in trunk. We can also go dynamic auto, which is basically where it's just going to be sit there and it's going to wait for stuff to actually do this. Keep that in the back of your mind when we start talking about trunking. So we've got an environment, for example, as I showed you, where you've got two switches. Pretty much we're going to be talking about the things in between these switches. So kind of keep that in the back of your mind. Now, there's still lots of shops that are using ISL trunking. I see it all the time, but I would never recommend it for these reasons. But like I said, I can walk into 30 or 40% of the businesses out there and we're still going to see it in use today, even though we should not. So the initial state when you set up two switches between them is going to be just switch port, not trunking. But at some point, they will negotiate in between them. So let's kind of create a trunk between two switches. Now, 99% of my career, I'm going to tell you, with a CCI number of 7417 and being Mr. BGP for most of these companies, I don't do a lot of stuff on the the switching side. Most of the stuff that I do has been, advising ISPs on their BGP, their traffic engineering, their label switching, their RSVP signaling. So that's kind of my world. So I'll go over the switching with you, but we're going to make sure the routing sections are really, really fun for you because, that's what network architects like me do after 25 years. But, we'll be working on this. So let's say we want to actually change these switches and we want to create a trunk. No big deal. We're going to go to the port. We're going to talk about it and we're going to create the trunk and it's going to be, say, desirable or not desirable. So let's say we wanted to do this. So Let's remove the G00. So let's not do this. Yes.
Make sure to share your screen if you're about to do something.
Sounds good. So let's go wipe this configuration again, just because we want to have some fun here. And it'll be easier to wipe our configuration on the EVENG node than it will be to start playing with it. Plus, it gives us a chance to just sort of play. And playing is fun. It's how we learn. We'll start it up. Of course, it'll take some time. It'll boot up. They're a little slow. So we can play the Jeopardy music if we had it in the background. Do-do-do-do. Well, while we wait. And I got to tell you, while we're waiting, I've seen organizations that have these big switch networks where they've got VLAN trunks everywhere, and they dealt with spanning tree and rapid spanning tree, which we'll talk about. I got to tell you, it's ugly. I got to tell you, for the most part, for the last 25 years, I've helped rip out all this trunking and all this layer 2 nonsense and replace it with layer 3 things for high security, higher availability, more rapid self-healing, etc. So I don't do a lot of layer 2 networks for that reason. I generally try to remove them. Now, people like them because they're simple, but you know, there's so much that goes wrong with all these broadcasts and spanning trees and rapid spanning trees. It's so much easier for me to make a nice network, turn on OSPF or intermediate systems to intermediate systems, turn on some RSVP signaling and some label switching, create some primary, explicit, and backup paths, and I can give my customer a 40 millisecond recovery around pretty much anything. So, you know, I don't see a lot of use for doing these layer 2 things, but there are times where you're working at a small company that has huge switch networks. You're at a university, huge switch networks. You're a medium-sized business that doesn't have 30 CCIEs on staff. Guess what? You know, that's kind of the concept. So keep that in the back of your mind. You will see switch stuff out there, especially in small companies. So let's go back to this. So let's P. So while we're here, let's do no logging console because I don't feel like being harassed. I'll buy this stuff. Let's set an enable password. Of course, we'll pick the world's most famous internet password, which is, guess what? Realistically speaking. Then let's say we want to go to interface. So while we're at it, let's go to interface G0/0. Let's make it a switch port, trunk port, switch port, mode, dynamic, desirable, Control Z. And what you'll see now is this is actually a trunk port that we actually set up. And you can see it now. You can see this. You can look at it. So what are you seeing? You can see that it's G0/0. You can see that it's the dynamic desirable trunk. You can see the trunking encapsulation is to negotiate, and it's auto negotiation. You can see right now that the only VLAN on the trunk is 1, because that's the only VLAN we configured in this brand new switch. We're not using private VLANs. What are private VLANs? Private VLANs are awesome. Awesome. They enable me to have 10 devices in a VLAN and not talk to each other. So think about it this way. Can't do this in the cloud, but you can in your data center. 50 servers sitting in a VLAN. Server 1 gets infected with malware, but it's in a private VLAN, and server 1 can't talk to server 2 in the same VLAN. Security. Can't do that on a cloud, but you know, when we know the cloud, we know we have less security, and we accept less security in the cloud, and we use other things for security in the cloud. But we just know these things. So keep that in the back of your mind. Now we've got a little bit of concept of what we've actually done with regards to creating trunk ports. So, you know, we're there, we're having fun, we're dealing with trunking. Now, we should probably show you what this looks like. Typically speaking, wrong one, if we're dealing with a voice over IP environment, what do? We typically create a trunk port from the switch to the user's desk. So what happens is the phone has a switch in it. And the phone will have one VLAN, which goes to the switch, and it'll have another VLAN for your data. And why do you do this? you separate your voice traffic over your data traffic. So let's think about this. If you have an emergency and you try and place a phone call and you can't make that call, it's a problem, right? I mean, a huge problem. So by comparison, let's pretend, for example, that what you really needed to do was as follows. You wanted to prioritize the voice traffic. So if you had a worm or a virus, your voice, you could call tech support. Hey, it's Mike. My systems are down. Now, if you have voice over IP and you don't have QoS enabled, you can't. So typically speaking, we segregate our voice traffic from our data traffic. We stick them on different VLANs, and that's the reason. So when we're dealing with voice over IP environments, just to walk you through what it's going to look like, we got our switch in the wiring closet. Plugs into the phone, which has got it switched. Now, this is plugged into the network on its own one VLAN, and this is trunked on another VLAN. So that's kind of what we're talking about. So let's play with this a little more. So we've got a switch. Got two VLANs. VLAN 1 voice, VLAN 2 data. No big deal, no big deal. All good. So how would we look into this environment? So if we wanted to do this, if we wanted to deal with a phone, for example, how would we create it? How would we set up this environment to work with voice over IP? Well, we'd do it like over here. So we'd find, what we'd have to do is first create some VLAN. So let's create a VLAN. So let's create a VLAN. Hold on. Well, let's go to VLAN 11, for example, and let's pop some interfaces in here. All right, let's look at the show interfaces on this before I do this and show. Anybody remember which port we created as a trunk port? If not, well, let's go look at the running configuration to make sure we remember. See, I don't see where we configured it. So let's make sure I just want to see what we put in here. Okay, so we've configured gigabit 00 to be the trunk. So let's say we want to take all of these things, the gigabit 01/3, etc. That line card. Let's create a different trunk. So configure another one. We'll go config T. We'll do this VLAN 11. Here, what we'll say is interface. Okay, never mind. Let me get back out of this. So we'll say interface range G1/0 to 3. Switchboard mode access. And then under here, we could do switch port access VLAN 10. Let's say we're going to create a VLAN 11 for our users. And that's how we would create a voice and a data VLAN on a switch. Just to kind of keep that in the back of your mind. And then what we can do is we can actually look at our interface. So interfaces, G0/0 switch port. It's going to show us. It's going to show us that it's a trunk port that we set up, which VLANs are enabled, etc., etc., etc. So kind of keep that in the back of your mind. We can do show interfaces trunk. You can see what you're trunking, etc., etc. And we could get a little more there. We could show interfaces. We could do G0/0. I think we set that up as a trunk port as well. And we could see exactly what we set up there. So, that's what we're doing. It's giving you the position to be able to look and see what's going on. Done lots and lots of voice networks. And when I started doing voice networks, it was interesting. I started doing voice networks to cut the cost between phone calls between, say, New York and London, or New York and Delhi, or San Jose and Bangalore. That's what it started with. What did it turn into? Expert networks, SIP presence, the ability to create environments to get who you wanted when you need them, and it became really, really cool. And when voice over IP became unified communications, wow, that's when we could really use this to basically show our customers so many things. Let's walk through a couple more commands while we're at it, and then we'll take some questions. So let's look at the show VLANs. Show VLANs, brief, walk you through it. You can see the VLANs, give you some concepts. Now you kind of understand the concept of a VLAN. We've got VLANs that are here. So we look at these VLANs, so we can make sure the VLANs are active. If not, we would do a no shutdown on them. And we could shut down a VLAN we wanted if we wanted. So let's go to, at least we used to be able to. So big T, interface, or we should say VLAN 10. Should be able to shut it down. At least we used to be able to. Now, if we do this the same question, show VLAN brief, notice that we shut it down. So I hope that makes sense. The next section, I hate it. It is spanning tree. I think spanning tree is the most ugly protocol in the world. I have 25 years experience of getting rid of spanning tree with layer 3 links. So I think we all know exactly my level of happiness with regards to spanning tree, but we need to know about it, and we need to take some questions first. So everyone, as part of your Cisco Certified Network Associate class, your CCNA 200-301, free CCNA training 200-300-1, day 2, let's bring in some questions right now. So Chris, bear with me for a second to pull up StreamYard so I can see the questions, and I look forward to answering some questions. Can you have the same VLAN and 2 switches? Absolutely. That's the whole point of all this trunking that we're talking about, to have the same VLAN and 2 switches. Absolutely. Can I clarify, Ivadike, can I clarify against layer 2 security and layer 3? Absolutely. So at layer 2, we can add QoS to the port, meaning we can determine that we send critical data over non-critical. Let me tell you about security. Having QoS attached to your port, which we can do at layer 2 and layer 3, huge thing. At layer 2, we can do something called 802.1x authentication, which basically means if you don't have the right MAC address, you're shut off. At layer 2, we can have a MAC address access control list that says your MAC address can talk to my MAC address, but nobody else's MAC address. We can do that in the same switch. Now, when we get to layer 3, we have firewalls, stateful firewalls. We have intrusion detection systems that can look for things that are going wrong. We have layer 3 access lists. We have host-based firewalls. At layer 3, we can do a lot. So the key is maximize what you can do at layer 2 and maximize what you can do at layer 3 and maximize what you're filtering at layer 4 and maximize what you're doing at layer 7 on your next generation firewalls with your intrusion detection. So different levels, different things you do, but really, really good question. Oh, I should ask you, if you're having a good time, hit the like button, subscribe to the channel. Please tell others. We have free AWS certification materials on our channel, free AWS Solution Architect Associate, free AWS Advanced Networking, which is like an intro to networking. And then, of course, we have the free CCNA. John Clark, is 802.trunking the same as VLAN tagging? Well, the trunk enables you to put multiple VLANs on a single wire. VLAN tagging is what enables you to put multiple VLANs on a single wire and keep them logically separated. So VLAN trunking is the ability to connect 2 switches. The tagging is what enables you to keep your traffic separate on them, but very similar Good question there. Great one, actually. Chris, if you want to bring in the next one. Explain it, SD-WAN. Ronald Nazo, SD-WAN is a concept way, way, way outside of the CCNA thing. But let me tell you this. Typically, in normal environments, routers have a control plane. OSPF, BGP, intermediate systems to intermediate systems. Label switching, tag switching, RSVP signaling. That's the control plane. And that resides on the routers. And we also have a forwarding plane on the routers, which is the forwarding. So with SD-WAN, what makes it special is instead of using the routers to determine the best path through the network, we separate the control plane onto something else that's smarter and more application aware. And then it can tell the routers how to forward traffic through the internet with the lowest latency possible. So kind of keep that in the back of your mind. Great concept. I will bring in someday. I know some people that have started some of the fanciest and best SD-WAN companies. We've been personal friends with some of the CEOs from some of the companies that have some of the best solutions. So, and some of the founders of these companies. So, kind of keep that in the back of your mind. That's what it is, but way beyond the scope of this, kind of beyond the scope of the CCNP course as well. So not really related to this content by any stretch of the imagination. What are some features that you can do in a database that you can't do in a cloud? You're talking databases, we're talking networking, Ronald, so that's not even close to related to this, so we've got to keep it somewhat related to actual networking. What does VLAN trunking protocol have to do with VLANs? It enables you to connect two switches and determine which VLANs you're going to pop on that wire in between them. Chris, you can go to the next one. How is a VLAN implemented in the data center, Ronald? Exactly the way we just did it right now. I've never heard of anything called VLANing. Then again, I've been in networking for 25 years, and I really only know the terms that are used by the world's greatest internet service providers, as well as the biggest banks, the biggest healthcare systems. I don't make up terms. I don't use acronyms. I don't make up fancy words, and I don't use buzzwords. So if I'm going to create a virtual LAN, I'm going to create a virtual LAN. If I'm going to create a trunk port between two switches, I'm going to use a trunk port. And people know trunking. Why? Because we're dealing with phone switches to phone switches, it's trunking. If we're dealing with switch to switches, and it's the standard industry term that's been used for about 30 to 40 years, as is the VLAN. I don't know about any kind of cool things that people make up on the job. I only know the official terminology, and I only communicate using official terminology. How do you get hosts to communicate on different VLANs? You can't. VLAN 1 is always going to be separated from VLAN 2 versus VLAN 3. The only way you can get them to communicate is with a router. And that's why organizations make VLANs, because VLANs can't talk to each other without a router, which enables you to put a router between them like a firewall and literally firewall off access control list of who can talk to whom. Massive security. That's why we do it. Good question. Frank, in normal environments, which is a better choice? Routers or multiple protocol switches? So it depends on what you're doing. If you're connecting to if you're connecting to the internet, you might want to use just a switch, but just a router. Why? It's going to be cheap. Well, it may or may not be cheaper, but the point is if you only need 4 ports, use a router. If you need 100 ports and routing, then you use a layer 3 switch. So realistically, it pertains to the speed. So Frank, as a general rule, routers are slow and switches are fast. And why? Most routers work on the following, except for big routers or switches. Packet comes in, it hits the CPU. The CPU says, yeah, go out this port, go out this port, go out this port. But when you hit this CPU, you're using software. What do we know about software? It's pathetically slow. What do we know about hardware? It's real fast. So you want to mine Bitcoin? You can use your CPU. And I promise you, you'll spend $1 a day on electric and you'll earn 30 cents a day back. Not a good use of your time. You could mine it on the GPU. And guess what? You'll spend $3 a day for your electric and you'll earn $1.50 back if you're lucky. Or you could buy an ASIC, an application-specific internet circuit, that can do the equivalent of 1,000 CPUs. Will cost you $2 a day in electric and generate 30 bucks a day return on investment. Why? Because the first thing was a CPU, which is designed to do anything. The second was it has a GPU, which is optimized to do certain tests. And the third is an application-specific internet circuit that does things legendary fast. So when we get into a switch, what do? We send the first packet to the CPU, and we send the next packet to an ASIC or a fully programmable ASIC. So that flow is in hardware. So when you need speed, we're using layer 3 switches. Or we're using core internet routers that have application-specific integrated circuits, fully programmable ASICs, and there. So now you know, software slow, hardware fast. Generally speaking, routers for connections of remote locations. Core routing, we're using layer 3 switches, which are high performance, et cetera, et cetera. Will I be talking about BGP in the CCNA? BGP is not covered in the CCNA. BGP is barely covered in the CCNP. And truth be told, I don't even think in the CCIE they cover BGP in anywhere close to the amount of depth. Because, well, I learned BGP for the CCIE, but when I took it, it was a 2-day test, and it was really challenging as opposed to today's easy CCIE, which is just a single-day test. But, you know, it's not covered there. Will I be talking about BGP? Yeah. We'll do a BGP 3 or 4 hour workshop on this channel, potentially as part of this boot camp to teach BGP for cloud. Yes, absolutely. But it's not part of the CCNA. But we might do it anyway. The alternative to trunking in a real environment is trunking. That's why we use trunking. That's what we use in a production environment. We have for the last 30 to 40 years, and we'll continue to do so. So no, there's not an alternative, unless you choose to use a layer 3 link. Could you run DNS and DHCP on a domain controller? You sure could, but reality is, I don't know of any business that's truly running DNS for their organizations or DHCP on domain controllers. Now, I know lots of people using it internally, but externally, people are buying DNS from F5, where they're using a DNS provider. They're not doing any. Windows servers are basically calendaring, Exchange, and small businesses. VLANs in clouds, do you have virtual? You don't have virtual switches, but you've got virtual routers in the cloud, and you have to run a VLAN to the cloud, so there's no way you can deal with the cloud if you don't know switching and routing. And that's where most people try and go wrong in the cloud. What is Cisco 8500 a company is worth writing off worth the experience? Look, let's face it. Any router is the same. The Cisco iOS is identical on anything. So what my advice is to learn, go buy yourself the cheapest routers you can find from Cisco. It doesn't matter. Or buy the iOS and buy yourself a simulator. Nobody cares if you say, I worked on this Cisco router versus this Cisco router. It's like saying, I speak Greek in the house, or I speak Greek in the house. Who cares? It's the same language. So if you know a language, great. I happen to speak Greek. I used to speak Spanish, but I don't anymore because I don't use it every day, and I lost 90% of it. So if I find somebody to talk to me enough Spanish, I'll be speaking Spanish again. But no, that's the key. Spade is a spade, ace is an ace, and there's no other way around it. Chris, if you want to have the next one. Do you think we'll ever fully adopt IPv6? You know, I've been working in networking for 30 years or 25 years. And to me, IPv6 is cell phones right now, but we will be on IPv6 within a decade, I'm pretty sure, for pretty much everything. We just ran out of IP addresses and we're too digitally enabled right now. Any more, Chris?
So normally I don't put this up here, but it's the first one we've gotten about our program, so I'll let you answer it.
Let's answer it. 7 Series Beamer. When does the next cloud batch for your cloud architect program start? It starts right now. So 7 Series Beamer, let me kind of describe the way we teach people. So before I went into networking, I used to practice medicine. And you know what I've done for 20 plus years of my life? I've practiced martial arts. And here's the thing. I don't have a day where we start for the following reasons. I welcome everyone on day one. So my students sign up, and the 500 hours of videos in my training program are all self-paced. The labs in my program, whether somebody's setting up a firewall, whether somebody's setting up server virtualization, building containers, or whether one of my students is building their own cloud. And I mean it, my students build their own cloud. That's all in their own time. It doesn't matter. Now, my live classes, which we have 3 classes per week, which we record because not everybody can attend every class, that's different. So in our classes, we have people from all kinds of backgrounds. So as it stands right now in my class, I've got about 30 people that are ready to graduate in the next month. What do I mean graduate? I mean hired. So certification is nothing. I can get somebody certified in a weekend, but it takes us 500 hours to get somebody hired of training. So we have live classes, which we run 3 times per week, 2 hours, 3 times per week, starting in next month. Now we typically do 2 3-hour classes. And what we happen is in the class, we've got some senior people. So the senior people are designing our cloud architectures. They're building the BGP architecture. They're setting up the addressing plan. They're setting up the servers, the containers, the firewalls, etc. The senior students lead the class. Well, I mean, I'm the leader of the class, but they lead the architectural design. The medium students help out the senior students, and the brand new students, they just observe. They pay attention, they listen. A couple of weeks later, those 30 senior people are hired. They're now working as cloud architects. They're all happy. The medium students take the senior students role, and those junior students that have been here watching around, they take the medium roles, and the new students come in, and they're there, and they're observing and learning. This is the same way you train physicians. It's the same way you train martial artists, and that's why they're so good at what they do. So that way you've got a collaborative environment. And that way where you've got Iwadokia, who's over there in Hungary, and Abigail that's over there in North Carolina, they're working together. They're building clouds together. They're talking together. They're working on presentation together. And my students work together. So that's that. The schedule is as follows, standing right now. You have Tuesday from 9 a.m. to 12 p.m. Eastern time, which as it turns out equals 2 p.m. on Tuesdays, UK time. 9 a.m. is 2 p.m. UK time. And our Friday classes, as it stands right now, are noon Eastern time, which is 5 p.m. UK time. We've chosen those times because they work for the US, the UK, and India for the most part, all of North America and all of South America, and Europe, which is where the majority of people are, is Europe, Africa, India, the US, the UK, and Canada. So let's get back to the content and type CCNA if you're here, you're awake, alert, and oriented. Okay, when I see a bunch more CCNAs, I know you guys are awake, alert, and oriented. So CCNA for me, everybody. Marjan, awesome. Leo, Nikhil, Mr. Gee, Hasman, Caroline, Leo, fantastic. Eva Doike, I love the cloud in the background. Dan Aguilo, Alexandros, Kalispera, CJ, Emmanuel. Fantastic. I know you guys are here. I know you guys are awake. I just want to know that you can hear and see things that are going on because I want you all to have the best career. But in order to do that, I need to know you're awake. It's not always the easiest thing to do. Abu Malik, good to see you. Hope everything's all right. I haven't seen you in a long time. So bear with me. We'll get back to the content. And now we're going to talk about my absolute least favorite topic in the world called spanning trees. So bear with me, everybody. This is not my big area. My area is routing and subnet design and architectural traffic engineering and things like that, and IP multicast video. But we have to talk about spanning tree. So I will not go to my bias of ripping out layer 2 networks and replacing them with layer 3 networks. We're going to talk about spanning tree right now. So we'll talk about spanning tree and rapid spanning tree. We're going to get relatively detailed in spanning tree, and then we'll talk about some spanning tree concepts. Okay, so remember when I created this document earlier, Chris, remember this is slide 174. I want to go back to this picture before we go there. We go back to this architecture that I designed with the broadcast storm because I really want to walk everybody through that. That's why I redrew that picture. Okay, wow, I really drew this back a long time. Okay, so let's Let's go back to this picture. On this picture, I want everybody to look at it. Remember, I've got this environment. Eva Doikia wants to send a message to my beautiful cat, Cindy. They like each other. They're friends. So Eva Doikia has a picture of a beautiful tuna. So she wants to send a picture. So she's on this layer 2 network, not a layer 3 network. So she does this ARP, who has the MAC address for this. And the question comes into switch 4. It gets sent out this port. It gets sent to switch 2. It gets sent to switch 3. It gets sent to switch 1. Switch 3 sends it to switch 1. Switch 1 sends it to switch 3. We got traffic circling, globing. Whoa, goes around, goes around, goes around. The switches re-forward it. They go back in both directions. Broadcast, broadcast, broadcast. The whole network is filled up. Our 100 gig link is filled up because of one broadcast. And that's called a broadcast storm because the network keeps routing these. Remember, there's no routers. There's no time to live. So there's nothing that degrades the packets and makes them die. The frames keep going on around and around and around and around and around. You fill up your network and everything breaks down. So we have to block one of these links. And if we block one of these links, look, the problem is solved instantly. Now Cindy sends a photo to Eva Doikia, and it's a photo and it has a question and it says, "Bring me salmon, please." And Eva Doikia sends a message back that says, "Cindy, guess what? I'm going to go to Alaska. I'm going to bring you some salmon, but will you let me rub your belly for an hour, pet your head, and play with your ears?" And Cindy says, "Yes." So now Evo sends it, and what happens? The unknown frame goes out this port, it 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 goes out this port, and it gets to Cindy. So Cindy responds, the switch has learned that this is the best path. Now what happened? It never got sent back because this port was blocked. And that's what Spanning Tree will do. Spanning Tree will dynamically block and unblock ports so we don't loop our data around. So the next time Cindy wants to reach out to her really good friend Evo and send her a picture of a salmon with the hope of getting the salmon back, or the next time Evo wants to see a picture of Cindy and she sends her a message over the network, we don't have loops. Our network doesn't go down. Now my cat Cindy is an expert at breaking networks. She's good at chewing Ethernet cables. She's good at using her paw to power off servers. She's incredibly good at helping me type good spelling by walking on my keyboard. And she knows how to use her teeth to unplug servers. She's good at this. She unplugs switches, and occasionally she gets her fur in my firewall. So she is a great network troubleshooter, but now we don't want broadcast storms. That's another problem that we don't want to add to the list of problems that we have. Broadcast storms. And let me tell you, I've seen broadcast storms a long time ago, and they are real bad. And they are nothing fun to constrain or deal with, and you don't want to be dealing with it. So either use layer 3 or, now we'll go back to this. So Spanning Tree, realistically speaking, is a redundancy protection. So without something like Spanning Tree or Rapid Spanning Tree, as you can see, we just have broadcast storms. So what happens when you enable Spanning Tree or Rapid Spanning Tree, some of the ports on certain switches will be blocked. And the whole point is that loop avoidance strategy. So what happens is it's going to prevent loops by blocking ports. So keep that in the back of your mind. Spanning Tree, Rapid Spanning Tree, prevent looping frames by adding an additional check on the interface before the switch sends the traffic. So if the port is in a forwarding state, it'll forward the traffic. If the port is in a blocking state, it's not used. So no different than if I've got 2 links and I rip out a link, it's not usable. Plug the link back in and it worked. But this is dynamic. This happens automatically, as they like to say in this. It's part of the protocol. It's part of the algorithm. So what is a broadcast storm? The forwarding of a frame repeatedly, consuming up the whole link or most of it. It creates MAC address instability because what happens is all these switches start forwarding it out all ports and they start getting response on all ports. The switches don't even know where to send the data. They get confused. In routing, that's called a routing loop, but in switching, it's called MAC address table. And the fact is we've got multiple stuff being sent from all angles at all times, and it is ugly. So I'll walk you through another example. We've got this guy over here. This is Chris. Chris desires to send a message to, let's say, Lemon. So Chris's message goes, and it goes to this switch, which gets forwarded to this switch, back 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 to this switch, and it becomes real ugly, and there is your network. So we don't want that. So what is spanning tree going to do? It's going to block one of those links temporarily. And if another link goes away, it's going to unblock it automatically. So we're going to make sure at all times, we're up. And when we've got a problem, no big deal. We've got the self-healing capabilities of the network. So think about it this way. Interfaces in the forwarding state, forward, normally. In a blocking state, no frames are forwarded except spanning tree, which is control plane messages will be sent. The bridge protocol data units, as they called it, going back and forth. So keep that in the back of your mind. So what does it look like? How does spanning tree block the loop? So it blocks the loop in the following manner. So bear with me a second. Let's go back into the same diagram over here. Bear with me, it's a lot of stuff to go back and forth with these kinds of environments. So let's take this over here. So let's go to here. So now you can see we've enabled spanning tree. And what's ultimately going to occur here is Chris sends the frame to switch 3. Okay? And as Chris sends the frame to switch 3 forwards the frame only to switch 1, but not switch 2. Why? Because it's in a blocking state. And therefore, switch 2 will flood the frame out its ports at fast Ethernet 0/12 and gigabit Ethernet 0/0. And then switch 3 will physically receive the frame, but it's going to ignore it from any place else. So that's what's going on. So if we were at layer 3, we would have a time to live, but we're at layer 2, so a time to live doesn't make sense, doesn't exist. So that's why we have to do this stuff, or else our traffic will go on forever. So how does spanning tree work? This is the ugliness of it. So spanning tree basically uses 3 criteria to choose whether to put an interface in forwarding or blocking. The first thing that happens is that whether we're dealing with spanning tree or rapid spanning tree, there's an election of something called a root bridge. Root, main, root, privileged access, root, king, whatever you want to call it. So spanning tree will enable and elect a root switch. Now, spanning tree will put all interfaces on the root switch into a forwarding state. Spanning tree will put all things on that state into a forwarding state. Now, each non-root switch will consider one of its ports to have the least administrative cost between itself and the root port. The least administrative port cost. That cost is considered the switch port's root cost. So I'm going to say this again. Each non-root switch considers one of its ports to have the least administrative cost between itself and the root switch. That cost is called the switch root's cost. Now, spanning tree or rapid spanning tree will place the port that is part of the least root cost path, and that will be placed in forwarding. So, root bridge, root switch, everything forwards. All non-root switches will look at the port that has the lowest administrative cost to the root switch. That's called the switch's root cost. Now, spanning tree or rapid spanning tree will place that part with the lowest path cost, and that will call it the root part, and that will always be in forwarding state. Now, you can have many switches that are going to attach to the same Ethernet segment, but due to the fact that the links connect 2 devices, a link that would have at most 2 switches. So with 2 switches on the link, the switch with the lowest root cost compared to the other switches in the same class is placed in forwarding. So we're picking the most optimal ports to the root switch. They're placed in forwarding. So the switch becomes the designated switch, and the switch's interface attached to that segment is called the designated port. So, well, I'm not Mr. Spanning Tree. It's pretty simple. You got your root bridge. You got your ports on the way to the root bridge that are the lowest cost to that root bridge or root switch. Guess what? Those are called root ports and placed in forwarding. We also have the concept of a designated port. And now you know the switch is the designated switch, and that switch's interface attached to the segment is called the designated port. So we'll talk a little bit more about this. So in spanning tree, what's going to make a port forward or block? If it's the root switch, every port forwards. If it's the non-root switch's root port, the one that's closest to the root switch, everybody forwards. If we're dealing with a LAN port or user access port, guess what? The designated ports, which are forwarding the things, are also forwarding. So any other port that is not a designated port, a root port, or attached to this designated root switch will be blocking. And that's how it's going to work. So thinking about that, let's talk about this whole election. Here's how it works. So we have the spanning tree, rapid spanning tree, bridge ID. Now this is an 8-byte unique value to each switch. The bridge ID consists of a 2-byte priority field and a 6-byte system identifier. That's part of the 8 bytes. With the system ID being a universal address or the hard-coded MAC address into the switch. So using a burned-in MAC address ensures that the switch identifiers will be unique. Why? Every MAC address in the world is unique. So they have the standard OEY, or the first part of the MAC address, and the second half, and that's the unique part. So doing it, it's always going to be unique. So when spanning trees has these messages that sends between things, they're called bridge protocol data units. I didn't make up the term. Bridge protocol data units, BPDUs, and they're also called configuration BPDUs, and this is where the switches exchange information with each other. Now, the most common bridge protocol data unit is the hello, which basically says, hey, I'm here, and tells you things about the switch's identifiers like its bridge ID. And by using its own bridge ID or listing its own bridge ID, switches can tell who sent the hello, I'm here, hello, I'm here, hello, I'm here. So let's talk about some key information that's in the bridge protocol data unit. Well, it tells you the root bridge. It says this is the leader. Then what else does it tell? It sends the sender's bridge ID. Hey, I sent the hello. What's my ID? My name's Mike. I'm Mike. I'm introducing myself to you. That's the sender's bridge ID. Now, what is the root cost? The spanning tree root cost is the cost that it takes via metric to get to that root switch. And then, of course, there's timers. You can play with these timers at your own risk. Hello timers, max age timers, forwarding timers. Again, play with them at your own risk. Why do people do timers? Because spanning tree is pathetically slow. And people didn't want to wait 30, 40, 50 seconds, so they started tuning timers. And when you tune timers, you break things. So try not to tune timers unless you have that choice. So keep that in the back of your mind. So how does this root switch election occur? Well, there's a logic, but it's kind of ugly. So the re-switch occurs by the device that has the lowest numeric IP ID. So the lowest MAC address. So, but it's really the lowest numeric value for bridge ID. So because the bridge ID starts with a priority, essentially the key is set the priority. So determine your architecture and plan your root bridge. So give it the lowest priority, and then it's the root bridge. Now, if you didn't set the priority, it's the lowest MAC address. So you have two switches with equal priorities. Whichever one has the lowest MAC address wins the election. Again, I didn't make up this protocol, but it's there. So realistically speaking, so how's this election process work? The process begins with all switches claiming to be the root to sound out hello messages, hello, 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 hello. And then what happens is if a switch hears a hello message that's better, the switch will say, hey, wait, new president, new root switch, we all migrate over. So kind of keep that in the back of your mind. The hellos that we're talking about, these bridge identifiers, they're going to identify themselves. So when the hello is sent by something that's better, it becomes the new root. So effectively what happens is everybody agrees with the switch that has the lowest bridge ID and everybody supports it. So do not leave this up to chance. Do not leave this up to chance. If you do, you're going to find out that some little mini switch in a wiring closet is the leader. You don't want this. You want your big, powerful, robust, multiple control modules, multiple power supplies, and multiple circuits being your root bridge. You want to know what's your most powerful switch. So manually do this. How do you manually do it? Lowest priority, and you're good to go. This is one of those things that you tune them. So let's talk about the election process. Let's walk through an election process example. I'll walk you through one. Bear with me 1 second. So let's now take this. So now what's really occurring? Let me share this with you so you can see it. Now what's really coming up? So switch 1 has advertised itself as the root, as have switch 2 and switch 3. So that's kind of what's realistically going on. So realistically speaking, switch 2 believes it's better than switch 1. So switch 2 now starts forwarding. At this point, what you see is switch 1 is saying, hello, I'm root. And switch 2 agrees that switch 1, hello, is better. And then it says, switch 1 is root. Now switch 3 is still claiming to be root, but it begins sending its own. And wait, switch 3 has a lower bridge identifier. So guess what? Now switch 3 becomes root. So that's the key. Manually pick your switch. Make the one that you want to be root and set the root priority, or set the priority of that to the lowest number, and then you're going to be, guess what? That becomes the root bridge. So manually do this kind of stuff. Give you another example. In this particular situation, switch 1 has a lower bridge ID than switch 3. So switch 1 wins. But generally speaking, I don't like to leave things up to chance. I like to be careful with what I do. So now let's talk about it. So we know lowest bridge ID, lowest priority. That's what we're setting. But what about the ports on these switches? So the second part of the spanning tree, rapid spanning tree election process is when each non-root switch has to choose its root port, which is the port that is closest to the situation, to the root bridge. So which interface has the lowest cost via spanning tree to the root bridge? That's your root port. So how do we calculate it? What switches do is they take their interfaces, the local ones, and add that to the root cost listed in every hello message they see. So they get these bridge protocol data units, which send information, their MAC address, for example, et cetera. These are kind of those things that are coming in. So, each interface is going to send it, and then the interfaces know their cost, so they're just going to add their cost. So what happens is the spanning tree, rapid spanning tree cost is a numeric value assigned to each interface per VLAN, and the switches will look for each neighbor's root cost as the hello. So ugly way to say this, you take your primary bridge, the ports closest to the primary bridge are the root ports. Get rid of all that complexity, but that's the way they describe it. So, kind of configure for this. So if we were here, for example, all that we need to talk about is as follows. We've got this port advertising its cost. We know this link's cost, and we know this link's cost. So which is the most expensive to the root? Well, this link is 5, this link is 4. So lock this port. 4, well, so, figure actually, in this case, what would the cost be? Would probably block this because this total cost is 8 versus this total cost is 5. But as a rule, if everything was equal, block the one with the lowest cost. So now you kind of have an idea for the way these elections are actually occurring. So now let's talk about the designated port. So for the designated port, and again, I'm really sorry, this spanning tree is the ugliest content in the entire CCNA curriculum. And quite frankly, I actually think the spanning tree is the ugliest content in the Cisco Certified Internet Expert curriculum too. So the last step is spanning tree or rapid spanning tree, choosing the designated port. Now remember, the designated port on each LAN segment is a switch port that advertises the lowest cost hello. So the switch with the lowest cost to reach the root bridge among all the switches becomes the designated port on that section. And if the advertising toss tie, guess what? You pick the pass with the lowest bridge ID, again, lowest MAC address. So all designated ports are forwarding, so keep that in your mind. So all root ports are forwarding, all designated ports are forwarding. So kind of keep that in the back of your mind. So how do we influence spanning tree? Well, remember, spanning tree, rapid spanning tree works on all Cisco devices by default, but spanning tree and rapid spanning tree will work on extreme network switches. They will work on Juniper switches. They'll work on any switches because guess what? There's a standards-based protocol. So they're all going to work this way. By default, switches have a default bridge ID based upon a default priority value. So set the priority, lowest one. It's root switch. Now, switch interfaces basically come, realistically speaking, the cost is based upon the speed of the interface. So 100 gigabit is faster than 10 gigabit, which is faster than 1 gigabit, which is faster than 100 megabit, which is faster than 10. Now, all these routers have a reference bandwidth, and you may need to change them because they were designed not really to start looking at gigabit and 10 gigabit and 100 gigabit because, these protocols were invented way before then. So we have to do some tuning periodically with our routing and switching protocols. But with regards to this, just keep that in the back of your mind. So it's very common that you're going to have a network engineer that's going to want to change spanning tree, rapid spanning tree settings, and you're going to do that. So it's really about, determining who your root bridge is, changing bridge identifiers, so you can basically change the port cost to favor this link versus another link, because you don't want this stuff working itself out for you, because again, it'll pick some bridge in a wiring closet, and you're going to be sending all of your corporation's data through the wrong switch, and everything will fall apart. So kind of keep that in the back of your mind. So what are the default costs as it stands right now? 10 megabit, the default cost used to be 100. Now the cost after 2004 is 2 million because it's so slow. 100 megabit link right now has got a cost of 19. Used to have a cost of 19 when I started networking. And now it's got a cost of 200,000. A gigabit link used to have a cost of 4. Now it's got a cost of 20,000 because it's considered slow in today's world. A 10 gigabit link used to have a cost of 2, but now it's got a cost of 2,000. In the old days, we had nothing for 100 gigabit links, but now the cost for that is 200. And for a terabyte per second links, the cost is 20. So we have to adapt to all this rapid stuff coming out there. So let's talk about spanning tree when the network is stable. So root bridge has been elected, root ports are into forwarding, designated ports are forwarding, and everything else is out there and blocking, and life's good. So it's stable. So every 2 seconds, I'm here, I'm the root bridge. And then every 2 seconds, the non-root bridges forward those out of all designated ports. So all the devices get to see, hey, I'm here, I'm the root bridge, I'm alive, I'm awake, I'm alert, I'm oriented, kind of like a health check. Like me asking you to type hashtag CCNA so that I knew that you were there at the time. It's a health check. I knew you were awake. Say I'm a routing and switching guy. I do health checks for everything. Health checks with load balancers, health checks with DNS. I just do health checks everywhere. I'm a routing guy. We routing people do health checks for everything. So that's where we create self-healing, high availability, high performance networks. So each non-root switch will forward the lows. Now, each switch will set the root cost based upon the calculated cost, but you can also see the calculated cost to the source. Now, assuming that the hold timer is the hold timer is the same, and we didn't tune it, and I don't recommend you tune it, each switch will send those messages every 2 seconds. And if a switch stops saying hellos, hello, are you there? Hello, are you there? Hello, are you there? Or it gets a hello and stops hearing it and doesn't get the hellos, it knows something's wrong. Or what if the switch receives different details in these hellos, something that shows stuff that it's different? Guess what? We got a problem, a big problem. So again, when the switches stop hearing hellos, they know recalculate, 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 kind of like your GPS. When you hit a detour, it recalculates it. And that's what spanning tree is doing. And again, I'm really sorry. The spanning tree is the hardest, most complicated, most ugly stuff of the whole content. So bear with me. So when we're dealing with spanning tree, we've got a hello timer that's 2 seconds. A max age is 10 seconds. So How long do you wait after not hearing hello, 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 before you say, okay, it's not there? So 10 seconds. And now think about it. If it takes 10 seconds to detect it, and then it takes about 15 more seconds for the port to transition into forwarding, you're dealing with a long time. So you can be, the minimum is 25 seconds with layer 2 till you detect a change. Now, my customers, I put an OSPF or an intermediate systems network. We turn on some RSVP signaling. We then turn on tag switching or label switching, create primary and explicit paths across the network. Now I got a cable cut. I can do it in 40 milliseconds, which means you won't even know that my network is dead. So that's why people like me, our heavy hardcore routing engineers, don't deal with any of this layer 2 stuff. We've replaced it with stuff that works so much better and faster. But in the enterprise and the smaller companies, you're going to be using spanning tree. And when you're going to connect to the cloud, you do have to send them a VLAN. So you're going to at least want to run that on this port just in case. Actually, you probably don't need to be, but if you've got multiple ones, they're still going to be on different subnets. So you don't need it, but just understand bridging, spanning tree. So let's talk a little bit about timers and healing. If a switch doesn't get its hello within the hello time, it realizes there's a problem. So with the default settings, what happens is the max age is 20 seconds. 10 times the default hello sections is 2. So realistically speaking, based on your settings, it can be 10 seconds or 20 seconds. So now, poof, you stop hearing the hellos, 10 seconds or 20 seconds later, it expires. And now the switches are going to recalculate and restrend their data. So it's not going to be the fastest thing in the world. So kind of keep that in the back of your mind. So let's talk about the last thing on spanning tree, and then we'll take a little break and we'll talk a little about rapid spanning tree, which is a huge improvement over spanning tree, but it's not great. So spanning tree uses this concept of a role and a state. And a role relates to how spanning tree is going to analyze the topology, and a state's going to tell it which switch is going to send or receive frames. Now, when spanning tree converges, and what is convergence? When everybody figures out the way that the traffic should go, the switch will choose their new port roles, when the switches will determine whether to block or forward. So kind of keep that in mind. I talked about in the beginning, that's that election we're talking about, and switches can just move. And realistically speaking, by tuning spanning tree to creating something called rapid spanning tree, which we'll talk about later, switches can move faster from a blocking to a forwarding state, etc. But switches come out forwarding. They announce themselves as a root bridge. When they receive a bridge protocol data unit, which has an election, the switches determine which paths have the lowest cost to the root bridge. That's the root port. Forwarding. They elect their designated ports, forwarding, and they block all other ports. So that's why. So now when we're talking about spanning tree, there's a couple of states on the port. Let's talk about what those ports are. So right now you got a port that's blocked. And in the blocking state, what happens? Nothing. Now all of a sudden, the port's going to transition, and the port goes into a learning state where it's just learning which frames, which MAC addresses are there. The switch will get rid of the old MAC address table, and it's still going to start to create new entries by the MAC address as it comes. Then, after listening, it's going to learn. Switch is here, it's hearing stuff, it's learning MAC addresses, it's learning all the topology of the network, it's learning. Then, at some point, it's going to have to transition to forwarding. And that's realistically, so listening, learning, those kind of things. Keep that in the back of your mind. So what are the states in spanning tree? Blocking, not sending. Obvious. Listening, hey, what's going on? Learning, let me get smart. Forward, I start forwarding, I unblock that thing. So from the blocking to the listening to the learning to the forwarding, 25, 45 seconds, that's about how long it takes. That is for spanning tree. And that's the way spanning tree works. So I've got a couple of slides on spanning tree. And after we get to spanning tree, through spanning tree, I will take some questions because the spanning tree is a little ugly. So let's talk about spanning tree. So I just told you about spanning tree. I also told you I don't use it. I told you I hate it. And here's why I hate it. Not only is this brood bridge complex kind of pain in the whatever, but it takes forever to converge. And I was like, hey, wait, I can just turn on this MPLS network and converge in less than 40 milliseconds. Or I can wait 45 seconds for this horrible spanning tree to work. So what did the switching people say? Well, switching is dying and we don't want switching dying. So, because otherwise we're going to have a whole bunch of Mike Gibbses running around ripping out our switches and replacing them with routers, which I've done and still continue to do, and it works great. So the switching people said, hey, not everybody can learn routing. Routing's kind of complex. We're going to create a new spanning tree, and we're going to call it rapid spanning tree, and it's going to fix all the problems of the old spanning tree. So they run the same elections. Spanning tree, rapid spanning tree elect the same root switch with the same rules and tiebreakers. Spanning tree and rapid spanning tree elect their ports, their root ports the same way. Spanning tree and rapid spanning tree elect their designated ports the same way. Spanning tree and rapid spanning tree each report their ports in a forwarding state. But normal spanning tree, 25, 35, 45, 50 seconds or more every time a cable cuts to get your traffic. That is not acceptable. So spanning tree enables the convergence or the self-healing to occur rapidly. That's why it's rapid spanning tree. So rapid spanning tree changes and adds the way spanning tree avoids loops and enables you to transition quicker from forwarding to from blocking to forwarding. That's the difference, the speed that you go from blocking to forwarding. And rapid spanning tree can go from forwarding to blocking fast, or from blocking to forwarding fast. So how? Rapid spanning tree defines more cases in which you can avoid waiting for the timer. So rapid spanning tree adds a mechanism by which a switch can replace its root port without waiting for the forwarding in certain situations. Rapid spanning tree adds a new mechanism to replace the designated port without waiting for it to reach forwarding in some instances. And rapid spanning tree lowers the waiting times, in which case rapid spanning tree must wait for a timer to time out. You know, like that hello every 2 seconds where you could wait up to 10 misses in order to do anything. So rapid spanning tree uses the term alternate port to refer to a switch ports that could be used as a root port if the root port ever fails. If you got potential, it uses the term alternate port and it keeps it stored. Now the backup port can provide backup into the other switch. Now this, realistically speaking, it's a backup port. Now, backup ports were all really designed that had hubs, so they're unlikely to be used today because there's no hubs anymore. But spanning tree and rapid spanning tree, are similar in a lot of ways, but rapid spanning tree differs in a few ways. With spanning tree, the root switch creates a hello. With rapid spanning tree, each switch generates its own independent hellos. And with rapid spanning tree allows for queries between neighbors rather than waiting for hold time. So, are you there? Are you there? What's going on? What's going on? They're all talking to each other. You got a family that communicates. You can detect a problem faster with communication than without communication. So kind of keep that in the back of your mind. So these types of protocol changes help rapid spanning tree isolate what happened in the network fast as opposed to waiting for all these timers to expiration. So what are the port roles in rapid spanning tree? Well, we've got the port that begins the non-root switch, which is called the root port. We've got the port that replaces the root port, called an alternate port. We've got the switch port designated to forward, which is called the designated port. We have a port that replaces the designated port, called the backup port, in case the designated port fails. And we've got a port that's been administratively disabled, called the disabled port. So the point is you've got more stuff, more backups, and the ability to detect things that are there. So kind of keep that in the back of your mind. So to be an alternate port, both the root port and the alternate port must receive hellos from the same root switch. So 2 hellos, 2 links. An alternate port is basically the second best option for a root port because it's fast, it's going to come over, and the alternate port can take over from the root port, which changes very, very rapidly. So let's walk through an example of this. In this particular environment, we've got a root switch and we've got a blocked port. But we can unblock this port really, really, really fast after a failure. That's why it's spanning tree versus rapid spanning tree. So now look at this over here. So now we've got a link failure over here. This link failure is detected. And instead of listening and learning, oh, I'm in the wrong one, apologies. So we've got, in this particular case, we've got a link that fails over here. Now, if it was spanning tree, we'd wait for 10 seconds of hellos, or 20 seconds. Hello, missed. Hello, missed. Hello, missed. Hello, missed. Hello, missed. And that would go on. That's 20 seconds. Now this port over here would go into the listening mode for about 10 seconds, the learning mode, etc. By the time this would normally fail, that would be 50 seconds. But now we're using rapid spanning tree. So we've got all this alternate port figured out ahead of time. This link fails. Poof! This instantly transitions to forwarding. So now we don't have to wait 50 seconds. It's fast. So for the heavy-duty routing people like me that say, hey, this switching thing is terrible, the IEEE came up with this, the Internet Engineering Task Force out there. So the IEEE, the Institute for Electrical Engineers, that does Ethernet, versus the Internet Engineering Task Force, which does our RFCs, et cetera, that we run forth in our specifications for IP stuff. That's what went on, and that's why they fixed it, to go straight from transitioning into forwarding. So let's talk about the RSPP, the rapid spanning tree states. Both spanning tree and rapid spanning tree use port states, both similar, but they're similar but with differences. Rapid spanning tree keeps the learning and forward states, so it goes straight to forwarding. Rapid spanning tree renames the blocking state to a discarding state, and it redefines it slightly. So rapid spanning tree uses discarding as opposed to blocking the link. So there's a difference between disabled and blocking. It's just discarding frames. Blocking should be somewhat obvious by now, but the interface can work, but spanning tree chooses not to forward the traffic. Spanning tree disabled means that the interface was administratively disabled, meaning you shut it down. So rapid spanning tree just combines that into a discarding state. Let's talk about the port state. So if a port is administratively down, in spanning tree, it's disabled. And if the port is administratively disabled in spanning tree, it's disabled. In rapid spanning tree, it's discarding. If we've got something that's stable in spanning tree, it's blocking, while it's discarding in rapid spanning tree. Now, with spanning tree, we go listening, and we go straight to learning and then forwarding. But with rapid spanning tree, we can technically go straight to forwarding from blocking. So what happens is we go straight into learning, and forwarding into forwarding. So we don't have to go through as many states. And we're not reliant on waiting for the hello and the hold timers to wear out. And that's why we can go so much longer. So rapid spanning tree and the backup designated port role. The rapid spanning tree backup port role acts as yet another rapid spanning tree port role compared to spanning tree. The rapid spanning tree backup role creates a new way for rapid spanning tree to replace the designated port on certain LANs. The need for a backup port can be a bit confusing at first, but the backup port role only happens in designs that are very recent, and that's how these kind of things sort of work. So that's what we're talking about: spanning tree versus spanning tree. Loop avoidance strategies to make sure you can have multiple links. Now, I'm not going to really spend a lot of time configuring rapid spanning tree with you guys or spanning tree with you guys, because I want to get you guys into the heavy stuff that really matters. I want to get you guys into some routing, some subnetting. So tomorrow we're going to get into internet protocol. We're going to have some fun, but some people may have some questions. I want to make sure everybody had a good experience on their CCNA course. I know this is a free CCNA course, but I want to run this as if it was a $5,000 boot camp. Questions, lectures, labs. Ask us the questions so we can help you get network hard or cloud hard. So, got some questions? Please ask them. Why do you need spanning tree if you have TTL? Well, Kaigaisa, we don't have a TTL at layer 2. We have a TTL at layer 3. So spanning tree is for layer 2, and we have routing protocols at layer 3, and routers degrade TTL, but we don't have that in layer 2. So we can't use it. But good question. Chris, if you want to bring in the next one. Thank you so much, 7 Series Beamer. I work really hard to make sure that everybody has the best opportunity to get their first cloud architect job, network architect job. I got to tell you, I had such a good tech career. I was able to retire at 34 years old and then just do, and I loved it. And I want every one of you guys to have the absolute best career. And whether it's a networking cloud, as a cloud architect, solution architect, network architect, enterprise architect, I want you to have a ball. It's my mission in life right now to train the next generation of the world's best network architects and cloud architects. And after that, I'm going to go to Jamaica and I'm going to practice Ashtanga yoga, listen to Ziggy Marley singing about beach in Hawaii, which is a song written about Ashtanga yoga. That's where I'm going to be. So we're that. So I haven't asked anybody to do so. If you're not a subscriber, please subscribe. If you're paying attention and you're having a good time, please leave a comment. It helps us with the algorithms and the rankings. And we really like to share our message of free training to help as many people as possible. Thank you so much, Marjan. I was thrilled to have you here, and it was wonderful. Yay, internet protocols. I'm with you there, Eva Dike. Internet protocols are my favorite. Alonzo, my good friend. I am so happy to see you. Awesome session. Thank you. Loving the GCA community. Thank you. Alonzo, I know I haven't spoken to you for a day, and it's been a long time, but I hope you're doing wonderfully. And I hope you're having a great time. Joe, so wonderful to see you here. CCNA, Alonzo, yes, absolutely. It was a great session, CCNA. Thank you. I want to try hard for you. Leo, CCNA, fantastic. Alonzo, cloud hired. I love it. Tom Arthius, thank you so much. If you understand me with Parakalo, I know you're in the Netherlands, but I not love that name of yours, so just in case. Okay, so you're welcome, FM, Linux, CCNA, so fantastic. Twinkle, so wonderful seeing you here. Ruben, so wonderful seeing you here. CJ, in determining the cost of a spanning true route, you mentioned the weighted values for speed versus 10 versus 100, etc. Is there a table that's easiest to get that information? Yes. You go to the Cisco website and you look spanning tree link cost and it will tell you. Why do I want to send you to the Cisco website and not give it to you? Because it changes constantly. And I will give you the best advice that I can give you from 25 years tech experience. Reading 5 minutes of documentation can save you 500 hours of troubleshooting. So every single time I always go to the manufacturer source and look at things even after 25 years, if it's a production environment, because I want to make sure that nothing changed. Great question there. Chris, you want to bring in the next one? Thank you so much. Thank you so much, Cryan. He never loved pets, however, and every night you dream of Cindy and Sonny the cat. All the credit goes to Mike and Steve. Thank you. You know, here's the funny thing. I never wanted a cat at all. My wife loved cats, so what did I do? I went to the cat rescue to make my wife happy and get her a cat. While I was there, little baby girl, literally speaking, puts her paw on the glass. I walk in, she rubs against me. I sit down, she sits on my lap. 45 minutes later, with that cat looking at me like this, that cat came home. I got the cat for my wife. The cat sleeps either in between my knees, on my chest, or right above my head every night. And she's like, God, the greatest thing that ever happened to me. Who knew? Eva Dwight, it's so wonderful to see you here. I rescued the cat for my wife, and I think the cat rescued me. I try, so 7 Series Beamer. I used to practice medicine before I went into technology. And the thing for me was I had to learn how to teach patients to take care of their health. For example, if I had a patient that had congestive heart failure because their left ventricle was too thick, I couldn't say to my patients, your left ventricle is this many millimeters too thick, which causes the ejection, which causes the preload of your heart via Frank Starling's law to be low, which causes your ejection fraction to be reduced. But what I could say is, because your heart muscle is enlarged, what's occurred is your heart can't pump efficiently. So I'm going to give you this medication to increase the pumping ability of your blood. And the patient says, okay, Mike, I'll take it. So I did a couple things. I practiced medicine first, and that really taught me how to simplify concept. But to be fair, I did and Cisco together, we probably spent about $250,000 on my communication skills, soft skills. and emotional intelligence training. And a lot of that was taught how I could translate technology concepts that were really challenging from really smart engineers to the executives that would be the buying decisions. So engineers, all tech, architects, half business, half tech. That's why I'm an architect. That's why when people that want to become engineers become architects, if they don't study the communication skills, the leadership skills, the emotional intelligence, the ROI modeling, the CXO relevancy skills, that's why they can't get there, because it's that special training. So that's the difference between this, and I've had to have special training to become an architect. And for the students in my Cloud Architect Career Development Program, I teach them all how to do this because it's required for the job and even the interviews. Chris, if you want to bring in the next one, I love questions that are like that. They're really solid. Do you need to know networking before the cloud? Well, if you don't know the network, you don't know the cloud. So I have a lot of students that come with me and I teach them the data center and the network, which is the cloud. And then I teach them the cloud and they're like, oh my God, Mike, I could have learned the cloud in 48 hours. And you do. If you don't know the network and you don't know the cloud, then it's incredibly challenging. But if you know the network, you know the cloud. And I got to tell you, it's not hard. So when I was practicing internal medicine, I woke up one day and said, I want to learn networking. And within 6 months, I was the lead architect at the world's largest internet service provider at the time, which was WorldCom. And I was in the team that did the most sophisticated designs in all of networking. A year later, I was the lead architect designing systems for the world's busiest market maker on Wall Street. So if you know the network, if you know the router, if you know the switch, if you know BGP, if you know your IGPs, everything on the cloud is going to be silly easy. And then if you know the data center, what is virtualization? What are containers? What are firewalls? What are load balancers? How does block storage, object storage, file storage work? Guess what, Anthony? If you're on Azure, Google, Oracle, Dell, Palo Alto, Cisco Cloud, it's irrelevant to you. So that's all you need to do. You'll be good to go. So yes, do both at the same time. Would I recommend a switch to practice learning VLANs? It depends. Are you an architect or are you going to be an engineer? If you're going to be an architect, you need to know all about how VLANs work, and I would be focused on being an expert. If you want to be an administrator or an engineer, realistically putting with those kind of things, then you're definitely going to need to practice. So should you buy a switch? You could buy a switch. You could, that's probably the easiest thing to do. Most of these servers are going to cost you more to set up than the switch. So they have CCNA racks on eBay that you can buy. And I find something cheap, basically one switch, 2 routers, and you're good to go. And you can typically do that for about $100 or $150, but you can probably get away with enough without it. So it depends on what is your goal. If your goal is to be a network engineer, yes. If your goal is to be a network administrator, yes. If your goal is to be a cloud architect, it's more about how the BGP works and how to design it than necessarily how to configure it. So for that, it would be helpful, but you could probably get away with simulators, etc. So it depends on your goal career. But definitely speaking, if you want to work in networking, I would definitely get some hands-on experience. Any tips for a mind that's racing? Yes.
Can I butt in here, Mike?
Yes.
You're probably not the best person to ask that question to.
Yes. Okay. So, as Chris said, asking me, who at 11:30 at night sends my chief operating officer, hey, I had this idea. I don't expect you to do it now, but I don't want to forget it. Hey, by the way. So, but what I will tell you is this. I actually practice Ashtanga yoga every single day. And Chris can tell which days I haven't practiced yoga because I'm calling him at 10 o'clock at night. Hey, Chris, I had an idea. Hey, Chris, I had this idea. And on days where I actually practice yoga or meditate, Chris, I thought about this. And Chris, you know what? This thing that you've been suggesting, I'm going to do it tomorrow. Chris, I had a chance to think about this. And guess what? Tomorrow I'm going to do this. So, yes, I recommend learning how to control our thoughts. Either through cognitive behavior therapy, which I use on a daily basis, or via, realistically speaking, using breathing meditations, which I have for the students in our Cloud Architect Career Development Program. We have a cognitive behavior therapy section, and we also have about 6 or 7 different meditations plus yoga that we use. Why? Because when you're stressed, you can't give a good presentation. And what is emotional intelligence? It's the ability to control your emotions and manage somebody else's emotions. So, kind of keep that in the back of your mind. Yes, I was an internal medicine nurse practitioner, and I switched to IT, and I had my own internal medicine office, etc. I say, yes, I did. I came from a medical background. I just love tech more. Okay, so for me, I like you to learn the cloud. So I want to make this clear. Certifications do not get anybody hired for any job, anywhere, anytime. Now, certifications can make up for a lack of experience on a resume, and a certification can get you an interview. So here's what I like to tell my students. Don't get a million certifications. In fact, if you get 30 certifications, the world's going to see you as an architect and as an engineer and never an architect. So I have friends that have gone and gotten 10 certifications and said, Mike, I want to be an architect. And I say, let's remove 7 of those certifications from your resume because nobody's going to take you seriously. And what happens? They don't believe me. They spend a year trying to apply for jobs with 10 certifications. I say, are you ready? I get rid of the certifications. I start talking about the digital transformation they did. I get rid of all the coding and all the acronyms and all the techies business. Send them on their first interview and they get paid and they get $100,000 more than their last job. So what gets you hired? Knowledge. So there's 2 ways you can do this. You could do it the way the cloud providers would suggest, which I think is the worst way to learn. Let's say I get into a car. If I teach you this is a steering wheel, and I teach you this pedal is the accelerator, and this pedal is the brake, and this is the ignition button, you know what it is. Now, what did the cloud providers do? They took the same 40-year-old networking services and they renamed them. So pretend you're at AWS and you have this elastic rotational directional changer. And you go to Google, and Google has this cloud rotational interdirectional optimizer. And then you would go to Azure, and Azure has something that's called the express rotational turner arounder thing. You'd be lost. Now, instead, if you learn what virtualization is, and you know what a virtual machine is, and you built it in VMware ESXi or KVM or QEMU, now you know a virtual machine on the Dell cloud is identical to the virtual machine on the Azure cloud, which is identical to the virtual machine on the Oracle cloud, which is identical to the virtual machine on the Google cloud. And by getting rid of these stupid names that the manufacturers make to make their 40-year-old technology sound cool, you're learning to drive. So learn what a virtual machine is. What is object storage? Learn object storage, what it works, how it works. Be good at it. Understand the metadata, how it works. And then it doesn't matter whether it's Microsoft Blob, Amazon Simple Storage Solution, who thinks of these names? Google Cloud Storage is the same technology. So I recommend you get one certification, Azure or AWS, one certification. Become a master of the cloud, become a master of the network, become a master of the data center. Build your emotional intelligence, your leadership skills, your communication skills, your presentation skills, your ROI modeling, your business acumen. Then you're getting cloud hired. Now, let's talk about this. Statistically speaking, once you go above a certain number of certifications, they don't raise your salary. But let's look at it if it is. Let's say you only had one certification and you wanted 2. Potentially by getting a second certification, it can raise your salary upwards of maximum $10,000. So you've got a salary, average cloud architect earns $160,000 a year. Good one earns double or triple that easily. But let's say you're an average cloud architect at $160,000 a year. You get yourself 40 more certifications, and now your salary goes from 160 to 170. Or you go out there and you get some soft skills training, which on average raises your salary 30%, which is $60,000 a year for that average salary 160. Now you get yourself some emotional intelligence training. Poof, on average, that raises your salary $29.6 thousand per year. So now we've raised your salary $90,000 by not wasting on an extra certification that's worthless. And you do that for 30 years, that's $2.7 million. Now, those other 2 skills that we told you to focus on, your soft skills and your emotional intelligence, now enable you to become a director, a VP, the chief technology officer, or anything you want. And what does that extra certification do? It locks you behind the desk. This is the techie. So figure out what you want to be. If you want to be an engineer, and engineers are great, yeah, get lots of certifications because it really matters the name of the service and how to configure it because that's all you're going to do. But if you have any desire for architecture or leadership positions, if you actually go to a customer and you start talking about EBS and S3, they'll laugh you out of the room. They're going to say, are you an advertisement for Amazon? Where if you said, okay, I can deal with your 3 petabytes of object storage, but moving it over to object storage on the cloud. And if I can deal with your 1,500 virtual machines, I'll replace them with similar virtual machines on the cloud. And I can then give you an environment that says, we need security. Of course, we can't use the cloud native things. What are we going to do? We're going to get 2 firewalls from Cisco and load balance them with a network load balancer. That's architecture, and that's the design. So build the skills and go get hired. And certifications don't get anybody a job. Never. Nobody hires you for any certification other than maybe the CCIE because they have to prove that you're competent. Competency gets you hired. Good attitude gets you hired. Emotional intelligence gets you hired. Leadership skills get you hired. A good attitude, happiness, good communication skills. That's what gets you hired. That's your focus. That can raise your salary $100,000, $200,000, $300,000 a year easily, where a certification can't. So that's my recommendation. That's how I've been coaching my people. And I got to tell you, I've got graduates that are earning $300,000 a year. It's not average, but it happens lots of times. Why? Because we focus on high value skills, not low value skills. Stamina. Here's the reason I have stamina. I actually was trained by a bunch of Navy SEALs for mental toughness. I was actually a competitive martial artist, and I've been practicing martial arts forever. So hard physical training. I subscribed to something that was called SEALFIT many years ago, and SEALFIT was run by Navy SEALs to get guys and girls, well, guys through buds because they didn't have any women at the time, and it was mental toughness training. So there's that. My multitasking skills, I wish I could say they were good. They are not. My ability to go for a week straight without sleep, that's pretty solid. And that came from medical training, hard work. And when I did my CCIE, I read 1,000 pages a day every day for 6 months. It was 75,000 pages of reading that I had to do to pass that CCIE exam. And I did it in about 6 months because I was really motivated. So thank you so much. I do work pretty hard. And I tend to be a fireball with energy. You know, it's really funny. When I went into tech, I thought tech was the least stressful environment in the world. In fact, I know other network engineers and they're like, this is stressful. I'm like, stressful? I remember in my first job, everybody was stressed. They're like, the network is down. And they're like, I'm like, hold on. Click, 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 click. Okay, fixed. And they were like, Mike. And there were like 30 people and they were all stressed out over it. And I was like, can't be stressed. See, here's why. See, right now we're talking. And we're using the prefrontal cortex of our brain. That's the thinking, logical reasoning part of our brain. When we're here, we can make magic happen. But you know what happens when we get stressed? The prefrontal cortex shuts off and the amygdala kicks in. And the amygdala is this crocodile part of our brain, and it's nasty. And the amygdala is great if we got to fight somebody. Yeah, well, because freeze, fight, or flight. But the amygdala makes us dumb. So if you don't know, if you've ever had an argument with someone and said something horrible that you regret, that's because your prefrontal cortex shut down and your amygdala kicked in. So, yes, I view networking as nothing. So when I get in an environment, it's $1 billion architecture and it's not working, and somebody's like, Mike, oh my God, oh my God, oh my God, we're losing money. And I take a deep breath, I get to it, and I go through it. And they're like, why aren't you stressed? And I say, is anybody going to die if I don't fix this in the next 3 seconds? And they say, no. I'm like, then it's a vacation for me. Because that's what I did working in the emergency department. How did I pay my way through college? I was a paramedic. I dealt with life and death things. So to me, this is nothing. It's just networking things. It's a packet. It's not working. We figure it out. So I do utilize a technique called box breathing. And I'm also going to bring Todd McLaughlin back on my channel. So Todd McLaughlin trained with the Joyce family in India. He trained in Thailand, and he also trained with Bikram himself. And he's been teaching yoga for a while. He is my guruji as it pertains to yoga. He hates being called guru, but since he trained with guruji himself, Patabi Joyce, and the other guruji himself, Bikram, for me, he's my guru. I've been working with him, so that's kind of the thing. So it's the thing is just mental toughness. Just keep fighting, 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 and you'll get there. Can someone compare the CCNA to the CompTIA Plus? I tell everybody to never do any CompTIA certifications ever. And here's why. They are good certifications. There's nothing wrong with them. But except for the US government, employers don't care about them. So what is the CompTIA A+ Network Plus good for? The people that work at the Geek Squad at the Best Buy that repair your PC, not really kind of any industrial jobs, potentially help desk. So the CCNA is about 1,000 times more valuable than the CompTIA Network Plus. I would never get the CompTIA Network Plus. There's no point in it. Do the CCNA, the CCIE, the CCNA, the CCNP. They're the only networking certifications you're going to need. And the CCNP will give you a lot to get hired. Ruth, you currently have a networking background. Fantastic. CCNA and CCNP. Okay. But it's currently expired and later switched to cyber security. What can you do to get hired as a cloud architect? Well, Ruth, if you truly understand networking and have CCNP knowledge and CCNA knowledge, real networking, and you understand BGP tuning and traffic engineering and OSPF and QoS and VLAN tagging and VLAN trunking, you already have half of it. So then, assuming you know all of that from a design perspective, and if you don't know the architect part of that, study it from us or study it from somewhere else, learn the design, because remember, architects don't configure, we design. So learn the network, learn the data center, switches, routers, VLANs, trunking, tagging, BGP, IPsec, etc., etc. Learn servers, server virtualizations, containers, firewalls, VPN concentrators, storage, etc. Then focus on developing your leadership skills, your communication skills, your emotional intelligence, your presentation skills, your business acumen, your CXO relevancy, etc., etc., etc. And then guess what? You will have an easy time getting a job. So that's really the key. It's building the portfolio that shows you're a cross between a business exec and a technology professional, having the business acumen, the networking acumen, and the data center acumen, and then just knowing what are those network and data center equivalent services in the cloud, and then which service to use and how to do it, and knowing business well enough to be able to interact with an executive, figure out what their business problems are, and craft a technology solution. So Ruth, that's the skill, and that's the process, and you can go out there and get yourself cloud hired easily. Chris, if you want to bring in the next one. Okay, so, to be fair, somebody asked about reading 1,000 pages a day. That's not normal. And I know that's not normal. So here's the thing. I have a laser-like focus that's bordering on the obsessive-compulsive side without being a disorder. And here's what happened. When I went to college, I was really, really poor. I mean, to the point where if I had gas in my tank to survive the next day, I was really in good shape. So what did I do when I was in college? I worked full-time as a paramedic. And that enabled me I went to school from 7 to 3. From 3 to 11, I worked on the ambulances. 3 days a week from 11 to 7, I also worked on the ambulances. And then on Saturday and Sunday, I worked 7 a.m. to 7 p.m. And I did that for 4 years straight. So when I was in school, in order to survive, I learned how to read. I learned how to basically be able to read through the content, find exactly what the critical stuff was, pull it out and remember it, and then go. Now, when I learned healthcare things, again, it was like learning another language. So because of that, that's why I learned how to read very fast. So I do read differently than other people. I do learn at a different rate than other people. But you know what? Other people learn a lot faster than me. I went into my wife's medical office one day, and I heard her say in Spanish, on a scale of 1 to 10, 1 is a little bit, and 10 is a whole lot worse than having a baby. How much does it hurt? And, it wasn't the usual medical professional of te duele. I mean, it was detail-oriented in Spanish. And I went, wow. And she said, my translators couldn't understand my thoughts. So what was I going to do? I got a dictionary and I memorized things. So the point is, you can all do anything you can imagine. And I got to tell you, I've been coaching people forever. I have seen people do amazing things. I had a student, his name was Richard Afukar. He was in my program for 3 weeks before he got hired by Amazon. But he bought 3 private interviews, and I think he was up 24 hours a day, 7 days a week. Because when I spoke to him, he said, I haven't slept in 4 days. But that's why Amazon hired him. I had another amazing student. His name is Coyote. Actually, and Yvonne. They're 2 students that just got hired by Amazon with 0 tech background whatsoever. One was working as a waiter and one was working something else, but not tech. But what did they do? They put in the oomph, 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 oomph. So in martial arts, we say hard work beats talent when talent doesn't try. And let me tell you, in my experience, it's the people that will just do, and do. And you know what? If you read a little slow right now, don't worry. Today, start with 10 pages. Stretch it out. Go to 11 tomorrow. Go to 12 the next day. And if you're a 12-hour week, fine. Go to 15 the next time. You'll see, as you do more of it, you get much, much better at it and you learn it much quicker. So that's my thing. So let's do this. We've been here for a while. I don't want to keep you too late because we've got 2 weeks. If you can all type hashtag CCNA and write hashtag your geography, we'll end the day and we'll have fun tomorrow when we get to more networking related stuff. I just like knowing where everybody's from. And if you can, hit the like button, comment, subscribe, tell a friend. We want as many people to be helped by this video as possible. Okay, I'm starting to see the CCNAs pop in. Dan Steer, Cornwall, UK. I love that. Nikhil, CCNA. I know where you're at, Nikhil. Sharon, CCNA. Anthony in Kansas. I love it in Kansas. I spent a lot of time in McPherson, Wichita, and Kansas City, although it's Missouri. Twinkle, you're in India. I love that. Brian, CCNA, Dallas. Fantastic. Robert's over there in Dallas. I love that. Robert's a great security guy. Brian's from Philly. That's where I'm from. Marla's in Atlanta. I love that. Abu Malik, it's good to see you. You got one of my favorite musicians listening there. I hope everything's Irie. Good to see you, Danica. CJ, good to see you. Tom Orthius is in the Netherlands. I always love that. Gabriel in Zambia, fantastic. NASCO, Frankfurt, Germany, fantastic. Dimson Mentor, I know you real well. ET, good to see you. Danica, good to see you. Cloud Hired. Earl Owen, CCNA in Tacoma, awesome. I see Egypt over here. I see Maryland over here. Network Bush, you're in Orlando. We should meet one day. I'm in Port St. Lucie, Florida. Hand to God, CCNA, good to see you. Dan, Chicago, wanted to see you. CCNA, Bangladesh, fantastic. Maryland, I love that. Eva Doikia, 7 Series, good to see you. Sharon, wonderful to see you. Muscat, fantastic. CCNA, are you in Pakistan? That's wonderful. Frank Soto is in Portland, Maine, fantastic. Millicent's in Maryland. Dave is in Beltsville, Maryland. I love that. CCNA, FM, great to see you. Kulani, you're in Taiwan. How terrific and how international. AK's in India. I'm loving this. Okay, fantastic. Glasgow, Scotland. Boy, I spent a lot of time there a while back. Leo's in Brazil. William is in Massachusetts. And Ivo Doik is there in Denmark. Fantastic. AK's in India. And Mohammed's over there in Egypt. ET, Maryland. Lisbon, Portugal. Wow. Tech with Mufaz over there in Nigeria. I love that. CCNA in India. Birmingham, Alabama. Hand to God. That's fantastic. Birmingham, UK. Okay. Fantastic. I've been there quite a bit. Alex is in Boston. Fantastic. And Ruth is in Maryland. I'm loving this. Rocket Flies, Florida. Well, we got both Chris and I are in Florida. And I think there we go. So, and Mark is in New York City. Mark, I'm loving that. I see some great things out of Mark all the time. Mark's really, really capable and really, really smart. So, thank you all. Have a wonderful night. And I will see you all tomorrow. And we'll be talking about some more IP-related things. We'll start with subnetting, but it'll be fun. I promise. I'll make it interesting. Welcome back, everyone. This is Michael Gibbs, and I'm the founder and CEO of Go Cloud Architects and Go Cloud Careers. And today we're going to continue with day 3 of the Go Cloud Careers completely free Cisco Certified Network Associate CCNA 200-301 training camp. And this is a completely free CCNA 200-301 course. My name is Michael Gibbs, and of course, I'm with Go Cloud Careers. So today is going to be day 3 of our CCNA program, And whether you desire to be a network administrator, a network engineer, a cloud architect, a solution architect, this Cisco Networking Essentials training, or network administrator training, or network engineer training, or networking for cloud computing training will help you go out there and get yourselves cloud hired. These are critical cloud architect skills. This is critical cloud architect career training. And this is some critical cloud career tips, because guess what? If you're a cloud architect or desire to be a cloud architect, half of what the cloud is a network. The remaining 50% is a data center. And if you want to be a network engineer, like I started my career, it's a wonderful job. If you want to be a network architect, where I spent multiple decades, again, it's a really wonderful job. So again, this is free network training. Basically, we began with what is a computer network and started with this as an intro to networking course. As you can see, we get into networking and cloud computing as well. But let's have it. Let's begin. Let's have some fun. So if you're here and you're awake and you're alert and you're oriented and you want to have a good time and learn a lot of networking, type hashtag CCNA. And if I see that, I'll know you're awake, alert, oriented, and then I'll start getting into the content. Daniel Green, I love that. Where is Cindy? Cindy right now is unfortunately chasing some squirrels around in my backyard. So I feel very bad for the squirrels. I asked her not to do that, but she doesn't seem to listen to me. So she's not on my lap this 5 minutes. But thank you for asking. She's doing great. So, realistically speaking, so good to see you. Georgetta, wonderful. Alexandros Kalispera, Daniel, Hike, good to see you. Earl, and CCNA, Mr. Gee, CCNA, I'm loving this. I can see that you're there. Nikhil's here, fantastic. Crypto, fantastic. Sarah, welcome back. Ned, welcome back. Sanchin, fantastic. Brian, wonderful. Muhammad, fantastic. CCNA, Ransom, CCNA. Elvis, CCNA. Sadie, CCNA. Ruth, CCNA. Daniel Green, CCNA. Leo Paredes, CCNA. Mick B, hello, Mike, Chris. Hello, Brew Ranchers, thank you so much. And Emmanuel, CCNA, fantastic. Angelo, CCNA. And Casigo, CCNA. Not sure how to pronounce that name, but thank you so much. And CCNA. And Jeannie, it's so good to see you today. Dan, CCNA, I get it. I'm loving this. Jim Weaver, CCNA, I'm fantastic. Sharon, good to see you. So good to see you. CCNA. Mark Hema, CCNA. And Udi Wilson, so nice to meet you. Farman, so nice to see you, CCNA. Jabuki, CCNA. Hasnat, CCNA. Fantastic. So let's have some fun and talk about some networking training. Now, some stuff in networking is really fun. Some stuff is a little dry, but it's all necessary, whether you want to be that cloud architect, solutions architect, or network engineer. So having some fun with this, let's start with subnetting. Subnetting. And let's talk about subnetting. So when we're dealing with IP networks, what we're really dealing with is being able to make sure that our traffic can go from place to place. And realistically speaking, in order to do that, every interface on our network needs an IP address. Say it with me. Every interface in our network needs to be on a different network or subnet. So you've got a router with 4 interfaces. They're going to be on 4 subnets. You got a server with 4 network interface cards. Guess what? They're going to be on 4 subnets. You got a firewall. Each port on it, chances are, is going to be a different subnet. Is going to be on a different subnet. So that's what we're talking about. Is everything needs a different subnet. Now the reality is, if we're not careful, we could waste so many IP addresses, so many of them, that what it could do is it could, literally speaking, use up pretty much everything that we actually have, all in a couple of interfaces. So, when we're dealing with this, we're going to talk very carefully about why we have to subnet. So I'm going to give you a couple of examples, and I want to show you why we have to subnet. And we're going to get into a lot more depth of the rationale of why, but let's just walk you through in a simple example. So in this example, what I'm going to show you over here is I'm going to show you a network that's not been subnetted. And For example, here we go. I've got a network here. I've got 4 interfaces on a router, and we'll talk about what we mean by Class A, Class B, Class C, Class D addresses, site or routing, and all this cool fun stuff. But if I didn't subnet a network and I used this 2.0.0/8 as a subnet on one port, and the 1.0.0/8 as a subnet on another port, and I used the 4.0.0/8 on another port, and the 3.0.0/8 on the subnet. Wow, do you know how many IP addresses I would use? 64 million. You heard me. I'd be wasting over 64 million IP addresses. Now, I did tell you can put up to 250 hosts in a subnet, 500 if we're really pushing it. So now we've got 500 on each port. Now, we've got 2,000 hosts, but we've wasted 64 million IP addresses. Not so good, huh? So, now let's say we were to break these networks down. And I'll be walking through this, but now we broke them down into something called the /30. A /30 is a subnet that has 2 available hosts. Now, on the same router, it's got WAN links. One link to another router, one link to another router, one link to an upstream router, one link to a downstream router. And we've subnetted down and we're using a /30 subnet. I burned 16 total addresses. Now, I only used 8 of them, and I'm still wasting 50%, but I only use 16 addresses versus 16 million. So we don't have a lot of IP addresses. Do you want to waste 16 million of anything? Of course not. Of course not. So keep that in the back of your mind. So when it comes to networking, I'm going to tell you right now, your IP addressing plan or your subnetting plan is the most critical thing you have in your systems. Your IP addressing plan or your subnetting plan. Absolutely critical. So let's talk about and walk through some examples. And you'll see what I mean. So let's say here, we've got a switch, which is on one subnet. See this link on this router? This is all going to be on the same subnet. Now this is going to be in a different subnet. This is also going to be a different subnet. This is a different subnet, and this is a different subnet. So just in this example, we have a minimum of 1 subnet, 2 subnets, 3 subnets, 4 subnets, 5 subnets. Minimum. So what we have to do as network engineers, network architects, cloud engineers, etc., when we're dealing with networking, we have to think about what these things are. So, for example, if we made each one of these a /24, we'll talk about what that means. We'd have 250 hosts or 253 hosts available on the subnet. So good. 254. But anyway, so on this one, what do we need? If we use a /24, we're going to burn 260 address or 250 some addresses. But if we use a /30, we only use 2. How many addresses do we need on a link that connects one router to another router? 2. How many addresses do we need in this LAN subnet? I don't know. Do we need 16? Do we need 32? Do we need 64? Do we need 128? Do we need 512? How do I know? Ask the customer. Hey, what do you want to put in here? I don't know. How many hosts? Determine my subnet. How many subnets I need? Determine my subnet size. So there's going to be some noodle work here. This is where we're going to get our hats on with the propellers on them. We're going to get a little geeky, and it's going to be fun. But, keep that in the back of your mind. So that's why we have to subnet it down. And we have to be very, very, very careful how we do it, because the addressing that we use will determine our routing. So the first thing we're going to do is we're going to analyze the needs. Number of subnets, number of hosts per subnet, and the size of the subnet will determine. Then we're going to design our subnets. We're going to choose the network. We'll pick our subnet masks. And then obviously we've got an implementation plan of typically speaking, it's the junior implementation engineers that go and configure this stuff. So that's kind of works. And we'll talk about how to do all of that. So let's analyze subnetting addressing needs. So how many hosts need to be able to talk to each other? There you go. How many hosts? And if you want them in a subnet, if you want them to talk to each other without a router, they have to be in the same subnet. So you might create 2 subnets for security, but you might want 2 people to talk to each other in the same subnet. It's most practical. So how many hosts? How many but you're going to need in the network. Remember, if you've got 10,000 WAN links, you're going to need 10,000 subnets just for your WAN links. Now, then we have to think about how many hosts do we need in that subnet. on a point-to-point link, which is effectively a wire between two people. Here's a wire. How many people? There's one person on the wire, one router, and one on the other end of the wire. It's a wire. How many addresses do we need? 2. That's it. Because there's nobody else we want on the wire. By using 2 and not 24, it makes it more secure. If people tried to get in there, they couldn't even get an IP address. They wouldn't be on the same subnet. So keep that in the back of your mind. So let's walk through another example. Need a subnet here, a subnet here, and a subnet here. Now, I'm going to give you some generic guidelines that are going to work in 90% of the situations. We use a /30 on a WAN because we only need 2 links. And you know what we use on a LAN? A /24, 255.255.255.0. Now, we're going to talk through all the numbers, but you want to know what to do in practicality? /30 on a WAN link, /24 on a LAN link, and Bob's your uncle. Everything works great. But we'll get more specific because there's times we want to go more than that. Let's look at another example. Here, LAN segment, 1 subnet, WAN subnet, 1 subnet, WAN subnet, 1 subnet, WAN subnet, 1 subnet, and another subnet per LAN interface. So 1 subnet, 2 subnets, 3 subnets, 4 subnets, 5 subnets, 6 subnets, 7 subnets. Now imagine if we use the /8, which we'll talk about later, where we get 16 million addresses. So 16 million times 8. Wow. 64 times 2. We'd be burning 128 million addresses. We know you can't get more than 250 to 500 hosts on a subnet before we have too much broadcast traffic, so that'd be a waste. Let's look at a different version of this. Okay, we've got 12 VLANs over here. So how many VLANs do we need? Subnets for VLAN. Each VLAN's on a different subnet. So we need 12 subnets over here. We need a subnet for the WAN link. We need a subnet for the WAN link. We need a subnet. So now we're up to 15 subnets. Now we've got 2 VLANs here. So 17 subnets, 19 subnets, 21 subnets. Now imagine using 8 million hosts for that number of subnets. I mean, 16 million hosts per subnet. We'd be in the 40 million range of IP addresses that we're using, when the reality is we probably need 500, 500, 500. So that's 1,500, and 12 times, 12 times 250. Again, 250 times about 3,000. So 3,500 addresses effectively versus, 40 million. Big difference. Let's walk through another example. Here we got it. We've got a core router, which has got a subnet to connect to this subnet. It's got a subnet to connect here and a subnet to connect here. So 1 subnet, 2 subnets, 3, 4, 5, 6, 7. Now, notice what they said here. They said the biggest subnet we have is going to have only 50 hosts per subnet. So if we wanted, it would be real easy for us just to do this. To pick a subnet that can handle, say, 50 users, to pick one that can do 16, or another one that can do 32, or whatever the subnet size is. Now, and that's, perfectly using address space. Why do I recommend /24 for LAN links, /30 for WANs? See, in this particular environment where you say largest 50 hosts per subnet, yeah, we plan on 50 hosts per subnet. And you know what happens? The company does well. And they thought they needed 50 web servers in the subnet. And the reality is they need 100 web servers in the subnet, or 200 web servers in the subnet. And that's the thing. Because of that, I'm going to tell you, in your career, use a /24 for LAN links, no smaller, regardless of whether you can do the math. Use the /30 for LAN links. But we're going to go through the math here. Anyway. Now, when we're dealing with subnets, what we're dealing with is as follows. We got a 32-bit address with IP. 32 bits. So what that means is we have 2 to the 32nd in terms of the number of addresses. 2, 4, 8, 16, 32, 64, 128, 256, 512, 1024, etc., etc. So 2 to the 32, which gives us a couple billion addresses, which is great, right? Okay. How many billion people in the world? 7 billion. Got a problem. How many mobile phones in the world? Probably 5 billion. How many computers in the world? Probably another 5 billion. how many smart refrigerators, smart homes, et cetera, that are out there. Billions and billions more. Internet of Things sensors out there. So does anybody see a problem? We ran out of IP addresses a long time ago. So that's why we have to be really careful. So what we're doing is we've got this 32-bit address, and it can be all network bits or all host bits. And what we can do is we can move the network bits over in one direction to basically make smaller subnets, or we can move the host bits to create bigger networks. And we're going to be doing a lot of that. So here's the reality. If this, it says need 200. So like I said, use a /24, that'll give you 254 addresses. Now you need here 50, but if you use a /24, guess what? You're still going to be good to grow for growth, good to go for growth, good to go for growth. But would you use a /30 on this WAN link? I mean, a /24. No, why not? We don't need 254 addresses on the WAN link. And even though I'm telling you to plan for extra in your LAN segments, guess what? Can we ever have more than 2 people on a WAN, on a point-to-point connection? If I'm looking at the Blue Ranch, if I want to run a wire between my house and Eva Doike's house, is that wire ever going to talk to more than 2 people? No, because it's going straight from my house to Eva Doike's house. So I only need 2 addresses. So there's no point to allocate room there. But for your LANs, give yourself room for growth. Now, in this particular case, and we'll work through examples like this, we're going to use more mathematical numbers. We're going to say, okay, we need a class C or a /24 here. We're going to say we only need 2 addresses here. And now we're being digital. We need 50 addresses per subnet, but there's no subnet that gives us 50. So what we do is we use a subnet that's got 64 total addresses. We minus out the network address. We pull out the broadcast, and now I've got a subnet that can support 62. And we create 3 of these subnets. And actually, we can create 3 of these all on a single class C address or a /24. So let's play around with this a little bit. Here we've got 4 class Cs or 4 /24s, which people like me in the networking world would call us a class C because, well, we'll talk about class A, B, and C addresses. Typically, those of us that have been around for a while, a /24 is a class C, a /16 is a class B, and a /8 is an A. We networking people have made up our own classes, which are totally different than the rest. So just so you know what that is. But look, as you can see, and this is generally speaking best practice, you've got a /30 for 2 usable addresses over here. And we've got what we're talking about over here is /24s for our LAN segments. So again, what are we doing? We're analyzing needs. How many hosts can be on each side of the link versus, realistically speaking, how many networks do we need? And that's realistically how we're going to do everything. So the next thing that I want to show you is for communication to occur, every device needs to have a unique address. So let's pretend it was mail. I want to send a letter to Eva Doike out there. I need her address. Now, let's say Eva Doike lives at 123 Greek Street in Hungary with a certain postal code. And let's say Mike lives at 123 Greek Street, but in Palm Beach Gardens, Florida, with a postal code of 349 or 53. My address is unique. Eva Doike's address is unique because our postal codes are different. Even if we both live at 123 Greek Street, because I speak Greek in the house, and my family's from Greece, I kind of like using Greek Street, but whatever the case is. So when company A speaks to company B, they have to be on different addresses. So anything that needs to be reachable from the internet needs to have public addresses. And anytime one company needs to talk to another company, guess what? Again, we're in the same position where we need to have unique addresses. So we'll be talking about things like NAT throughout the thing in order to translate public addresses to private addresses, but that's coming in the future, not right now. Now, what I do want us to talk about is private addresses. And What happened was the Internet Engineering Task Force looked and said, we have an IP address problem. We don't have enough addresses. So if we want more addresses, what can we do? So what the Internet Engineering Task Force decided to say was they carved out a lot of addresses, and they said, all organizations use these internal to your network. Anything that does not need to be reachable by the internet or reachable by external entities, use these private addresses. And by organizations using these private addresses, we never ran out of address space. So, I mean, the point was is we didn't have enough IP addresses 20 years ago. Even 20 years ago, we were using these private IP addresses, and that enables us to kind of get a lot more mileage out of our network. So where do these private IP networks sit? They are the 10.0.0.0/8 subnet, which is a class A, which we'll talk about later. But it is 2 to the 24th number of hosts that you can put in there. Wow, that's a lot. 2 to the 24th, it's about 16 million to put in your mind. Next, the Internet Engineering Task Force said, we will use the 172.16.0.0 all the way to the 172.31.0.0. So it's the 172.16.0.0/12 address base. And guess what? That gave us basically 15 or 16 class Bs we could use. So by doing that, we've got a lot of addresses per region, and we split it out. Again, lots of usable addresses. Next, we decided to dedicate the 192.168.0.0 all the way to the 192.168.255.255. Guess what? What does that give us? I'll tell you what it gives us. It gives us 2 to the 16th in terms of number of addresses. So lots of addresses, lots of networks, all kinds of cool stuff. So that's what we did. And those are the addresses we're going to use inside of our networks. Now, if it's in our network, great. If it's in the AWS cloud, great. If it's in the Azure cloud, great. If it's in the Oracle or the Google cloud, great. It's the same thing. A cloud is nothing more than a network and a data center that's been virtualized. So let's look at the system of format of unsubnetted class A, B, and C networks. The number of networks of a class A is 8 of them, but we've got 24 host bits. So how many hosts per segment? 2 to the 24th minus 2. Why? 24 bits of host, 8 bits of network. So 2 to the 24th minus 2. Anybody wants to do the math? You'll see that it'll give you basically 16,777,214 addresses. That's a lot. Remember, we can only put about 250 in a subnet before we waste them all due to broadcast. So that's what we're doing. So now the class B that I was talking about, the /16. Well, 2 to the 16th minus 2 is about 65,000 addresses, 534. Again, a whole lot. You're going to be subnetting that down. Class C, number of network bits is 24. Number of host bits is 8. 2 to the 8th minus 2. And guess what? That's why you get 254. So why is everything 2 to the whatever? We're dealing with the binary address. What is binary? 0 and 1. How many is that? 0 counts as a number, and 1, that's 2. So that's why we're dealing with 2 to the x minus 2. Now we're going to subtract 2. So why are we subtracting 2? So the first address is going to be reserved by the network. So 192.168.1.0, 255.255.255.0, otherwise known in CIDR notation as /24. I can't use the address of 192.168.1.0. Why? That is the network address or the subnet address. That's what the routers are going to put in the routing table to build them out. But they can't use that address. Now, 192.168.1.255, that's called the subnet directed broadcast. And what's that mean? Everybody listen to me, everybody listen to me, everybody listening to me. So we can't use that either because that's a screaming loud broadcast. So with every subnet, it's going to be 2 to the x number of host bits minus 2 slash 30, 2 to the 2, which is 4 minus 2, slash 29, 2 to the third power minus 2, 8 minus 2 is 6, 2 to the fourth, 16 minus 2. Guess what? 14. So now you get it. Broadcast address. So that's really what we're talking about. And what's it going to look like? It's going to look like this. And I'll show you. So A, you've got 8 network bits and 24 host bits. Class B, you got 16 network bits and 16 host bits. Class C, we got our 24 network bits and our 8 bits of host bits. So you can see what we're dealing with here. So now let's decide to subnet it down. Instead of dealing with that class A, we used to be using the class A, it was a /8. Now, guess what? Instead of keeping it as we could have 10.0.0/8. Or, and what can we manipulate there? The 10 is going to be there. We can do the 10.1 all the way to 255 effectively. And on the third octet, we can do the 1 to 255, or 0 technically. And on the third octet, we could go 1 all the way to 255. So that will be 2 to the 24th minus 2. But now, let's say we want to subnet this down. Subnet it down. We're going to subnet it down. So we're going to get 8 subnet bits plus 8 host bits. So now, instead of being 2 to the 8 minus 2, now it's 2 to the 16th minus 2. Wow, 65,000 addresses versus 16 million. Let's subnet it down some more. Let's subnet it down to 255.255.255.252. Okay, how many network bits? 30. How many host bits? 2. And that's all we're doing with the subnetting, is sliding in one direction back and forth to either or. That's all it is. So if we need a certain number of subnets, we borrow host bits and go this direction. We need a certain number of host pair subnets, we go in this direction. And vice versa till we have our subnet size. That's what we're really talking about. So when it comes down to it, it's kind of like the power of 2s. Because binary is a 32-bit address. It's either on or off. Now, this gets a little complicated for Americans, and it's much easier for Europeans, because in Europe, when we push the elevator and we go to the first floor, it has a 0 on it. And then the next floor has a 1 on it. So Europeans count starting at 0. Now, Americans start counting at 1. So when you tell an American floor number 1 and they're in England, they think they're on the first floor when they're really on the second floor, and it causes all kinds of confusion. So that's why if you're not used to starting at 0 and counting 0 as a whole integer or a whole number, then you will find this confusing. So just remember, we start at 0 or 1. Binary addresses are 0 or 1. And we'll have some time. If this gets complicated, I have some other slides that I created that are a little less like the Cisco slides, which we can use. Because no matter what, you will all understand subnetting by the time we're done this. So let's do a little bit of analysis. Here in this particular environment, we figured out that we were going to use this subnet. And by using this subnet, we need, realistically speaking, 200 hosts per subnet. So in this particular case, if we need 2, we do a /8. We need 200. What do? We have to find the thing that's next closest. So is there a subnet that gives us 200? No. Is there a subnet that gives us 256 minus 2, which is 254? Yes. That is a /24. So that's what we use here. And we'll walk through the math. I have a couple of charts should people not be enjoying this, and I'm going to start with one right now. Here is what this looks like binary-wise. We've got all 1s and all 1s. For the extra subnetting, we've got all 1s. For the host, we've got all 0s. So what I like you to all do is look at this chart. We're gonna to make it consistent. Everything we're gonna do over here is gonna be as follows. I want you to think about, let's just bring this over here. Everything we're going to talk about is bits and bytes. So 128, 64, 32, 16, 8, 4, 2, 1. So let's look at it this way. We've got, actually, I think I'm going to introduce this a little bit later. I might be too premature for us to do this. So now let's go walk around and play with some additional subnets. If we look at this, these are our usable addresses. So 172.16.0.0, what does that enable us to do? It enables us to use this for the router. This is that, hey, everybody, broadcast. And these are our usable addresses. So again, in another situation, we go to the next subnet. These are the address range that we can use. This is, again, that everybody broadcast. So I hope that that kind of makes some of this relatively simple for you. And we're going to get through the numbers and how to do this. But before we actually get to the numbers, let's look at this. And this is a good thing for you to really get. What we're trying to do is as follows. We're trying to make sure that when we design our systems, we've got a subnet range for one set of systems in one geography, a subnet range for a set of systems in another geography, and another set of subnet range for another one. Because what we're trying to do is minimize the routes that we need to actually send to somebody. So for example, we can have one route that we can send over here that summarizes all of this. We can have another route for this entire summary address, and we can have another route over here. So this is pretty beautiful. Why is it beautiful? They've chosen dissimilar information for each section of the network, and that's what we're going to want to do. We're going to want to segment it out. So let's work through this little example here. Let's say we got a server over here, and its server has an IP address of 172.16.1.11. Now, that server is on the 172.16.1.0 subnet. That's what the router sees in its routing table, and it tells the rest of the world. Okay. Woohoo. So now, how many addresses do we need on this link? 2. How many addresses on this link do we need? 2. So this PC over here is going to have a default gateway. And for example, if this PC wants to go to this PC, the PC needs to have a route in its routing table. And guess what? Most PCs don't have a lot of routes. What did the PC have? This is my default gateway. So let's say this PC wants to reach this server wants to reach this PC, what have you. Server goes to the default gateway. The default gateway says, I know how to reach this system. Send it this way. This system says, I know how to reach it. It's my directly connected LAN. ARP, who has the MAC address. This guy responds. This guy responds, and he says, I don't know where to go. I got a default gateway. The default gateway says, yes, I'll give you that MAC address. Now the router forwards the thing to this next thing. Now the router forwards to the server, and she says, I'm here. I responded. The server basically responds to the message. The server looks in its routing table, goes to its default route, and that's how messages are passed back and forth. That's how messages are passed back and forth. So we're going to actually start getting into some of the math of subnetting pretty quickly. And, some of that's going to be fun. But before we do that, I want to make sure that we've given you guys some, we've had a chance to go through some questions, because we've been babbling for about an hour and, or at least about 35 minutes. And, some of this stuff gets relatively complicated fairly quickly. So let's take some questions. Chris, it looks like there's some stuff in there. If you want to come and bring some of the questions onto the StreamYard screen. Hey, Mike, can I please guide when you use Class B versus Class C? Raul, here's the thing. There is no such thing as a Class A, B, or C address anymore. What you really is, you're going to use a /30 on WAN links, and you're going to use a /24 on a LAN link. And pretty much that's what you're always going to use for everything. We can never use a Class B. We're going to have to subnet it down because we'd be wasting 60,000 addresses. So Class C, /24 for LAN links, /30 for WAN links, and that's going to work in 90% of your environments. Chris, you want to bring in the next one? Default gateway is a default route. That's all it is. A router is often called a gateway. So on PCs, they call it a default gateway. If you put a default router on a router, they call it a default route. Same thing. Good question.
And Mike, can you go over the last diagram again? For some reason, your cursor wasn't showing up on the screen, so people couldn't see where you were pointing when you were talking on the last one.
Yeah, I don't know which was the last diagram I was on, though. I don't know which was the last diagram I was on, Chris.
Okay.
Crypto Fiend, you got a bunch of acronyms, and I don't really understand what you mean by VXLAN. Tell me in some plain, simple language, and I'd be happy to understand it for you. Chris, do you want to bring in the next one? One thing I will tell you, if you're in engineering, you ever desire to be architects, don't ever use acronyms. Your customer won't know. In medicine, they teach us not to use acronyms for the following reason. I can give you 50 different definitions of a VLAN. And now that you've got another one, it becomes totally impossible to figure out where it's coming from. So just spell it out exactly and we know what you want. Williams. Okay, that is good, Williams. You're already ahead of us. So the reality is what you're going to see is in the old days, we had class A's with a /8 and a class B with a /16 and a class C with a /24. And guess what? About 25 years ago, we went to classless interdomain routing. And by doing that, we basically moved that thing around. And the whole point of using a class B address with a class C subnet mask is subnetting. That's exactly what we're doing. And yes, we intentionally are doing that. Absolutely. And if we don't, we'll be burning 65,000 addresses every time we use a class C on a single interface. So yes, it matters. And we no longer use any kind of classful addresses. Everything's classless at this point. Good, solid question.
All right, so people are responding about which slide it was. It was a static from the low end and DHCP from the high end slide.
I don't know which slide that is. Why don't we go to a question that I can actually answer?
Okay. I'll wait for some more questions to come in.
Let's answer some questions that I can answer. I don't know what the slide is. I'm skipping around through a 2,000 slide presentation. There's no way I can get to it. But I can actually answer technical questions or networking questions that aren't related to a slide. I don't know, Mohammed. I haven't worked with VLAN extensible local area networks. Yes, we'll be talking about CIDR or classless interdomain routing. Absolutely. /24/23. That's the subnetting we're going to get to. How is the subnetting the same or different? It's almost the same whether you're subnetting a 32-bit binary versus a 128-bit hexadecimal address. It's pretty much the same. Okay, Chris, you can bring in the next one.
There's not any more questions.
Oh, okay. Well, then we can get back to the content. So let me make sure I may do this a little differently on the subnetting piece. Bear with me a second. Okay, so let's talk a little bit more about subnetting. And here's where we're going to talk about how to actually do it. We're going to begin by talking about this concept of the Class A, Class B, Class C. Now, previously I mentioned and I gave you the Class A addresses. And a Class A was anything that began with a 1 all the way to a 126, and it had a /A subnet mask. And then I told you there was a Class B, which had a /16 subnet mask, which was basically 128 all the way to 191. And that was a Class B. And then I told you we had a Class C, which was basically the 192 all the way to the 223 /8. But guess what? They don't exist anymore. We don't use them. They were the address classes. And because of that, we said, wait, I can't use a /8 because if I use a /8, I'm going to burn 16.5 million addresses on a subnet. So about 30 years ago, when we came up with the concept of subnetting, we said, we can't use IP address classes anymore. They're dead. So what did we come up with? We came up with classless interdomain routing, which basically meant we would subnet our Class A's, B's, and C's, and then they would no longer have those silly /8, /16, or /24 masks. So classless interdomain routing really means subnetting. That's it. That's it. So no such thing as a Class A IP address, B address, or C address. They don't exist anymore. They did 40 years ago. About 25, 30 years ago, we went away from it. So keep that in the back of your mind. Now, this was the default mask. So we don't use the default mask. So let's go back to this picture again. With a Class A, it was 8 bits of network and 24 bits of host. So 2 to the 24th minus 2. 16,777,000 addresses. Again, you can't put more than 250 on a subnet. Maybe 500 worst case scenario. Or you get broadcast. So kind of keep that in the back of your mind. So what we did here is as follows. We took a /8 and we subnet it down because otherwise we'll have 2 to the 24th minus 2. We can't use that. Or this Class B. Now, it was cool when in 1980 somebody thought of the idea of a Class A, Class B, and C. And when the internet was designed and it had, 50 users on it, it was cool. But look at everything that has an IP address. So clearly this isn't working. So we decided to subnet it down. How do we subnet it down? We added more bits of network. So the Class B, which used to have a /16, can now have a /29, a /28, a /27, whatever we need it to be to give us the number of hosts and networks that we need. That Class C was a /24, but guess what? And we'll do some labs with this today. We won't use a /24 on a WAN link. Why? We don't want to burn 254 addresses when we only need 2. So to get to our goal, we got to get smart. How do we get to our goal to get smart? What do? We do the math ourselves. So this is what a Class C looks like. All of our, we've got 8-bit network mask bits, another 8 more, because it was a Class B. Now we added 8 bits of subnets. Now we have 8 bits of hosts. So 2 to the 8th minus 2. Before, we had 2 to the 16th. So 2 to the 16th, 65,000 and change, minus 2, still 65,000 and change. Now, we can only put 2 on a WAN link and about 500 on a LAN link. So is it a good idea? It depends on the link. If this is a LAN link, guess what? Awesome. Perfect. If this is a WAN link, not a good idea because we're wasting addresses. So let's look at it a different way. I want you to see CIDR notation, binary notation, decimal notation. So I speak in CIDR notation. /24, /25, /30. Why? Because when I communicate to a networking person other than the end of the phone, and I say this is a /30, they know what that means. In medicine, when I tell another doctor the patient has a macular papular rash, they're instantly thinking of scabies on the other end of the phone call because they know what a macular papular rash is. So we use CIDR notation and CIDR communication because everybody knows what it means in networking. So /24, /30, etc. Now, This notation really is just a number of bits. So look at it this way. Here is your class C. All ones in the network, all ones in the network, all ones in the network, 255, 255, 2550, or /24. Now, let's say we want to take this and chop it down a little bit. We're going to go 8 bits of network, 8 bits of network, 8 bits of network. Oh, wait, an extra bit of network over here, which means now for hosts, we have 2 to the 7th minus 2. Now let's go over here. 8 bits of network, 8 bits of network, 8 bits of network. Oh, wait, 2 more. 8 plus 8 plus 8 equals 24 plus 2 equals 26. Okay. 255, 255, 255, 192. So I'm going to show you where these wacky numbers are coming from in a minute. Now, here we go. We're going to do a /27 now. So 255, 255, 255, 224. Wow. Where is this coming from? 24 bits, right? 8 plus 8 plus 8 plus 3. Now it's 11. So what are my hosts? I have 2 to the 5th minus 2. 2, 4, 8, 6. Hold on. 2, 4, 8, 16, 32 minus 2, 30. Okay. Now, break it down one more. Now we've got 8, 16, 24 plus 4, 28. 2 to the 4th minus 2. 2 to the 4th minus 2. 2, 4, 8, 16. Guess what? Map out 2, we've got 14. No, caveat, 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 warning, 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 warning. If you're on AWS or some of the other cloud providers, they have a funny take on IP networking. They decided not to read the documentation of the Internet Engineering Task Force and make up their own. So when you're dealing with AWS, they get rid of the first 4 addresses and the last address. So in normal networking, the first address is lost due to the network. The last address is lost due to the broadcast. But if you're working with Amazon, they reserve the first 4 addresses and the last one. So go back to this /28. 2 to the 4th minus 5 on Amazon. So 2, 4, 8, 16 minus 5 is 11. So 14 addresses in every network in the world except for the cloud providers, and you may only have 11 there. Why am I telling you this? Because if you're on a cloud provider and you use a /28 and your devices are going to scale, you're going to run out of IP addresses pretty quickly because you don't have enough. So make sure you don't run out of addresses. And I recommend for the LAN, in most cases, /24, 255, 255, 255.0. Now let's talk about some special other subnets. /29. Well, let's look at this. 24 bits plus 5. That equals 29. That's how we got to the /29. 255, 255, 255 /248. Okay, how many addresses here? 2 to the 3rd, 248 minus 2. So 6 addresses. Now let's look at the /30. The /30 is every networking professional's favorite one, because every point-to-point link gets a /30. So let's look at this. 8, 16, 24 plus 6. The mask looks like this. 255, 255, 255, 252. Okay, that gives us 2 host bits. 2 to the 2. 2 times 2 minus 2 gives us 2 usable addresses. Wow. 1 address on both sides of the wire, the perfect subnet for a WAN link. So what does everybody use in the WAN? They use a /30. So keep that in the back of your mind, and I'm going to show you where this numbers come from in a minute. So let's look at the next one, /31. 31 bits of network mask. Now let's think about this. 2 times 2, or 2, because there's no exponent here, minus 2 equals 0. So not a usable subnet. Which gets us into this really wacky subnet called the /32. What a /32 looks like is all ones. No, Now, you can actually, on a router, when we create a loopback, we can create, this is called a host root or a host subnet. And there's a very wacky thing, but we use this for administration purposes in cloud computing. So where's all these numbers and calculations coming from? Let's play with it. Look at it this way. 128, 64, 32, 16, 8, 4, 2, 1. So think about it this way. 1, 1, 1, 1. 128 plus 64 plus 32 plus 16. 128 plus 64 plus 32 plus 16. Somebody added up to me. And now you know what that mask is going to be. So we're going to do a couple of things. We're going to calculate where the subnet begins, and we're going to look at this. So everybody right now, I want you to tell me in terms, what is a slash? Before I even ask you to do this, let's do this. So let's work through this one together. So what do we think this subnet mask looks like for this slash 25? Let's build it in right now. What do we have? We have the subnet mask is a slash 25. So 1, 2, 3, 4, 5, 6, 7, 8, right? 1, 2, 3, 4, 5, 6, 7, 8, right? 1, 2, 3, 4, 5, 6, 7, 8, right? 1, 1, 2, 3, 4, 5, 6, 7. So now look at this. Okay, what do we think the slash subnet mask is going to be? I think I saw it from Aguilo or Angelo, depending on whether you're from Italy or Greece. He figured it out. It's going to look like 255, 255, 255.128. Okay, let's look at the next subnet. Let's look at this slash 27, the 172.16.127. So let's add 2 more bits, dot, dot. So let's figure out what this mask looks like. 128 plus 64 is 192 plus 32. Do the Jeopardy music while you guys answer it. Do 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 do. Okay, what's this mask look like? Okay, 128 plus 64 plus 32. Somebody tell me the mask in the chat box. I even played the Jeopardy music for it, which is humiliating, but I wanted to have fun and just enjoy it. So let's say, what's this going to look like? 128 plus 64. Angelo, 224, fantastic. Sarah Ahmed, 224, fantastic. I'm loving it. See, you guys are getting it. Nitropan, excellent. Earl Owens, excellent, excellent, excellent stuff. This makes me happy. John Clark, 7 Series Beamer, excellent. Nitropan, I'm not really sure what you got there, but we'll work with it. You got it right the first time, Nitropan. So, Dan DTM, fantastic. Okay, excellent. Excellent. Now let's take this one. Let's take the 172.16 1.27/32. What's that goofy mask look like? And this is going to be a cuckoo mask now. We'll add 128 plus 64 plus 32 plus 16 plus 8 plus 4 plus 2 plus 1. I wonder what that would be. Let me go out there and get my calculator. If I can't figure this out in my head, let me get my calculator out there. We're going to do a 128 plus a 64 plus a 32 plus answering it is 16 plus an 8 plus a 4 plus a 2 plus a 1. Exactly, everyone. We got 255. How did I know it was 255? Because we know that this is always 255, but I wanted you to figure it out. All right, you guys are doing great. Now let's do this slash 28. You guys are making me happy. I'm proud of you guys. You're doing fantastic. What slash 28? It's going to be a 128 plus a 64 plus a 32 plus a 16. Bring the Jeopardy music back. Do 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 do. Okay, Ruth, you got it. I'm so happy. Earl, you got it. Fantastic. Alexandra Polikala Imapolia Feristimanos. And I hope you know what I mean by that, Alexandra. But, you know, fantastic. I'm seeing it coming from everywhere. I'm loving this. We're going to go through a few more examples because I don't want anybody doing my free networking training and not be smart, capable, and hireable when they're done. So we're going to go through a few more because I want you to be great. I'm very happy that you got that, Alexander. Fantastic. So now let's play with this /29, everybody. /29. What is that? 1, 2, 3, 4, 5. Okay, 128 plus 64 plus 32 plus 16 plus 8. Jeopardy music. Do 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 do. Wow, we got it. Angelo got it. MJ's got it. I'm loving it. Ruth's got it. Earl's got it. Wow, we're doing good. Okay, fantastic. You guys got it. Now we're going to do one more. We're going to do the /30, which means 1, 2, 3, 4, 5, 6. Jeopardy music. Do 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 do. Okay, I'm waiting for this to come in. Ruth, you got it. 252. Earl, you got it. Alexandros Polikala. Fantastic. Chibuki, you got it. Sarah Ahmed, you got it. Mark, well, not sure. LM, I got it. Eric Strotz, I loving it. 7 Series Beamer and Lavone. Fantastic. You guys are doing wonderful. I am so happy and proud of you right now. So now, here's where we get a little bit of trickiness. Now, sometimes on a networking interview, they ask you where the subnet begins. Where does the subnet begin and where does the subnet end? So let's talk about that. When you look at a subnet, I'd like you to be able to remember this 128, 64, 32, 16, 8, 4, 2, 1. Keep it in your mind. Remember this. And if you don't know, you can always draw it out. 128, 64, 32, 16, 8, 4, 2, 1. Write it out. Now, when we have a /25, we have 2 subnets. We have the 192.168.1.0 subnet. And the next subnet we have is the 192.168.1.128 subnet. 2 subnets, because we have 1 bit of subnet, so it's 2. So when you're on networking, if you're on the router looking at the routing table, or if you have a task as part of your cloud architect, solution architect, or network engineer, network administrator, or network architect exam, they're going to say, where does the subnet start? Where does the subnet start? So if they were to say that, here's the secret. 192.168.1.132. Is this number divisible by this with a number of greater than 1? Yes. Is it divisible with less than a number greater than 2? No. So I know that this subnet begins at 192.168.1.128. I also know this subnet ends by adding 127 plus that, which means it begins at 192. It ends at 192.168.1.255. Now let's go back to this one. It's a /27. So I have to look at this and say, what is divisible by what? So is 27 divisible by 128 with a whole number? No. Is 27 divisible by 64 with a whole number? No. Is 27 divisible by 32 with a whole number? No. Is 27 divisible by 16 with a number of greater than 1 and less than 2? Yes. So now we're going to go here. Where does the subnet begin? I can tell you right now. Take the first subnet goes 172.16.1.0 and it ends at 172.16.1.31. The next it ends at .15. So first subnet begins at 172.16.1.0 and ends at 172.16.1.15. Next subnet begins at 172.16.1.16 and it ends at 172.16.1.31. Which subnet does this belong to? The .0 or the .16? Pop it in the chat box. We'll go back to the Jeopardy music. Do 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 pop. Ba-da-da-da-da, boom, boom, boom. Chris, we got to get actual Jeopardy music or something fun as opposed to me doing this in the background for the future. But okay, let me know in the chat box. Let me know in the chat box. Help me out a little bit. And okay, getting a question mark. So realistically speaking, okay, you're confused. Questions again. All right, so let's try and approach this from a different perspective. Dan, it does begin on the 16th. So let's go back to subnetting. And when we do this, I'm going to subnet a specific subnet down. Just give me a minute. I think I've taken something and I've subnetted down. I think I've got a slide where I've taken a single network and I've subnetted down. All right, so I haven't. Let's just do it in real time. Let's look at this subnet over here, the 172.16/27. /27 means the subnet mask looks like this. 8, 16, 24 plus 3. So that tells us that our subnets are going to have how many people per host? So they're going to have 2. So realistically speaking, that means our subnet mask is going to look like this. So that tells us /20, 24, 20, 25, 26, 27. So that's our what we're dealing with here. So with a /27, if we've got 1, 1, 1, 0, what's that look like? 128 plus 64 plus 32. Somebody tell me what that looks like, because we actually, there's the good news is you guys are confused for a reason. Very good news. So let's do this math one more time. That's the challenge when we do some live stuff. We occasionally may make a math error. So what's 128 plus 64 plus 32? 224, everybody, right? So that's what this mask is going to look like. This mask is going to look like this: 255.255.255.224. Okay, so now how many hosts do we have per subnet? 2 to the 5th minus 2. 2, 4, 8, 16, 32 minus 2, which gives us 30. So now, with Mike doing the Mike math in the background, is 27 divisible by 32 with a number of greater than 1? No. So where does this subnet truly begin? This subnet begins at 172.16.1.0. And this subnet ends at 172.1.1.31. Okay, everybody, now tell me where the next subnet begins at. The next subnet will begin at 172.16.1.32, and it will go all the way to the 172.16.1.63, right? Good, you guys figured out the next subnet. So now what's the next subnet up? The next subnet begins at .32. The next usable address is .33. Ruth, you got it. It goes all the way to 63. So Ruth, now, where does the next subnet begin? 172.16.1. Something more than 63. One more than 63.
Mike, can you pull that text box up some?
That would be a good idea. .64. Where do we think this is going to go to? Somebody let me know. Come on, can 64 plus 31, 64 plus 31, 64 plus 31 equals, hold on, no, yeah, 64 to 95, exactly. And the 95 is what? The broadcast address. Okay, so what do we think is the next subnet, Ruth? After this one, where is it going to begin? Come on, add 31 plus 95. Jeopardy music. Do 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 do. Ba da da dum dum. Ba da 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 da. Okay, so let's do it. Let's really look at that. Ruth is looking like she's doing some pretty good math. So we've got 96 plus 31, and where's that going to take us? All the way to 127. So we're going to have, this is going to begin at 172.16.1.96, all the way to go 31 higher, which I believe is 127. So it'll be 172.16.1.127. So where do we think is the next one up? Next one up. Next subnet, guys. Okay, so if this one ends at 127, where do we think the next one begins? Alexandros, Polikola, exactly, 128. Ruth, you got it. The next one is going to go 172.16.1. God, 128. Ruth, I haven't, 159 sounds about right. 159, because that is 31 plus that. So 172.16.1.159. I'm going to double check because this way I don't make any funny math. We're going to have 128. Whoops. 128. 128. 128 plus 31. Excellent. Okay, so all the way to 159. Now, what's the next subnet, everybody? Where do we think that would start? Where do we think this would go? It's going to be one number higher will be the subnet, which is used by the routers. Then the first host bit will be one more than that. And we go up 31 from the initial subnet address to get to the broadcast address. What would that be? $160, yes. 172. Excellent. 16.1.192 or 160. All the way to 191. Nice job. 172.16.1.191. All right, everybody. So what's the next subnet? We're going to subnet this whole one, and then we're going to do a different kind of subnet.
Hey, Mike, just so you know, you are in front of that text. That table is one image, so you can move that table.
Okay, excellent. Okay, so now we've got it. 172.16.1.192. That's the subnet address. Okay, you guys did it all the way to 223. I'm loving this. Okay, so 172.116.1.223. Now tell me the last one for this subnet, and you can see how many networks were created out of this single one. Okay, where does this next one end? Start 172.168.1.224. Where does it end? Where does it end? Where does it end? What is the broadcast address here? Everybody see this. Everybody see this. Everybody see this. Ruth, you got it. Ruth, gold star for the day. You've gotten the math perfectly. And just yesterday, we were exchanging messages on networking, and wow, you got it. So, Ruth, fantastic. John Clark, fantastic. Summer Series Beamer, fantastic. Loving all of this. So now you know. But while we're at it, we're not going to take this is good enough. You're taking my course, you're going to be capable. So let's do something different. Now, let's go over here and do the /30. What's that going to look like? 255, 255, 255. Okay. Bingo, bingo, bingo. Now, where does this subnet begin? Let's start with the 0 subnet. We've got, let's say the subnet, it's a /30. Let's say the /30 looks like this. It looks like a 192.168.1.0/30. Now, where does this subnet begin? Where does it start? Somebody let me know. Where is that 0 subnet start and where does it end? We've got how many bits here? 2. So 2 to the second minus 2. So Angelo, I don't know whether you're Greek or not. Excellent. Elvis, fantastic. So the first subnet is going to be 192.168.1.0 all the way to the 192.168.1.3. So the .0 is used by the router for the subnet. The .3 is the broadcast. So now, somebody tell me my next subnet. So the first subnet is 192.168.1.0, and it ends at .3. Where's the next one going to go? Where's the next one going to begin? Ruth, Eugene, Kirshen, fantastic, you guys. I see it in this other monitor. You're coming in, you got it right. Exactly. The next one is 192.168.1.4 all the way to 192.168.1.7. All right, we're going to do one more of these because I want to know that you guys get it. And then we're going to go the other direction and do route aggregation. One more. Give me the next one. I'm greedy. You guys are doing so good. I just want to know you guys get it. I'm loving this. I'm so proud of you. Ruth, gold star. Jason, platinum star. I'm loving this. You got it. You guys got it fast. So, wow. 192. 168.1.8 all the way to 192.168.1.11. Woohoo, I'm loving this. Now in a couple minutes, we're going to go the opposite direction. And I'm going to show you why. Angelo, are you Greek with that awesome name? Because if you are, I'll call you Aguilo, which is the way we Greek people would pronounce Angelo, since apparently you're not Italian, but wherever you're from is fantastic. Okay, so now we get it. So now let's do this. Now I'm going to open it up for some questions, and then we're going to go the opposite direction, which is always fun to go with regards to Supernetting. So not really sure what's been going on in the chat box. Love to see what's going on. If you're having a good time, and Hispanic, fantastic. I used to speak Spanish. One of these days, I'm going to relearn it. Hit the like button if you're having a good time. Subscribe, hit the bell, tell a friend. But until that time occurs, if you've got some questions, Chris from my team is going to bring you off mute, or not off mute. He's going to bring in the questions. So we're in a position where we can go out there and do whatever we need to help you. So, Chris, are there any questions in the chat box?
There was one from earlier in that session. Let me find it. Yeah, I gotta find it. It's way back here.
And yes,
Okay.
we do everything.
This was when the answer was starting at 32 and going to 63. I can't. That's all. That's all I can remember to jog my brain.
Okay, so Nitropan, I think what's going on is I actually did the math incorrectly the first time I demoed this, and I said 16 when it should have been 32. So Nitropan, I'm pretty sure that's what you're referring to. If that's not the case, pop it back in the chat box and I'll answer it. But the first time, it's a live show. I did a little bit of a mini miscalculation in my head, and then we fixed it. So that's why there was a little bit of confusion.
And to the person asking about subtitles, we can't turn them on while it's live. We'll have them on once the live stream is finished. The subtitles will be there.
Sounds good. If there's any others, ask them now. Otherwise, I'll get back into the content. I'm having fun with the content. It looks like you guys are doing great with the content, but I like to check in periodically with everybody to make sure you're having a good time, make sure you're learning. And that way it's a live class as opposed to like just something you watch. Chris, it looks like another question popped in. Do we always change the fourth decimal of the subnet mask? No, not necessarily. We could be going in the opposite direction, which we're going to be doing next. And Sarah Ahmed, that's an incredibly good question. When we mean decider, what we're referring to is we don't use Class A, Class B, Class C. It has nothing to do with whether it's public or private. It means we're not adhering to the /8, /16, or /24 boundaries, or those predefined things that somebody defined 30 or 40 years ago. That's all it means. Good question. What is the formula again? I don't know what you mean with regards to what formula. I will tell you to determine host per subnet, it's 2 to the X number of host bits minus 2. And calculating networks is going to be exactly the opposite direction. Chris, if you want to bring in the next one. Can you ask a question regarding codes on TCP UDP? If we're talking about error codes, that's not really part of anything like this. And that's not really in the network engineer scope of practice. Angela, you mentioned /24 LANs. Are there industry-specific recommendations? So pretty much /24 for LANs, /30 for WANs. Now, Angela, I will tell you, when you're designing LANs in the cloud environment, you don't have access to a lot of the cool security stuff we networking can. But what we can do is we could do a /24 and still put our servers in one LAN, but we would create something called a private VLAN, which would make it that the servers in the same VLAN were logically isolated from each other and secure. We can't do things like that on the cloud because we don't have access to the switches. So we have much less security control on the cloud and much less security options. But in the data center, we can segment it out into just a couple of servers, and we can do private VLANs, and we can do MAC address lists in our VLANs, and we can do so many things in our VLANs to keep it secure. But if we're on the cloud, we lose most of the good security, and we're stuck with whatever the cloud provider gives us, which is about half of the security we can build in the data center. But cloud's still wonderful because it's so agile, it's magical. But in high security environments, typically speaking, you're dealing with firewalls and IDS, IPS systems and access control lists, 802.1x authentication, private VLANs, QoS policies, identity and access management things, encryption, routing authentication. I could go on for the next 6 weeks on how to do high security networking. And I've been doing it for a long time. Lots of things to do. When is the /8 ever useful? You know, a lot of times when I deal with a company and I design their addressing plan, I start with the /8. And the reason I like to use the /8 is it gives me the ability to say, okay, this /16 is going to Africa. This /16 is going to India. This /16 is going to Europe. This /16 is going to the US. And this /16 goes to South America. And then I still have so many addresses. And that way I can create a really nice BGP peering session between my regions if I choose to, or route summarization between my regions. So I always start with the biggest block I can, and then I subnet it out for the environments that I have. I learned early in my life, give yourself a lot more than you ever needed. Double it, triple it, multiply it by 10, and chances are you're finally going to get there. So, for example, everything you ever do, if you do it right, it's just going to grow. I remember setting up a voice system for a bank, and they thought they were only going to use it for 5,000 users, so they said 5,000, and I said, no. And I designed it to work with 50,000, and when they said 5,000, and they're like, Mike, we want 5,000. I said, okay, I'm still building the same foundation for you. And in the end, I gave about 8 presentations before the bank adopted my design. And you know what happened? 6 months later, 30,000 phones. And you see, I knew this was going to happen. So basically what I like to do is I like to build in the ability to scale and the ability to grow everywhere. And, you know, when you're a network architect with a lot of experience, you start to see customers have no idea what they're going to need in their network. And then, so I always start with a /8. But, you know, those are those things that you learn. Like, I wish I could say after being a CCIE for about 10 years, that's when you start really learning all the stuff that you've seen people break. And then you're like, okay, we've got to do this, this, and this. But it's a great question there, Network Bra. An extremely good question, because normally there'd be no reason to use anything like that. But I like to give myself a lot of room to grow. How many bits in a routing table? I'm not really sure what you mean by that. Because if you're dealing with a IPv4 subnet, you're going to have a 32-bit address in a routing table. If you're dealing with an IPv6 subnet, it's going to have a 128-bit hexadecimal address for each route in the routing table. But it's not about how many routes in the routing table. It's about how many routes in the routing table. So if I connect to 3 different internet service providers, typically speaking, I take in about 800,000 routes per internet service provider. If I'm dealing with a customer that has 40,000 remote locations, which is nothing for me, I'm dealing with 40,000 subnets just for the WAN links. I'm then dealing with 40,000 subnets just for the loopback addresses on each WAN link, on each router for the most part. And then I'm dealing with as many subnets as I need for the LAN links, which is probably another 15 or 20,000. So it's pretty normal to me to deal with enterprises that were not, nobody thought of their IP addressing plan, and they've got 100,000 routes in the routing table. So, and then they have problems, and then they hire an architect like me, and we basically re-architect their network, re-architect the designs, put this subnet's here, this subnet's here, and then share routes and route summarization. Everything works great. So whoever's doing your IP addressing really needs to be good at network. Usually the most senior person you have. Can I explain the parameters of a 3-day handshake? Sure. Hey, Chris, I'd like to talk to you. Are you willing to talk to me?
Sure.
Okay. Chris says, okay, Mike, I'll talk to you. And then I say, okay, Chris, you agreed to talk to me. Now I'm going to talk to you. That's the 3-way handshake. Great question there, Yash. Excellent question. Chris, you want to bring in the next one? All the rules change with IPv6. It's a slightly different version of subnetting, but we're going to talk about IPv4. My recommendations are as follows: /30 for WAN links, /24 for LAN links. Pretty much use that in 95% of the designs over the last 25 years. Jason Henry. Okay, here's the biggest joke. What's the difference between a cloud and a data center? The cloud is somebody else's data center. That's it. Literally speaking, the cloud is just somebody else's data center. No more than that. So when you go to the cloud provider, what do they have in there? They have servers in there. They have routers in there. They have switches in there. They have storage in there. They have firewalls. They have load balancers. And that's their network. They've got big switches. They've got big routers, all of it. Standard data center. What do they do then? They install the cloud control plane software. And then they chop it up into a virtualized environment and sell you access to their cloud. Now, mind you this, because it's a virtualized data center, it doesn't perform as well as the regular data center. It's always going to be slower than the cloud. In the cloud, but it's super agile. I get what I need. So what makes the cloud possible? To have a high-speed network connection to the cloud. If you didn't have a high-speed network connection to the cloud wouldn't work. So the cloud is just a data center, somebody else's data center that's virtualized. Why is everybody confused on the cloud? I'm going to tell you right now. Because Amazon decided initially to come up with crazy names for their stuff. So, Amazon doesn't call a virtual machine a virtual machine. They call it an elastic compute cloud. Those of us that are architects, we deal with object storage. Amazon thought it would be cool to call it Amazon Simple Storage Solution. Heck, Microsoft decided to call it Blob. Google decided to call it cloud storage. So in the end, people don't even realize that it's the same 30-year-old technology that we've worked with forever. AWS, brand new thing. You can route between subnets. Okay, thank you, AWS. Cisco did it in 1985. So the cloud is just a network in a data center that's virtualized. Now, that doesn't mean I don't love AWS, Google, and Azure. I think they're incredible. But if you actually call a router, and you call a switch, and you call a firewall, and you don't make up a bunch of words to make it complicated, you can do it. Cisco calls routers. They don't call them elastic traffic interprocessing units. They call it a router. You go to Juniper, they call it a router. Everybody knows what a router is. You go to the cloud, they got 50 different names for a NoSQL database. They got 50 different names for firewall. Seriously, call a spade. Would you ever create a WAN connection to the cloud? Dan, you can't have cloud computing without a WAN connection. Okay, think about it this way. I'm at my desk. I want to access my servers, which are on the cloud. If I don't have a wire to them, I can't access them unless they're publicly facing servers. And then how would I manage them without doing all kinds of crazy stuff? So you have to have a connection to the cloud. In fact, Dan, you not only need a connection to the cloud, you need a backup connection to the cloud, and you most likely need a backup connection to the cloud. Well, again, I really don't understand because I see acronyms here. Now, PBR may be peanut butter rotation. PBR could be policy-based routing. PBR could be a test that I run on my patients to check for mental health illnesses related to an STI. So, Genius, I don't know what you mean because you're using acronyms. If you can please tell me exactly what you want, I can answer your question. What are the advantages of using contiguous networks? We're going to get to that immediately. Pretty much we explained the parameters. I send a SYN, someone acknowledges my SYN with an ACK and then sends to me, and I go back to them. So it's the same thing as I described before. Hey, Chris, willing to talk to me? Yes, Mike, I'm willing to talk to you. Okay. And I say, and he says, good. He sends a message to me. I say, good. And we're over there. So, realistically speaking, we're that. So if we had anybody translate their acronym, we can answer it. Otherwise, we're going to go back to the content. Okay, so let's get back to the content. Let's talk about subnetting, but the opposite direction. Okay, so why would I want to do this? Why would I subnet in the opposite direction? So let's think about it. Generally speaking, we use what? /30s for WAN links and /24s for the LAN links. So what does that mean? Well, every time I create a subnet, I have to tell every device in the entire network about that subnet. So let's go play with this. Let's ask some questions. So let's think about this. Every subnet that we create needs to have another route in the routing table. But here's the thing. Right now, so I'm going to show you why we have to do this. Actually, let's go through the math first, and then I'm going to show you why. So 192.168.0.0 and 192.168.1.0, are they contiguous networks, meaning the first /24 is 192.168.0.0, and the next one up is 192.168.1.0. And the next subnet with a /24 will be a 192.168.2.0. And the next subnet on the way up is 192.168.3.0. So while I might want these /24s as my actual subnets, which I do, and the reason is it's about the maximum number of hosts I can put in a subnet before I run into problems. So there's that. But what if I don't want to send this many routes? Now, for example, let's pretend you're in the cloud. Now, if I connect to 3 internet service providers, I take in 800,000+ routes from AT&T, 800,000+ routes from Verizon, 800,000 routes from, say, NTT, and maybe another 800,000 routes from CenturyLink. Now, I've got the best path to multiple destinations on the internet, and I can make a decision. Now, let's look at here. I'm taking in 2.5 million, but if you're dealing with a cloud provider like AWS, they only let you give them 100 routes. So how many routes is 100? None. I mean, none. I've never seen a 100 route network in my entire life. So, but I've had to summarize a lot of routes to get into that 100 subnet range. And I'm going to tell you, the secret to making your network scale and be high performance is having the intelligence where you need it and having the lack of intelligence where you need it. So look at it this way. If I had 3 locations, if I had a location in Florida, a location in England, and a location in Athens, if Athens had 1,000 subnets, and England had 1,000 subnets, and America had 1,000 subnets, guess what? England only needs to know about the single subnet site or range that I'm using. Greece needs to send me their site or range. England needs to send me their site or range and send Greece their site or range, et cetera, et cetera. By doing that, I can put one route in between our organizations. Now, once the traffic gets to the organization, they're going to be smart. So what's it all going to be like? So let's say Chris is in the Tampa, St. Petersburg area. If I knew how to get to Tampa, St. Petersburg when I wanted to go to Chris's house, and I had one path to Tampa, St. Petersburg, and I got there. And then I'm sitting in Tampa, St. Petersburg, and now I call Chris on the phone and say, Chris, how do I get to your house? And he says, make a left, make a right, make a left, make a right. Well, that's what routers do. We can set this up where you know where to go. And then once you get there, the path goes through the most intelligent path without doing this. So we're going to talk about why. So these are contiguous networks, which I see a lot of you have. So now let's think about this. Now let's do our math again. If we do this in the other direction, if we do 192.168.0.0/23, move the host bed over, I got an extra network bed. Now, how many does that mathematically equal this plus this? Will this cover these 2 routes? The answer is it does. Now, what kind of a route do you think I could create? What kind of a subnet do you think I could create out of here? This could also turn into a 192.168.2.0/23. Okay. Now, what if, now I could now send 2 routes as opposed to a single route to AWS, for example, if I was using the cloud. Now, do these 2 routes, can I summarize them down to 192.168.0.0/22? Does this encompass all of this? Yeah, it does. Yeah, it does. So let's have a little more fun with this. And let me actually fix some of these slides. I am very privileged. I have some really good graphics people assist me. But every once in a while, the numbers that I put on my little napkins that I say, here, please draw this. Sometimes I could do a better job of giving my graphic artists, who are really incredibly talented and wonderful and super smart people, a little better information than just what I do give them. So let me just fix these addresses real quick over here. Okay, 5, 6, 7, and then let's get rid of this. Okay, so now let's look at these. 10.0.0/24, 10.0.1.0, 10.0.2.0, and 10.0.3.0. That's a /22, right? I can aggregate all of these as a /22. So it'll look like this. It'll look like 10.0.0.0/22. Now, what if on the bottom, 4, 5, 6, 7, I decided to summarize these into 10.0.4.0/22? And now, what if I decided to aggregate these two together into the following? 10. Oops. .0/21. You guys see this, how we're creating summary addresses? So why, Mike? Why are we doing this, Mike? I don't understand. Why does it matter? Why are you saying these addressing plan is so important? If you do your addresses right, and we use what's called contiguous addresses, I'll show you why it's so elegant. And if you do this wrong, I'm going to show you how we break things. And we can break things really easy here. So now let's look at this. This was someone that does not know a lot about networking. This is someone that's a Linux sysadmin, a Linux sysadmin, and somebody said, hey, you're a network engineer for the day. And they said, but I don't know networking. And they said, guess what? Get a subnet calculator. So in this particular environment, we've got this person that put 3 subnets in the data center. Now, mind you, we'd have 300 subnets in the data center, but let's say it's 3. And 1 subnet on the cloud. Now look, 10.0 is here, 10.0.1 is here, but 10.0.2 is here. So how many routes do we have to send to the data center for the cloud to make this work? Every one of them. And how many routes does the cloud have to send us? It's 1. Is there any magic that I can do here? Absolutely not. Absolutely not, because our subnets are not contiguous. Now, granted, I could put these 2 in a /23, but it's ugly. It's ugly. So by comparison, let's look in this environment. Let's say we had somebody that was smart, that knew a lot about IP addressing. And let me move this over to another slide so you can see this, because my head's kind of over there. So let's say on the cloud, we used 4 contiguous summarizable subnets. And in the data center, we used 4 contiguous summarizable subnets. Now, the cloud only needs to send a single route. The data center only needs to send a single route. Look how scalable that is. So how are we doing this? Why does it all matter? Why do I like my /8s and why do I begin? We begin this for the following. So look at it this way. Data center. Because this is really what we're talking about now, and this is real networking. And this is the kind of stuff network engineers, cloud architects, solution architects are going to be dealing with in today's world. Let's say this is going to be AWS. They're always going to be on 2 clouds for the most part, because a single cloud is a single point of failure, no matter how many availability zones you use. And all the cloud providers have proved it to us with multiple global outages this year. And what are we typically going to do in one of these environments? We're going to have a couple of routers on each side, router here, router here. Well, actually, it's going to be 2 routers, but just for argument's sake. So we've got a couple of private lines going in each direction. You've got a private line in this direction. Now, look at this. If we start with this 10.0/8, so in the data center, look, 10.0.0.0/16, because I'm subnetting my /8 down. Now, over here, I'm going to have 10.1.0.0/16. Now, down here, I'm going to create another one over here. Now, how many routes need to be sent anywhere? Guess what? I'm sorry, this is a 10.2. Azure needs to send 1 route to our data center. AWS needs to send 1 route to our data center. And we may have 1,000 subnets in our data center, but we only need to send 1. All we need to do is tell either provider over here, hey, by the way, This is all you need to do is reach 10.0.0.0/16. So one route. When AWS says, hey, we can only take 100, we say, oh, 100, no big deal. We had some CCDE and CCIE networking people design our networks. You can have one route. Or most likely what I would do is I would probably leak a specific subnet on this route, and it leaks a specific subnet on this route, add an aggregate route on both, and then I could load share and have 2 links and not have any out of order packets and magic, and life is beautiful. So it's beautiful. That's why we have to be careful. That's why we want contiguous subnets. That's why the person that's doing the IP addressing needs to know a lot about networking, because that is the most complicated part, is determining your addresses and determining your subnet. So go back to this, play with it a little bit more. And the next thing we'll do is we're going to calculate some more subnets. We're going to analyze some more subnet masks. And I'm going to make sure by the end of the day, every one of you has a good grasp of IP addressing, subnetting, and everywhere in between. So let's do this. I don't know how long it's been since I've taken questions the last time. So Chris, if you want to check and see what kind of questions were there, let me know. If you're having a good time, please hit the like button, comment, forward to friends, for example, and I'll wait for some questions to come in. Difference between an access switch and a core switch. What a great question. And we start talking about architectures. We're going to talk about the core, distribution, and access layers. But I'll give you a little bit of a brief answer right now. The core is our fastest routers we've got. They're layer 3 switches. They're routing real fast. Above that, what do? We have a set of distribution switches. And what they do is they bring stuff into our core. And then we plug in switches called access switches, which is basically where our users are. So we typically segment our network into the core. Think your biggest, baddest routers. Distribution, connections to you, to the core, and access is where your users plug in. We will spend a lot of time on these architectural concepts because they are very important when we do that section. But great question. Chris, if you want to bring in the next one. Will you be using Supernetting on your WAN connections to the cloud? You won't have a choice if you're dealing with normal networks, because the cloud providers only take like 100 routes, which is absolutely nothing. No. Dan DTM, why? If Amazon has 1 million customers and each one sends them 100 routes, that's 100 million routes. That's a lot of routes. So you got to look at why they're in this predicament, because they've got millions of customers. So, you know, when we say a normal router can handle a couple million routes, if we're dealing with an internet router, we've got to remember they've got a lot of them. So because of those extreme limitations on the cloud, and we've got extreme performance limitations everywhere on the cloud. Everything we do in the cloud, we're going to have to modify our subnets. We're going to have to do extreme workarounds to make the cloud secure, virtual firewalls with load balancers and virtual IDS, IPS systems, because we can't do a lot of things. Layer 2 access control of 802.1x authentication, private VLAN. So we got to get extra cautious. So we'll almost always be supernetting on our WAN connections to the cloud. Chris, you can go to the next one.
There's not any other questions right now.
Wow, fantastic. So if you guys are caught up, not having 1,000,001 questions, let me know you're here by typing hashtag CCNA. Hashtag CCNA. If I see about 100 of them across the screen, I know you're awake and you're not sleeping. We'll get back to the content. Okay, it looks like you guys are getting it. I'm pretty happy. Let's do a little more examples together. I'd rather do this than go through some prepackaged content. Let's do some subnet mask conversions. So let's do this. Let's take a Class A address. We'll take a 10/8.
Make sure to share your screen, Mike.
So what's this going to look like? It's going to look like a subnet mask of 255.0.0.0. Okay, everybody see that subnet mask? Okay, so now everybody, let's do a little bit of architecture work. New York. Let's pick a couple of cities where we've got lots of wonderful students throughout the world. Let's say we've got New York. Let's say we've got London. We've got a really magical student over there in Hungary. So we're going to say Hungary. Or should we say Bulgaria? So we'll say Hungary because even though she's from Bulgaria, she's in Hungary. And because she's in Hungary and I'm from Greece or my family's from Greece, we're going to put Greece over here. You know what? While we're at it, let's pop in a location in Dubai. And while we're at it, let's have a little bit more fun. Let's add another one. Let's add Lagos, Nigeria. It's becoming very rapidly a pretty big tech location. So these are kind of the environments that we have. So now let's say we need to create a really high performance network between all of these. And you're given the subnet and the address block of as follows. 10.0.0/8. These are the addresses that you have. Now, you will never have, ever have the need for more than 32,000 addresses per location or subnets. You will never need more than 32,000 addresses per location based upon subnetting size. So what does that mean? 32,000. So how many addresses do you have right now? 10.0.0/8. 2 to the 24th minus 2. Somebody want to do that kind of cool math and tell me how many addresses they've got? 2 exponent 24 minus 2. Two exponent 24 minus 2. Somebody give me that math. Somebody give me this math. 2 to the 24th minus 2. 2 exponent 24 minus 2. Jason got it. Alexandros Polikala. Fantastic. Kershin, you got it. I'm seeing it. You guys got it. So we got a lot of addresses to use. 16,770,000 exactly. We got a lot of addresses. Are we going to ever need that many? No. Nowhere close to it. So I said you'll never need more than 32,000 addresses. So you could give me for 32,000 addresses, or you could say, I got 16 million. I'm never going to run out of them. Let me do something more. So if instead we looked at it and said, we think we only need 32,000, but we want to double it, we could use a /16. So 2 to the 16th minus 2, everybody. 2 to the 16th minus 2. Tell me what that turns into. 2 to the 16th minus 2. 2 to the 16th minus 2. Jeopardy music. Do, 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 boop, 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 boop. Okay, so 2 exponent 16 Alexandros. Polioreo. You got it. It's like 65,000, some crazy number. Kershang, you got it. Fantastic. So I said you're never going to need more than 32,000, but Babita, yes. Jason Henry, Jeannie, Sarah, all of you guys got it. Perfect. Perfect, Sanchin, perfect. So what if we were to do this? If we make New York 10.0.0.0/16. And let's say that we made London 10.0.1. I'm sorry, 10.1.0.0/16. And we decided to make Hungary 10.1.0.0 or 10. I'm sorry, it's going to be .2. These are all beautiful contiguous subnets /16. Now let's say we've got Greece that wants to use 10.3.0.0/16. Let's say we've got Lagos. We've got a lot of wonderful people in Lagos, Nigeria. We've got 10.4.0.0/16. And we've got Dubai. 10.5.0.0/16. Okay, now let's look at this. Add some networking connections. Add a bunch of networking connections. We'll have some fun over here. We'll connect this to this. We'll connect London to Hungary. We'll connect Hungary to Greece. I'm going to move Greece over here for a reason. Then we're going to move, we're going to connect Greece to Lagos. Then we're going to connect Dubai to Lagos, Nigeria. While we're at it, we want a little redundancy. New York and Greece are really important because my family's there, so I'm going to have another connection there. London and Dubai have a lot of business relationships. And Ivadoikya over there in Hungary works with a lot of my students in Lagos, Nigeria. So now we've got a full mesh environment. So there's this. Now, realistically speaking, we decide that we're going to connect to the cloud. We decided that we're going to connect our New York office to the cloud. And we're going to have 2 direct connections, private lines from New York. What subnets does the cloud need to know about, realistically speaking, to make the optimized routing work? We've used contiguous subnets for everything. I can send, how many subnets do I need to send to the cloud for them to be able to reach back to all of my locations? Okay, so I'm asking all of you guys, how many subnets do I need to send to the cloud to make this work? Just to make, Jeannie, yes, Jeannie, yes, I'm so happy. All I need to send is 1 subnet. I can send a 10.0.0/8 or could I somehow summarize this, 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 and this, and this into potentially a 10.0.0.0. Now, how many bits would I need to go to cover 1, 2, 3, 4, 5? I don't have to send the full 10/8, right? I could send a 10.0.0.1. All I need to do is accomplish the subnets from 0 to 4, and then I can probably go to 10. So yeah, exactly. I could do a /10 and send a single subnet. Or I can send this. Or what could I do? I could say, hey, on this link, we got a lot. I could load share. I could say on this link, send 10.1, 10.2, and 10.3. And on this link, send 10.4 and 10.5, and then a summary route just in case the links fail. That's what we're talking about. That's what we're trying to architect around. That's what we're designing them. Making sure we only send what we need when we need it and nothing more. That's what we're trying to talk about. And that's why this matters. So let's look at some basic subnets that my team drew just to walk through it. Here we go. We've got a server 172.16. It's in the 1.0 subnet. We've got a /24 for a WAN link, which means we wasted how many addresses? 254 minus 2. So we've wasted 252 addresses by using a /24 and a WAN link. That's what we use /30s. Okay, now let's see this. R1 connected to R2, another /24. Now we've got a /24 in the LAN, which is perfect. And that way this system, she can talk with her and he can talk with him. So, this is a perfect kind of design in the way we'd naturally do these things. So let me just look and see if there's anything more I want to cover in this section. And then maybe we should configure some subnets on some routers and then try and play with it. So let's do this. Let's open it up for a couple minutes of questions, even though I don't think there's going to be that many. And then we're going to start to get to some labs, have some cool fun on some routers. And we'll get into operating Cisco routers, which is all kinds of fun. So are there any questions before we go into the next chapter? Chris, is there anything for me before I go?
I'm just waiting to see if there's any questions.
Sounds good. Yeah, we are in a delay between you and us and them. How many parts are left in this series? I think we've got about 7 or 8 days left. It's a lot of content here. Please go back and watch the first 2. They're there. We're going to leave them up permanently. My /10 because we had a /8 and we wanted to go up one more, which would get us to a /9, which would give us the ability to aggregate 2 of them. And then we wanted to aggregate 4 of them, which would get us to a /10. And then actually wanted to aggregate 11. We wanted to aggregate 8 of them, which would actually be a /11. It was someone in the audience that said /10, and I didn't do the math myself. You can watch these videos, Jim Weaver. We don't provide our intellectual property or our own internal slides ever to anyone. Any other questions there, Chris?
Not yet.
Okay, well, if there are not, keep going through the content, which I'm totally always happy to do. So let's have a little bit of fun. So let's look at a couple of different kind of situations. Typically speaking in networking, we're going to have something that looks like this. We're basically going to have our data center, which we're going to call a central site. And that's going to plug into a WAN router, which is either going to have an Ethernet port or it's going to have a serial connection. And if it has a serial connection, what we have to deal with is we deal with something called the CSU DSU. So what happens is we call the phone company and they bring in a WAN connection to our house or our DFS or data center. They terminate it in something called the CSU DSU. And basically that is their stuff. That is the point of demarcation between our network and theirs. Now that CSU DSU supplies some information to our routers, such as clock rate, etc., etc. So, keep that in the back of your mind that we have that cable. And with that, it provides that. So typically speaking, that's the way a WAN works. Provider comes to you. They basically terminate their equipment or their data communications equipment. It looks like a CSU, DSU, and we plug it into our devices. Alternatively, there are some routers that we can plug that internally to the router, but basically speaking, that's something that terminates the connection. So now we're getting into the official Cisco way of the way they like to teach you how to configure their routers. So let's teach it the official Cisco way right now. I've been having a lot of fun with you guys, just making some stuff along the way. And I like doing that for a reason, for the following reason, and it gives you guys a chance to really get good at stuff. So, but let's just play right now with a single router. Let's close this lab. We'll create a new one. And as soon as I do, I'll share my screen. There's lots of simulators out there. By far the most robust is EVE-NG. EVE-NG is what you use if you actually worked at a networking company. It's what you would use if you worked at a consulting firm. There's some free things like GNU3, but they're not real robust. They're good for practice labs, but if you really want to test anything for real, you're either going to need to buy real routers, you're going to need to buy an EVE-NG server. There's a community free version of the server you guys can use, and it's great. We obviously use a much bigger, more sophisticated thing because we're a school. So let's keep that in the back of your mind. We're just going to call this basic router config. Going to see if it needs us to do this. So now we're going to add one router.
Hey, Mike, you're showing your slides, not your EVE-NG.
Oh, well, I knew I was doing something goofy. So thank you so much. So here we've got a router. Let's launch a router. We're just going to give it extra Ethernet ports because we don't know whether we're going to need it or not. Going to make it work. Oops, I didn't mean to do that. So let's come. Now we're going to turn on a router. Now we're going to console into the router. And this is going to be like any other router. What is it doing here? I'm going to tell you right now. This simulator is basically a server that has server virtualization. The server is running in multiple virtual machines and or containers based upon what's going on, the different devices we're using, individual routing software. So if you go to many kind of major tech company, they're going to be using something like this, and they're going to be running simulations. They're going to be testing firewall software, router software for whatever projects they're going to be using. And you can connect these systems to your network, push huge amounts of traffic to your network. This stuff is really, really cool. When I was younger, we literally built out proof of concepts for all these things. Now organizations are using these kind of tools, specifically EVE-NG, to do proof of concept testing. Fantastic, fantastic, robust software package. Otherwise, you can buy a CCNA rack for about $150 to $200 on eBay. Again, very helpful. We're going to let this system boot. So come on, router, wake up, wake up, wake up. It'll be with us in a minute or so. Okay, so router comes up. Would you like to enter the initial configuration dialog? Never. The answer is no. Would you like to use DHCP to assign an IP address to your router? No. Would you like anything to be automatic? No. If you do, here's what's going to happen. You're going to have network devices that are going to change addresses. You're not going to be able to find anything, and it will be a nightmare. Literally speaking, a nightmare. So everything's going to be static. So I talked about it a little bit, but I want to make sure you guys know it. So we are right now in user mode. User mode, meaning can't do much. I can do a little bit of show command, show IP interface brief. Let's see if it even lets me do that. Lets me see some stuff. Okay, what do we see on this computer? Router, same thing. We see 16 gigabit Ethernet ports. Wow, that's a lot. Now, are they up? No. Gigabit Ethernet, unassigned. Method, okay. Administratively down. What does administratively down mean? It means in the configuration. So run int T0/0. Let's look at this interface. What does it say? Got an interface? There's no IP address on it. It's shut down. That's not why it's working. So let's add another router. Node. Cisco iOS router. Let's give this guy 16 ports too. I have no idea what kind of labs we're going to have fun building today. I mean, I've got some labs planned, but you guys are doing so good today. I might just have you guys do some more fun stuff along the way. Let's start this guy while we're starting this router. While we're at it, let's create a connection between these two devices. G00, G00. Okay, now that's going to change things. Okay, so now you can see our routers side by side. Router over here. So let's go back to this thing. Now let's configure this thing. So we can show interfaces, show IP interface brief, which is going to give us a list of everything. We can do show interface G0/0. Now watch what we see. We see everything. We get to see the hardware. We get to see its MAC address. We get to see the maximum transmission unit, the bandwidth, the delay. And this is administrative things that you set, the reliability, the load, et cetera, et cetera, et cetera. So next, what do we do here? Probably should put a name on every computer, right? If you've got 1,000 devices that say router, will you be able to find it? Of course not. So how do you do this? Config T. That enables you to get to what? Configuration mode? We'll put a host name. R1. Nope, it changed. Let's see what else is next. So now let's go to this router. Let's go back. Let's go in it real quick. Let's go into this device. Would you like to enter an automatic anything? No, we don't do any automatic everything. Okay, let's just give this thing a name, because if we don't, we're going to run ourselves into trouble. We're going to go to the interface. We're going to give it a host name. Let's call it R2, host name R2, so we can identify it. So let's go to that interface, G0/0, where we created that connection. Let's give it an IP address. Let's say 192.168.0.2. Let's give it a /30. 255-255-255-252. We're going to turn on this interface. We're going to store that so it doesn't go. Now, let's look on this. Let's look on the device where we actually turned this. Let's go with show IP interfaces brief. Now, look what we saw. We just put a gigabit Ethernet link up here, and it is manual up. Good. Now, let's see what happens if the link goes down. Watch what happens if the link goes away. If it'll let me. Let me bring the link down. Link's down now. Let's see what happens. Look at that. Look at that message. So we'll do a show IP interface brief. Now look, it's manually enabled, but it's down. Why is it down, everybody? The link is dead. Let's bring the layer 2 link back up. Watch what's going to happen. Where you should get a syslog message on our screen. It's going to come. It's going to tell us interfit gigabit Ethernet 0/0 change state to up. Oh wait, there it is. It came up. It came up. Okay, so now let's go to router 1. Interface D0/0. Can anybody tell me what's the other IP address that belongs on this subnet? Everybody tell me the other IP address on this /30 that goes on router 1 that's in that same subnet. We'll put on the Jeopardy music. Do, 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 pop, 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 pop. Okay, what's the IP address on this subnet, everybody? Elvis, nice job. All right, Elvis, I'm loving that. So we've got a one. Oops, let's make sure we're on the right router. We've got a 192.168. Good job, Alex. 168.0.1. What's that mask look like? 255.255.255.252. Okay, well, we'll probably have to tell it the words IP address. So how do you go to the beginning of the line? Control A. We can type IP, A to DR, and now we pop it in. Now, is this link up? Is this link up? Okay, everybody tell me, is the link up? Interface gigabit Ethernet 0/0. IP address 192.168.0.1. Status administratively down. What does that mean? It means I haven't turned it on. Ding, 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 ding. Okay, you guys got it. So can I ping across this link right now? If the port is down, can I ping this 192.168.1 or .0.1? If I can, we got a problem. Time out. Time out. Time out. Time out. Now, if we go to router 1, config T, interface T0/0, and we say turn on, no shutdown, watch what happens. So, configured by the console, line protocol and gigabit Ethernet changed to up, up. So, now are we up? Well, let's go back to the router on the other end. Let's repeat that ping. We're going to lose the first one, and then we're going to have the next 4 go through. Now, each subsequent ping, 100% get through. So why? The first ping, we lost one. Here's why. We did this. ARP! Who has the MAC address for 192.168.0.1? And then, guess what? The other router respond, I have it, but it took some time. And that's why we lost that first ICMP echo message, our first ping. That's why. Now you know why. So let's add another. So now we're there and we kind of get it. So we can now ping across the link. While we're at it, let's create a host. Let's add an additional interface to this, config T. And here we're in the terminal, we're going to create a loopback address, interface loopback 0. IP address, we're going to pick a wacky one. Let's say we choose 1.1.1.1. We're going to give it a host root of /32, 255.255.255.255. It's a host root. No shut. Now, when we look at this, show IP interfaces brief. Ah, we got it. Can we ping our own interface on this router? Make sure it's up. Yeah, we can. Now, if we go to this router over here, router 2, can router 2 ping 1.1.1.1? You guys think it can? Can router 2 ping 1.1.1.1? Why yes or why not no? Well, let's try it. Can router 2 ping 1.1.1.1? No. Why not? Why does router 2 not know how to reach router 1's loopback address? Can't reach it. Now, we could say we have a drunk router, but while we're at it, let's have some fun. Let's create another interface on this router. Int loopback 0. 2.2.2.2. We got to tell it IP address. IP ADDR 2.2.2.2. 255.255.255.255. Now, that interface exists, so IP int brief. Well, it's there. Ping 2.2.2.2. It's local to the device. Woohoo! I can reach it. Now, can I reach it from the other side? Ping.2.2.2. Can. Wonder why. Anybody want to know why I can't ping the loopback on the other router? Why each router can only ping across the wire, but it can't reach any other subnet. Now, why can't we reach these other subnets? Why can't I reach that loopback segment? Anybody know? This is a very critical reason I can't reach that subnet. Okay, well, I'll give you a hint. I want to go to Eva Doike's house. She's in Hungary. I don't have a boat or an airplane. Can I get to Eva Doike's house over there in Hungary? Answer me yes or no in the chat box. I want to go to Eva Doike's house. She's in Hungary, and I don't have a boat or an airplane. Can I swim across the Atlantic Ocean? 3,000 miles without getting eaten? We don't have any path. There's no route. So I want to go visit Eva Doike over there, the miraculous Brew Ranch. Super, super smart, wonderful, wonderful person. One of my amazing students. I can't because I can't swim 3,000 miles in the ocean without dying or getting eaten by sharks, hypothermia, etc. I don't have a route. So could we configure a route? Sure. Config B, IP route. You could do 1.0.0.0, 255.0.0.0. What's the next hop? 192.168.0.1. Now, what's going to happen if I ping it? Oh, we got it. So now, on router 1, can we ping 2.2.2.2? We can't. Why? Why not? Why not? What does router 2 know about? What does router 2 know about? Router 1 doesn't know about how to reach it. So we got a couple options. Config T, IP route 2.0.0.0/8 or 2.0.0.255.0.0.0. Next hop 192.168.0. This guy's 2 on this side, right? Pretty sure it's 2. We have to get the right next hop right, or everything's going to break. .2. Okay. Oops. Now I go over here. Now can we reach that? Can we reach that loopback? Yeah, we can because we have a path to it. So let's think about this. Now let's come up with a different kind of route. So show run. Now let's look at the routing table. What do you see here? You can see we've got the loopback, we've got this. Let's look in our, let's see, do we have any static routes in here? Okay, you can see Mike's put a static route here. Now I'm going to get rid of this route. Yeah, I don't know what the heck happened there. So we're going to go to config, P, no, IP, root, 1 or 2.0.0.0, oops, 0, 255.0.0.0, 192.168.0.2. Make sure that removed it. Check. Now we don't have that route on the routing table, so can I ping it? No. Now what if instead of giving a route, putting it on the routing table, I said to the router, if you don't know where to go, send everything to the router 2. Let's try that. It's called the default route, which says if you don't know where to go, IP route. This means all unknown data, 0.0.0.0, 0.0.0.0, 192.168.0.2. Now I gave it another route that says if you don't know where to go, go here. So let's see what happens. You can ping it. Working. So what we really need is some form of a route that says go here versus go here. Now, could we have just used the routing protocol? Sure. We can do config T, and we can do no IP route 0.0.0.0, 255.0.0.0, 192 or 192.168.0.2. Make sure we got rid of that out of the routing table. So it's not, let's just ping it. Okay, we can still ping it, which is not good. I don't think I erased it completely. I may have made a typo, which apparently I did. So it should say config T, no IP route 0.0.0.0. 0.0.0.0, and the next hop, let's make sure we get it right. 192.168.0.2. Make sure that got out of the running config. And what we can do is we can walk through just some other ways to look at this and see how we could do it. Okay, good. So now we shouldn't be able to ping this again. I'm going to do that. Okay, good. That's not working. Now let's do this. Let's go to this window, do a show run. Let's get rid of the static routes we put there. I showed you we did a static route. And then static routes basically are if you want to do this. So no, okay, so config T, no IP route 1.0.0.0, 255.0.0.0, 192.168.0.1. I'm pretty sure that was the address we have on the outside. Yep. Okay, this should be right. Make sure we got it right. So let's just do a show run. Okay, good. So now we shouldn't be able to ping this side. Okay, so now let's just pretend for a second we were to turn on a routing protocol. So let's do it. We'll go config T. We'll do router OSPF1. I will basically put in 0.0.0.0, 255.255.255. 255, which basically says accept everything. We'll pop it all in area 0. I'll go to the other router on the other side. We'll go to config T. We'll do router OSPF1, which is we're basically turning on a dynamic routing call protocol called OSPF, which I'll talk about in depth. Network 0.0.0.0 255.255.255.255 area 0. Now we could get a little more precision when we did this, but we're not going to do this for the following reason. I'm just looking to get your stuff as fast as we can in here. So let's see, let's make sure that we've got show IP OSPF interfaces. Let's make sure we've got it. Okay. We can do a show IP OSPF neighbors. And we can see that we're forming a neighbor relationship. Now we're in two-way. We need to get to full to where we're going to start to see routes in the routing table. So what should happen is in about a minute, we'll get a syslog message pop up on our screen. There you go. OSPF adjacency change, process number, Ethernet loading to full. So you think we can ping across the other side of the link now? Well, let's see if the route's there. Show IP route. Wow, we got a route to this. We learned it via OSPF. So let's ping it. Now let's go to the other side. You think we can ping the 2.2.2? Let's see. Yes, because we turned on routing. Routing. So, okay. Can we do this? Config T, no router, OSPF1. Would help if you could type. Okay, let's go over to here. Clearly that brought it down. Config T, no router, OSPF1. Let's try another routing protocol. Router, EIGRP. And I haven't used EIGRP since my CCIE exam 20-some years ago. Router EIGRP1. Let's just do this network 2.0.0.0 network. Let's do this. So we have 192.168.0.0. It's just another routing protocol. No auto-summary, because otherwise it'll summarize it. Now, let's go back to the other router. Let's do the same thing. Router EIGRP1. Network 1.0.0.0. Network 192.168.0.0. No auto-summary. I haven't configured EIGRP for a very long time. So I may have misconfigured this, but we'll see. Because I may have actually put in the wrong kind. Show IP, and if not, I'll EIGRP. Fine. Okay, so that's participating. What about this one? Okay, so for some reason they haven't formed an adjacency. I'll go figure that out. I most likely misconfigured EIGRP because it's not something I've done in 20 years. The point being is we need a routing protocol to route between the subnets. Otherwise, if we don't have a path to it, we can't reach it. So there's that. So let's give you a little bit of look into some of the things that are going on via IP. So for whatever I did in EIGRP that wasn't right, let's just fix it. Config T, router, no router EIGRP1, no router EIGRP1. Router OSPF1, network 0.0.0.0.0, 255.255.255.255, area 0. There's a reason we're gonna play with this a little bit. I want you to start seeing what's going on. Config T. No router EIGRP1 router OSPF1 network 0.0.0.0 255.255.255.255 area 0. Let's let this neighbor adjacency come up, and then let's look a little bit about some of the things that I told you which were going on in the network. So we're here. We're here. Let's make sure OSPF is coming up. Show IP OSPF neighbors. It usually takes a little bit to come up. Let's make sure, okay, we're still on 2A. 2A has to go to full. Once we get to full, we'll run a shortest path first calculation. Well, what is going to happen is we're going to get a syslog message. There you go. The adjacency changed. We went to loading to full. Now what we do is show IP route. You'll be able to see we've got full routing. I'm going to teach you something, and I'm going to show you something which you should never do. So again, I'm teaching you a little bit about internet protocol. So don't do this on a real production router or you will break the network. But it's pretty good for you to see what's going on. So if I do a debug IP packet, what I can realistically do is I can actually turn this router into a sniffer or a protocol analyzer. I'm going to do that. And what's going to happen is I'm going to let you see the messages that come across. Okay, so 192.0.0.2 destination 224.0.0.5. That's an OSPF hello. Here's another OSPF hello. We're looking over here. This is all OSPF communication with each other. OSPF, OSPF. Now, I'm going to generate some ICMP traffic, ping, and I'm going to do 2.2.2.2. Now watch, as soon as I send this, we're going to see ICMP messages. Look. Now look at this. These packets look a little different. We see an IP packet with a source address with a destination address of 2. You can see it. I'm going to do it again. Ooh, you see that? Source, which is the reply, going back to here. So we have 192 talking to 222, and then you can see we have 222 responding back. That's the way this works. You talk to them, they talk back. I'll do it again. I'll ping across the link, 192.168.0.2. Watch, the destination address will be different. See it right there. 192.168.0.1 going to 192.168.0.2. Heck, while we're at it, let's get out of the debug. Let's add some more subnets to this device. Enable. Config T. Int. Loopback 1. IP. ADDR 3.3.3.3. 255.255.255.255. Area. Make it area 1. Oh, let's not do that. Let's not do that. Create another loopback. Let me do this. Let me exit this. Exit this. No debug. It's going to drive us nuts. Oh, never mind. No debug. IP. Okay, so we can shut that off. And now you can see we're not going through there. But let's do this. Let's add a couple more. Config T, interface, loop back 2. IP, ADDR, ADDR 4.4.4.4, 255.255.255.255. No shut. Now going back to our router over here, what kind of routes are we going to see in the routing table? Look at that. 1 to 2 to 3.4. Can we reach it? Yes. Can we reach 3.3.3? We should be able to. We have a route to it. Can we reach 4? So we've got a route to it. Oh, we're at it. Now let's see if we want to see what's going on with OSPF neighbor relationships. Debug IP OSPF. One. Now, these devices send periodic messages to each other. So, what's that mean? Hello, are you there? Sending from 1 to this device. And it sends the hello to the multicast address 224. Guess what? Hello, are you there? Guess what's going to happen in a couple more seconds? Hello, are you there? You're going to see it. Anybody ever work with load balancers or DNS and hear of a health check where it says, hey, are you there? Are you there? Are you there? Are you there? So now let's have some fun with this. Config T interface B0/0. Remember, that's the link on the other end of the line. Now watch what happens. I'm going to shut it down. Shut down. Okay, what's going to happen? Are we going to be receiving any hellos from the other router? It sent a hello. Did it receive one? Didn't receive one. We sent a hello. Did it receive one? Sent another hello, but we didn't get one back. This doesn't look good. This doesn't look good. This doesn't look good. Now, while we're at it, another one. Now, let's look at the routing table over. Look at that. OSPF adjacency CHED. Neighbor 1.1. Neighbor is down. Dead timer expired. Okay, so now what kind of routes do we think we have in the routing table? Go to the other router. Do we have any routes to it? Show IP route. No routes. Why no routes? Why no routes? Because we unplugged the cable. We shut down a port. OSPF sent a hello. Are you there? Hello. Are you there? Hello. Are you there? Hello. Are you there? You must be dead. Goodbye. You're not there. Remove it. So watch what happens. Now I'll turn the port on. Interface G0/0. We'll have some fun with it. No shutdown. Now watch what happens. OSPF is going to start sending hellos. Line protocol went to up. Okay, we just sent a hello. Haven't gotten a response back yet. Adjacency change. We send a hello. Okay, we found somebody. Guess what? They sent us a hello. We received a hello. Okay, we sent a hello. This is looking good. Now we're full. We send a hello, they send a hello. We send a hello, they send a hello. Now, do we think we can reach all those subnets now? Let's look at the routing table. So, show IP route. We can reach it all. Ping 3.3.3.3. Ping 4.4.4.4. Big T interface G0/0. Shut down. Watch, we're sending hellos, we're receiving hellos. It's going to go, it's going to go, it's going to go. We sent a hello. Whoops, we didn't receive one. Not good. So we're going to send another hello in 10 seconds. We'll wait 10 seconds to get a response back. No response. Okay, every 10 seconds, hello. There you go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Hello. Oh, no response. Dead. Okay. Line protocol's down. OSPF neighbor adjacency is down. Do we have any routes? No. Wow, that's no good. We can't reach it. Why? Because the link is dead and OSPF misses 4 hellos. And it says Dead to me. Dead to me. Removed from the rotation. We need the network to work. Dead to me. So let's make the routing work. G0/0. No shutdown. Okay, we're having some fun with it. There you go. Can we run more than one routing protocol on a router? Yes, we can. We can run more than one routing protocol on a router. So we're going to be getting into a lot of concepts when we deal with multiple routing protocols on a router. So if a router has multiple routing protocols, the routers are going to have to determine which one. So let's walk through some show commands while we let that one debug because it's kind of fun. Some things to remember. Walk you through some show commands. So we have the show IP interface is brief. You're going to be using this constantly. It's going to show you the IP addresses that are available. If we do a show protocols, we can see what's going on. We can do a show interface. Get lots of detail on that interface. So while we're at it, let's walk through some more Cisco commands for the day. Go through a little more of it. So, hey, maybe we'll have just a little bit of fun. So, well, config T. Well, let's do this. Let's do interface loopback 4. Let's do an IP address. Or add it, and let's call it 5.5.5.5.5. Okay, so we just added another subnet. Now, right now, that subnet's actually added to OSPF. Why is it added to OSPF? The reason that a subnet is added to OSPF is as follows. I used a command that said install everything into OSPF area 0, which we would never do. So let's do this. Let's stop the debug because it's driving me batty. No debug IP, no debug OSPF. Okay, so we shut off all the debugging that I turned on. Let's have a little more fun. Let's just add another routing protocol. So we'll do this. Config P router BGP 1, 2, 3, 4, 5. Now, while we're at it, let's put a network statement of 5.5.5.5 255.255.255.252. Let's also create a summary of 5.0.0.0. Let's create a neighbor. Let's do 1.1.1.1. That's going to bring us into the eBGP multi-hop. Let's not do that. Let's do neighbor 192.168.0.1 remote AS. We picked this one 1, 2, 3, 4, right? 1, 2, 3, 4, 5. So we'll make that 5, 6, 7, 8, 9. Now we'll go over to this router. We'll do a config T. We'll do a router BGP 5, 6, 7, 8, 9. We'll do a network statement 1. 1.1.1. We'll do a network 1.0.0.0. We'll do a neighbor 192.168.0.2 remote AS. 1, 2, 3 was 1, 2, 3, 4, 5, right? Yeah. Okay, so we just formed the BGP relationship with our organization. So now if we do a show IP route on this router, what do we see? You see right now our routes are still being learned via OSPF. Why? It's not in the table because we're dealing with eBGP yet. And is the next hop reachable? If the next hop is reachable, yes. If it's not, then no. So that's what's going to determine whether we get there or not, is whether the route is in the routing table. We can't populate into BGP a route that's not in the routing table. Got routing in here. That's how we would configure an additional routing protocol. We're gonna spend a day doing that because I want that to be fun. But here's the key. What did we do and why did we do it? We did a couple of things for the following reasons. We came up with an IP addressing scheme. We showed you how you could summarize routes. We showed you how you could subnet routes. We showed you how to aggregate this. We showed you how to pop these questions in. So let's take some questions for the remainder of the day. And if there's any questions, I'd like to answer them. So Chris, let me go back to StreamYard, see if there's any questions that popped in while we were having some fun configuring these kinds of things. Sarah Ahmed, yeah, I think I'm going to have that the last thing we do today. I've been pushing you guys pretty hard. Tomorrow is a Friday, so we'll probably push it pretty strong. But I don't want to exhaust anybody. A lot of you guys are doing my cloud architect program plus this. Many of you guys and girls have full-time jobs. So today, yes. Cryptophene, I am so happy. Teaching networking can be a little dry from time to time. So I do anything I can. I try and sing, dance, do a little Jeopardy music. Here's the thing. I know what it was like when I took courses and it was hard to be there. So, I try real hard to make it as interesting as possible. Kenya, you can bring me with you anytime. I know you really well. You're about as sweet, nice, and smart as they come. Happy to go to work with you. Angelo, thank you so much. Here's the funny thing. I've been doing system design so long that I don't even do system configuration because that's what happens when you become an architect. So getting my hands so dirty like this, doing a little bit of engineering, which I haven't done in a while, I think you can assume there'll be some engineering courses coming from us soon because this has been too much fun. These labs are interesting. I'm so thankful. I'm so happy to hear that, Twinkle. Mike, if I tell my kids don't do something, that's exactly going to be the first thing they do. I know, but I wanted you to see the sniffer potential to actually look through the data that's going through the network. And at the same time, I also didn't want you to actually do that on a real network. Now, Eva Doikis, troubleshooting with Cindy is a magical experience because normally speaking, when you get troubleshooting, you can look at a routing table. It's real simple. But when you got a cute kitten that basically chews just enough through an Ethernet cable, to cause electrical signaling problems, but not the line to go down. Wow, we got some interesting troubleshooting. And when Cindy likes to lick her paws and with her wet paws, push the power buttons on my computer, that really doesn't do a lot of good either. And of course, fur all over the vents of my computers and routers and switches is also not very helpful. But I can't imagine not having the little baby girl with me. How should you resolve subnets with overlapping IPs? That is what network address translation is for, until you can readdress it. And that's why I say to people and learn that. And that is not just going to the internet. Company A buys company B, woohoo! And they use NOT between them. Chris, you can bring in the next one. Came in just now, but you're glad to be here. Anthony, we're thrilled to have you here. Come back, watch the replay. Danka, you're welcome so much. I'm thrilled to speak with you. Like I said, I want to train the next generation of the world's best technology leaders. Chibuki, can VRP or virtual router redundancy protocol be implemented between the data center and the cloud? You could, but what you would probably do would be as follows. You would typically set up a private line to the cloud and another private link to the cloud. And then what you would do is you would do multi-group VRP. What I mean by that, you would send one set of subnets on one link and one set of subnets on another link. But realistically speaking, VRP is probably not where we need to go to. We're going to be using BGP and IBGP between them, and we're going to be basically creating some routes. So we might use VRRP or Virtual Router Redundancy Protocol, which we'll talk about on the connections to the cloud. But really, it's BGP that we're going to be using, much heavier. Ruben, thank you so much. And William Byrne, who's an extremely experienced technology instructor, really experienced. We're honored to have him here. He taught at Alcatel-Lucent for forever. Yes, trying to do this live is always brave. You never know what the heck's going to happen because tech doesn't always work the way it's supposed to be. Our assignments are really challenging. Yeah, there's nothing simple about cloud computing or networking, so I have to give you what you need to get you all cloud hired. Yep, agree completely. John, it's always wonderful having you here. So thrilled you're here. Cedre, thank you so much. I enjoyed being on the WAN Podcast Manager. I loved it, so thank you so much. Actually, Chris from my team, if you can pop a link to that podcast, it's a pretty big podcast of networking professionals. We were just there today. We were talking about how to create high availability, high performance networks, specifically with regards to multi-cloud. So it should be very applicable for all of you guys. So Chris from my team, if you can pop a link to that, or better yet, pop a link to the LinkedIn post today so everybody could see it. I'd love everybody to see that. Oh, it's good to see you, MJ. You're more than welcome. Are we going to discuss VBNs, Aquo? Absolutely. Absolutely. Aquo is a wonderful guy. He's a friend. He does a lot of work helping with the War Fund crowd, and Aqua's got a great networking background. Aquo, definitely. I'm honored and happy to see you here today. I would have loved to have met you 10 years ago. You're more than welcome, Sarah Ahmed. Do you have any assignments you can practice on? Honestly, John, I think you should just go through the class this week. What I think you should do after this week is I think you should read this week and next week. I really recommend you read that book from William Odom from Cisco. It is an effective, wonderful, miraculous book. I think the two books together from Cisco Press are about $50. Remember, Cisco wrote the book for a Cisco exam, and it's from Vernal Odom. His CCIE number is like 1064 or something like that. So that is the official curriculum. And I have gotten more people hired from literally tutoring people straight out of that book. So I love that book. Strongly recommend it. I think that's what's really going to help you. And then after the course, if you want to do some kinds of labs, I'll make some recommendations in the end of the class. Sharon, you're more than welcome. Thank you so much. That's what I'm so glad you're bringing people. What I try and do is I try to make it as real as possible, based upon real experience. Angela, thank you so much. I'm so thrilled. Clint Stevens, buy the 2 as a bundle. It's like $50. And I'm telling you, that is a bundle that you should have. Like, I get paid nothing by recommending our Cisco's products. I earn nothing. I'm not an affiliate, but I want you all to have the best careers. And you know who I always recommend? The manufacturer's documentation, the official stuff. It's good stuff. And Chris, you can bring in the next one.
I want to reiterate about buying this. It's not just the book; it's all kinds of resources that Cisco provides. You know, you might not be able to see it, but literally all these resources that you get access to. You get access to all their practice stuff, all their virtualization stuff, all their everything. And since they're the ones that make the exam, that's why we strongly recommend going there. And we share the link to their page for the certification so that you see all the resources available, and not just the book, because it may seem like there's a lot, but it's just one purchase that comes with all this stuff. So I just wanted to pop in to make sure everyone was aware of that.
And you can see that I've been a network architect for 25 years. We still have the official materials for us because we always go with official materials.
Yep. So I'll pop back off now.
No, Chris, I think you're great. Thank you for showing that book. I'm thrilled you did. That's my recommendation. Can I get everybody, if you had a good time, to say hashtag CCNA and hashtag Cloud Architect? My 2 favorite words. Yeah, Sharon, that's my whole goal. I want to make it real, get rid of all the marketing speak, all the fluff, and make it that you guys are all experts. Brian, I think that's great. I'm so thankful Chris showed that. We have class tomorrow. Absolutely. 12 to 3 tomorrow, 12 to 3:30, something like that.
And just to clarify, in case any of our students for the Cloud Architect Career Development Program are seeing this, we don't have that class tomorrow. We have this class on YouTube tomorrow.
Yes, because many of my students had said, Mike, we love you, but you give us a video to watch each day, 10 posts to read each day, or 500 hours of course. If you're going to bombard us with all this networking stuff, can we please have off Friday? So that's why our students are off tomorrow. Cloud Heart, exactly, Aqua. CCNA. Oh, so thrilled to see you. Love it. Absolutely love it. Gabriel, nice to see you. Sharply dressed there. Mick, good to see you. Sharon, Cloud Architect. I love it. So please tell friends to watch this free training. Hand of God, you always have the nicest things to say. Salutations to you, Mr. Mike. You are a wonderful thing. I appreciate your presence on earth. I wish you all the best. I have to say, when I see your messages, they are so warm and sweet, and I appreciate them more than you know.
Yeah, it's almost as good as rubbing my cat's belly. You know, that's
I appreciate it that much. Mark Hema, CCNA. Anthony, CCNA. I'd love to speak to you, Anthony. Chibuki, CCNA. Abigail Marks, yes. CCNA, Cloud Architect, and CAD hired. Carlito's Way, CCNA. Robert Welch, Cloud hired, yes. Danica, Cloud hired, yes. Angelo, CCNA, yes.
So I see where MJ said that they got the book off of Amazon. That is a great place. One thing to keep an eye out if you buy it used, some of the resources may not be available because they're limited to specific uses. So just keep an eye out on that when you're doing those.
But no matter what, use, new, get it. This is some good information, Mark.
Yeah, the contents of the book are still the same.
Yeah, but like, I love that. Sean Ford, I see you more than my wife. You know, the sad reality is I see Chris more than my wife.
I'm not going to comment because my wife is occasionally on YouTube. So,
well, my wife is at the hospital, is taking really great care of her patients half the time, so that's the reason why. Mr. Gaze. So yes, Amazon has them used. It's a great environment. You may, well, thank you, 7 Series Beamer. You know, I got to say, I just love working with the community. Whether I was teaching engineers at Cisco, Riverstone, WorldCom, Comcast, I just like teaching. I'm so happy to have you here.
Do we have an idea of what might be on the agenda tomorrow? I know
I think we do. Let me go through and see what's on the plan schedule for tomorrow. Okay, so I know what we actually have in here. So we're going to start configuring some sample networking and some routing. Then we're going to be looking at ARP tables. We'll be doing with some static routes. We'll be pumping at host routes versus traditional static routes. Then we'll deal with a whole lot more stuff. And then we'll deal with some overlapping routes. And then after that, we'll do some LAN routing, and we'll deal some VLAN tagging and some VLAN trunking. We'll be talking about 802.1q tags, etc. And then after that, what I would be doing, we'll be dealing with some switched virtual interfaces and some routing. That might be a little bit fun. Be doing some troubleshooting of routing, which is going to be kind of fun. And might even do some ether channel kind of stuff. So it's going to be a really fun day. Lots of tech. Starting to get more into the routing concepts, which is where everything becomes fun. So we've got to hit the heavy stuff, the hard stuff, the ugly stuff, the spanning tree, the rapid spanning tree, the subnetting. Now we get to the fun. So have a wonderful night, all of you. It's been an honor and a privilege to know you, to see you, to work with you. Tell others to watch it. If you haven't hit the like, comment, or subscribe, please do so. Please tell your friends. And guess what? If you've not gotten a copy of our free AWS Certified Solution Architect Professional book, please download it. The link is in the description below. Got to know the cloud in today's world. And whether you're a network architect like me, a cloud architect like me, or either way, you still have to know the cloud. So see you all tomorrow. Have a wonderful night. Have a great night. And seriously, get some rest so we can come back tomorrow and have a party.